to record because I always seem to forget. So good morning. And like I said, I'm sure people will keep trickling in. My name is Scott. My call sign is N7JI. I say, got it. And I'm in Eugene, Oregon. And some of you might know me. Some of you probably don't. Most of you probably don't. I mean, I know the relatives of a few of you, possibly. And anyway, a little bit about myself. I've been a ham radio operator since before I was an adult. I got my license when I was the ripe old age of 15. College ham radio and clubs are very important to me. When I was at the University of Maryland, I very quickly found the ham radio club on campus. I basically found the building with the big tower and the beam antenna on it and walked up to the roof or to the top floor. And there was the club and there were people there. And this was like the day before school even started. And so one thing led to another. Within 3 months, I'd upgraded from my novice license, which was the intro license back then, even below technician license, up to extra. And then a month before, that was a month before my 18th birthday. And the guys in the club said, "Oh, you live on campus, huh?" Like, yeah. It's like, well, here's the box. You're going to be the head examiner now. It's like, well, but I can't do it till I'm 18. It's like, yeah, our next exam is in January. You'll be 18. Like, oh, fun. Okay. So I started at that point in a life of doing public service for ham radio, giving exams. And over the next 11 years, I ran a monthly test session on campus, which was a lot of fun. I've given thousands of exams. And then about 6 years ago, I thought, I should start teaching classes because, well, well, for one, I really enjoy teaching. And number two, people tell me that I have a kind of a way of simplifying things that are complicated. So I hope that that's actually true. And I hope you'll find that that's true. And if there's something that that doesn't seem to make sense to you, please let me know. And we'll try to go through it again. Because this class is not for me, although I do enjoy teaching it. This class is actually for all of you. And I have been through the book that we're using. I've been through the audio book. I downloaded it off of, I can't remember if it was Audible or whatever it was, but it only took the guy 2 hours to read it. And this class is 12 hours long, which basically means we've got 10 hours of extraneous chit chat that we can deal with. And kind of like a source information sort of viewpoint where we can get into, not only the fact that this is the answer, but, oh, here's why. And just so you know a little bit about me too, I also work in factory automation. I do all the electrical stuff for machinery. So power design, equipment layout, electrical cabinets, picking cables and conductor sizes and terminals and figuring out how much current something can carry. I also do all the programming. I started programming when I was 8 years old and I'm 53. So I was very lucky that my school system had an old school Commodore PET, a little 4K computer. I got to learn how to program on that thing. And it's one of those things that I am not a programmer, but I have always used it. So I tend to relate to things that are computery, even though I'm actually an electrical engineer. So as I mentioned, I went to the University of Maryland. I was an active participant in the W3 EAX radio club there, which is actually now having a resurgence, which is great. I have my bachelor's and master's from the University of Maryland in electrical engineering. So as technical as you want to get, I can go there. So if you've got any weird questions or anything like that, like I said, this class is not for me. This class is for you. So if there's something that is of interest to you, something that you don't understand and want to understand more of, I'll do my best to get an answer. And if we digress a little bit, apologies to everybody who didn't want to digress, but that's actually where a lot of the really good learning comes from. The fact that, you might learn something new, and to be totally honest, I might learn something new also, because I'm now thinking about something in a way that I haven't had to think about before. Okay, let's see. The next thing we're going to discuss really quickly is the fact that exams are tomorrow. If you're signed up for an exam, exams are tomorrow at 2:00 Pacific time. And what's interesting about this is that I am also, for this group, the logistics guy, which basically means that for tomorrow, I'm going to be making phone calls. And so if I'm going to be making phone calls to tell you, hey, time to log in, your exam time is now, I need your correct phone number. So if you haven't given me a phone number, I need you to do that. And that's why one of the reasons that when people sign up, I request a phone number. The other one is I was just told by the guy who runs the exam group, just looking at this, we've got 12 people signed up for exams, but it looks like 3 people who so far have not finished signing up. So I see some shaking heads. Is that true? Okay. So you've probably seen some notification that, yeah, okay. So in order to take your exam, you have to finish doing that sign up process. So anyway, and again, if you're going to be taking if you're going to be taking an exam, I'm going to need your phone number. And there are a few phone numbers that I don't have. So if you have not sent me a phone number, go ahead and email me your phone number. Okay, as far as logistics go, what I can say about this is there's a reason why hold on a second. Okay. So as far as the exams go, there's a reason why we do 8 hours today and 4 hours tomorrow. So hopefully for those of you who are going to be taking an exam tomorrow, you've done some studying and practicing already, in which case this class is hopefully kind of a brush up session for you. For those of you who haven't and don't plan it, you can come into this class cold, and if you have an engineering degree, by tomorrow you'll be ready to take a test. If you're not a technical person and you've never seen the material before, honestly, you might want to wait a little while before taking your tests. But that's actually okay, because there are many opportunities to take exams. There are in-person exams all over the place, although they've been a little less frequent because of COVID. There are remote exams, kind of like the one that we're doing. And there are regularly scheduled exams virtually every day of the week, if not every day of the week, all over the United States, all over the world. You can basically, if you have a US ID and you can register for an FCC federal registration number, or FCC registration number, you can take an exam. So that can be basically any government issued ID. All right. Well, I should ask, as far as logistics goes, we do 8 hours today and 4 hours tomorrow. And that way we do 65, 70% of the material today. And honestly, all of the math stuff is today. So we're going to be through all the hard stuff today. Tomorrow's going to be a coasting into the finish day. So by the time today is over, the hope is that you will say, oh, well, we did all the hard stuff. Oh, good. Tomorrow's going to be easy. and then go take a couple practice exams. And the hope is that by the time tonight rolls around, if you've taken practice exams, you'll start to see an improvement in your scores, just because there's a lot of background stuff that you will now hopefully know that you didn't know. And you can always go back to one of the ways that I like to work. This is how I how I made it through college. When it came time to exams, I could never remember everything. All right. I could never remember every formula that I had to remember, but I did remember the basic stuff. And if I had enough time, I could go and derive what I needed. So if you have the basics, you can go and figure out, well, you don't have to guess on the answer. You can figure, you can start with Ohm's law and you can figure it out from there. You don't have to memorize stuff. All right. Well, do we have any questions before we get started? Is there anyone who has any questions about, signing up for the exam or anything like that?
I have a quick question. Can you hear me, Scott?
Yep.
Okay, cool. So the test says to bring $15. How does that payment go through for the
credit
test?
card?
Credit card?
Yeah, credit card.
Okay, awesome. Thank you.
And just so you know, do we have anyone below the age of 18? Okay, we have at least one.
Yes.
Okay, so you may want to take an exam. You may want to ask about taking an exam through the ARRL, because the ARRL has a program by which I believe exams are either $5 or free for either would I be able to turn on subtitles? That's a good question. Live transcript. Okay, let's see if that works. Hey, that does work. Can everybody see that at the bottom? Okay, that's good. Recording on. All right, everybody can see the transcript at the bottom, I hope. Excellent. Okay, I see shaking heads. I respond a lot better to it to voice rather than having to look at everybody. So just so you know, feel free to blurt out pretty much anything anytime. That actually holds true for as we're going. This is a class where I'm not really necessarily looking for a hand up or anything like that. If you've got something to say, go ahead and say it.
I don't see any transcripts.
You don't? Okay. Let's see. There's at the bottom of the screen, there's something that says live transcript, hopefully. I have it turned on mine.
Okay. Show subtitle. All right. I think that's it.
Okay, good.
Thank you.
Okay, excellent. All right, so let's see. Other stuff. Let's see. Blurt out your questions. And the other thing is, if you know it's going to be really noisy where you are, please mute yourself. Because if I have to search for it, for like who's got the focus, because that's where the noise is coming from, that gets difficult. So if you've got a barking dog, or let's say you happen to be somewhere where there's a lot of people walking by, you probably just want to go ahead and mute yourself and unmute when you feel like talking. Okay, so where I was going with that was that the ARRL actually has a program by which, if I'm not mistaken, they charge either $5 or free. I don't remember which to administer an exam, and that includes online exams for those under the age of 18. In addition to that, the FCC has a $35 registration fee, $35 license processing fee. If you're under the age of 18, the ARRL has a reimbursement process by which you can actually sign up for and request a reimbursement of your $35 FCC fee. It's the American Radio Relay League's little way of making sure that, we don't want this to be a burden for those under the age of 18, nor should it be. So it used to be free up until about 6 months ago. So they basically created a fund. People's dues and donations feed that fund, and they pay for free licensing for those under the age of 18. Now, you're also in a position where there is also another thing going on with a company called Gigaparts, and you will actually also see at some point something called, well, probably QRZ, and I'm going to share QRZ. Can everybody see the screen?
Yep.
Okay, QRZ.com. This is a privately run website, which is tied in very, very tightly with the FCC database. In addition to that, it's also tied in with most other, because ham radio is a worldwide thing, most other member society databases around the world. People can then take their call sign information, which is automatically uploaded to this, and do stuff like this and create a profile where people can figure out who you are and what you like to do. And the other thing is that, notice this thing that says new ham jumpstart program. So you have joined this class at a convenient time. If you get your license, while supplies last, before October 31st, 2022, you can actually apply to Gigaparts and get a free handheld radio. Pretty cool. It's from what I've heard, it's actually a pretty nice dual band radio. Would normally cost about $70. Okay. Any other questions before we get started? Okay. Yeah, Lucas, you should definitely still take it. It's $15. You should definitely still take it. Unless you want to take that $15 and hold on to it. And, once you sign up for an exam, you don't have to take the exam. You can say, I'm not ready to take it, and then apply it to an exam at a later date. So conceivably, you could take your exam through ARRL and save this for when you're ready to take your general exam and use that to take your general exam or something like that. Or you could just take it. All right. Any other questions? Nope. Okay. All right. So what we're going to do is we're going to start by saying, as far as logistics goes, we have this book called the No Nonsense Guide to Amateur Radio. It's a free download. Hopefully everybody's got it. Did everybody get the zip file that I sent?
Yeah.
Yeah.
Yep. Okay.
Yep.
So part of that was the
Yes,
book,
sir.
and we're going to be going through the book, but we're not going to be doing it in the order of the book exactly. After about page 30 or 40, we do join back with the order, but what we're going to be doing is covering what is radio, right? I like to do this in a way where we basically start from nothing and we work toward, what is all this stuff? Because just starting with electronics or anything like that just doesn't make a lot of sense. This is a radio class, so we're going to start with radio. So the first thing I'm going to do is make sure that I don't screw up my whiteboard. Okay. And I'm going to draw this circle. We're going to ignore this little circle. And now I'm going to take this circle and I'm going to draw two axes on the circle. All right. By convention, this is the x-axis and this is the y-axis. These are perpendicular axes, which means they are at right angles to each other. By definition, we start at 0 degrees over here. And how many degrees are there in a circle?
360.
360. Okay. So one full trip around the circle is 360 degrees, which means that when we get up to here, how many degrees have we now gone through?
90.
We got 90. And when we get over to here, how many degrees have we gone through?
180.
180. And then when we get over to here, that's 270. And then one full circle is 360. What's another name for 360?
Zero.
Zero. Yeah, because it's the exact same place. So the great thing about this trip around the circle is that it's completely repeating. And unless you started counting at some point, you don't know. If somebody just says you're right here at this little asterisk, that has an infinite number of different names. That's either 315 degrees, or it could be, you could have gotten there negative. So it could be negative 45, or it could be 695 degrees, and so on and so forth. So for the sake of argument, what we're going to do usually is go in the first loop. We're going to call it what's inside the first 0 to 360. Okay, so now we're going to erase that circle and draw it again. Okay.
Significant that you're starting on the right-hand side as opposed to the top of the bar or someplace else.
Yeah, you always start on the x-axis at the right-hand side. Okay, so we're starting at 0 degrees, and we always wrap around counterclockwise. That's how we increase our angle. So we now can say, okay, well, now that we have this circle, we can say how far we can have two interesting things that we can say. One of them, we can say, how far in the X direction are we from that line? And the other one we can do is how far from the horizontal line are we in the up and down direction? So what this allows us to do, this gives us a coordinate axis where basically we can have a point X comma Y that says we're at a certain distance X and a certain distance Y, and that gives us a point. Okay, so that's our point XY right there. So how far from the origin, which is the center point, are we when we are at that point? And this goes back to the Pythagorean theorem.
The square root of x squared plus y squared.
Square root of x squared plus y squared. Okay, and that's known as the radius, or z. So in actuality, if we were to take this point and say, show me all the points that are that same distance away, that actually makes a circle of radius r. Okay, so we're getting there. We're almost there. So now we're going to take a very special case of this circle where we have a radius of 1. A circle with radius 1 is a collection of all the points that are distance 1 away from the center. So when we're over here, our distance is 1. How about when we're up here at the top? What's our distance from the center point?
1.
1. How about when we're way down here?
It's always going to be the same anywhere on the circle.
Always going to be the same anywhere on that circle. Okay. Which means that in all cases, the square root of x squared plus y squared equals 1. Whatever that x and y are. So it doesn't matter if it's here or here or here or here. The distance is always going to be 1. Okay, so now we can also say that we're going to name a couple of functions. This is x, and this is y. We're going to say how far, starting on the right-hand side, how far on that x number line are we from the 0 point? So how far would we be when we're over here?
2.
I hope we're 1, right? So we're 1 unit away from the X, and this is at 0 degrees. How about when we're directly up here pointing straight up?
Still 1.
How far from the X, from this vertical line are we?
0.
We're 0. We're right on it. How about when we're over here? Remembering that this is plus and this is minus.
It'd be -1
-1. And how about when we're down here at the bottom?
to 0.
That's back to 0. Okay. So this has a very special name. This is known as a cosine. So the X coordinate is the cosine of that unit circle. Okay, so now we have another function where we're going to say, how far from the horizontal line are we? How about when we're over here at the red dot? How far above or below the horizontal line are we?
0.
0.
0, okay. And how about when we're all the way up top?
1.
1. And how about over here at the left-hand side?
Back to 0.
That's 0. And how about down here at the bottom? We're underground.
-1.
That'd be -1. Okay. That is known as the sine. Anybody ever heard of something called a sine wave? Or a sine curve? Okay. So now what we're going to do is take this, and of these two things, the sine is much more commonly used than a cosine curve. So we're going to say that if we map out our angle and we start at 0 and then we go to 360, and let's make it all the way to 720. And this is our Y value. What's the biggest Y we can possibly get on this curve?
360, right?
Well, we can go up to 1. We can go as high as 1, and we can go as low as
-1.
-1. Okay. So when we start at angle 0, which is over here on the right, that's going to be a value of 0. How about when we come up here to the top? We're going to have a value of 1, and it's going to be at 90 degrees. And over here at the yellow dot, we're going to be at 180 degrees, and we're going to be back at 0. We're going to have our dot there, and then we're going to make a black dot. Now let's make it a blue dot. Another blue dot down here. So that's going to have a value of -1 right here. And now we connect the dots, and we start here, and we go up, and we go down, we go down, and we go back up. That is a crudely drawn sine wave. What's interesting about that now is that what do we do with the sine wave when we keep wrapping around and around the circle? What happens to that picture?
It becomes continuous.
It is. Yeah, it basically just repeats. So when does it stop or end?
Never.
Never. That's right. So basically, when you're looking at it, you don't really know where it started or ended. You just know that for this particular instance, it started at 0 and it ended at 360. So what we usually do is we just look at it from this range, from angle 0 to 360. This is known as one wave because it's an up and a down and back to where it started. The amount of time that it takes is known as the period. And the number of times that this happens in 1 second is known as the frequency. So now what we're basically doing is saying, okay, well, we have this thing that's now repeating. and it's a wave. It's a sine wave in particular. And the number of times that it happens in 1 second is called a frequency. You know, clap, 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 clap. That tells you how many times something happens in a period of time. And the period is how long it takes for one full thing to happen. Okay, so what we've now done is we've created something that cycles over and over and over and over and over. So now what I'm going to do is I'm going to take my phone and hopefully, if it lets me, turn on the flashlight, and I'm going to hide the screen. Okay, can everybody see my flashlight? Okay.
Yes.
So now I'm going to move the flashlight up and down with basically simulating like what would happen with that y-axis. It goes up, it goes down. Here's the 0 point. Up, down, up, down. How far in this direction am I moving? Not at all. Okay, so now that looks like a very boring thing. If I were to plot that in space, what I would get is this. Just a vertical line. Everyone agree with that?
Yes.
Okay. So now what I'm going to do is make it a little more interesting. I'm going to go up and down. And as I go up and down, I'm going to move it to the side. Okay, what kind of shape does that make?
A wave.
That
Looks
makes
like
a
a wave.
wave. That's exactly right. So that converted our up and down movement to something that looks like that. So if I'm moving up and down periodically at the right values, and I move the thing from one side of the screen to the other, that generates a sine wave, which is really the same as a circle wrapping around. Okay, so now let us say that I moved it very, very slowly. I'm going to take this and go up and down. Let me start over here. Here we go. And I'm going to move it side to side very slowly. What can you say about how far those peaks and valleys are from each other?
They're close.
They're very, very close. Exactly. Okay. So they look like this. Okay. But now what I'm going to do is take this and move it really fast. I'm going to go at the same speed up and down. Okay. So my velocity increased. So now instead of looking like this, the sine wave is now stretched. The amplitude, the peak is still the same, but now the distance that it covered is considerably bigger. So what are we seeing here? We are seeing some kind of relationship between something that has a frequency and the picture that it makes as something moves through space. So what we're now doing is combining frequency and period and velocity. So we're combining frequency and period and velocity, and we're actually able to make this out of it, or this out of it, or this out of it. So where do we go from here? All right, where we go from here is that we now have this circle where we're measuring the distance up and down as this angle spins around 360 degrees, starting at this point. This goes between +1 and -1 in the vertical direction. So now we've generated a sine wave. We now have a thing that's sitting on the circle that's moving up and down in that particular, in that particular shape. that particular up and down speed. And now we're going to take that and we're going to move it sideways. And as it moves sideways, we now get something that looks like this. Okay, so now, as this thing moves around the circle, the number of times it goes around a circle in 1 second is called the frequency. And that's, we can call that things per second. It's a something per unit time. And that's a thing per second. We also have a name for that. That's known as a hertz, named after Heinrich Hertz. Okay, so now we have a frequency, which is how fast something goes how fast something happens per second, or how many times something happens in 1 second. So we also have a period, which is 1 divided by the frequency. Because if it's things per second, now this is in seconds per thing. So that is a time necessary for something to happen. So if something has a frequency of 10 hertz, how long is 1 period?
10.
1/10.
It'd be 1/10 of a second. If something has a frequency of 1,000 hertz, our period would be
1/1000.
1/1000th of a second. Okay. All right. Now, it's very important to understand how units work. So if we have things per second, that's our frequency. And in this case, we're going to call it a cycle per second. Think of it as a bicycle wheel going around. That's 1 cycle, 1 full time around. A hertz is a cycle per second. Something that's 100 hertz is 100 cycles per second. So that bicycle wheel spun around 100 times, and the thing that it plotted out made that trip around made that up and down trip, up and down, 100 times every second. Well, now we're going to say that that bicycle wheel is also moving based on the center. It's not actually a bicycle wheel, but we're going to use that. We can also say this is a planet that's spinning, and it's spinning around its center point. Okay, so now we're going to say we're going to add a velocity to it, and velocity is measured in a distance per second. For the sake of measurement, we're usually going to say meters per second, because we're dealing in the MKS system, the metric system. Distances are in meters. So our velocity is in meters per second. A distance is in meters. So now, if we take a look at this, we can actually do a little trick here, and we can say we want to see how far something goes per cycle. So this is our velocity. So what we're going to do is say this is our frequency. So we're going to take velocity, divide it by frequency, and we have meters per second divided by cycles per second. Okay, so those cancel. And now we have something which is equal to velocity divided by frequency, and the end result is meters per cycle. Anyone have a guess what that is? It's a distance per something, distance per time that it goes up and down.
Distance per second.
Well, it's not per second. Remember, that is 1 cycle.
Wavelength.
That is called a wavelength. We have just created something called a wavelength. And that is represented by the Greek letter lambda. So that is no longer a question mark. And now we know that our wavelength is equal to our velocity of our whatever it is divided by the frequency that something is happening. So as it plots out a graph, this is a physical thing. This is now a physical distance. So we have this formula, V is equal to F times lambda. Anyone recognize that? It's okay if you don't. But this shows up in physics all the time. V is equal to F times lambda. Okay, so now if V is equal to F lambda, what we're going to do is say, let's look at a sound wave, which is actually a pressure wave that requires, let's say, air to go through. The sound, the speed of sound at sea level is about 300 meters per second. And let us say that we have a frequency of 300 hertz, which is a note that you could possibly hear, probably or something like that. So what is the wavelength that takes up? We can rearrange this equation and say lambda is equal to V divided by F. And that's 300 meters per second divided by 300 cycles per second. Again, these cancel, and the wavelength is 1 meter. All right, so where is something like this really important? Where is it important to understand something like this?
Well, this is all electricity measurement, isn't it?
Hey Vic, you're dropping in and out of it looks like you're dropping in and out of muting. Try that again.
I'm trying to use the control A as a push to talk button here.
Just push it one time.
Oh.
There you
okay.
go.
Is that working?
That's how it is. Yeah, otherwise it was just repeating. That was weird.
Oh, my bad.
So where is it important to note for instance, we're talking about sound waves that we have a wavelength of 1 meter.
Well, this is basically every measurement. The one that comes quickest to mind is the radio station.
But we're not doing that yet. We're
Okay,
talking about
never mind.
sound. We're talking about sound. Where is it really important to understand? Like a sound wave at 300 hertz has a wavelength of 1 meter.
There's also an answer in the chat too.
Is there? I can't see the chat from here.
Okay,
yet.
yeah, it says bands you can operate on
Nope.
and antennas.
Nope. Remember,
Okay.
we're talking sound waves. I mean, that's what we're using right now. We're talking sound. Where is it important to understand wavelengths when it comes to sound?
Human hearing.
Human hearing. How about anything else? Anybody play an instrument? Anyone play the guitar?
I have my guitar like 5 feet from me.
Okay. Why is a note? Why is a particular string? Why does a particular string play a particular note?
Because the way that they were set for it.
Yep. Okay. How about a pipe organ? Does anyone play a woodwind by chance? I played the flute forever.
I play the flute, oboe, and piccolo.
Okay. Why do you tune your instrument?
Because when it's off tune, it interferes with other instrument sounds.
Right. But why is it off tune? Why
Because
is it
they're
out
not
of
on
tune?
they're not on the same frequency wave.
Right. But why, in other words, how do you tune your, how do I tune my flute? Remember, I played the flute since I was 9. How do I tune my flute?
Flutes, you can move the headpiece, but it's better if you just work with the way the air is going.
Right. But let's say it's way out of tune. You're gonna pull the headpiece out. When you do that, what does it do to the length of the column?
It adds it, so then there's more room for,
It basically creates a room for a standing wave to exist. If you shrink the tube, the frequency goes up. If you lengthen the tube, the frequency goes down.
Hmm.
This is exactly what I just drew. Basically, this wavelength, if I were to create a musical instrument that was supposed to be operating at 300 hertz, that wavelength at sea level would be here. So what would happen if you went from sea level to somewhere else where the speed of sound was different? Your wavelength would change.
Mhm.
Your musical instrument would be a little bit out of tune. All right, so now we're going to use that same formula, V equals F lambda. And now we're going to additionally add something else, which is a special kind of wave, which travels not by pressure, but as a disturbance through space. And it has two components. Let's see, E and M. And it's going to have a vertical component that goes like this. And it's going to have a perpendicular component. Everyone hold up your right hand. This is going to be really important. And take your three fingers and put them all at right angles to each other, your first three fingers. So thumb, index finger, middle finger. This is known as the right hand rule, where you have this and this and this. Notice that they can actually be set up so they're all perpendicular. So what we're going to have is a field called the E field. And then we're also going to create something called an H field, which goes this way. It goes through 0 at the same point. Those are all perpendicular. And the direction of travel is this direction. And this is known as the S field or the S vector. So we have an E and an H, and these are always perpendicular to each other. Right? This is a very special kind of wave. The E is our electric field. And the H field is our magnetic field. They're both sine waves, usually. So a wave that consists of the two of those is called an electromagnetic wave. And important to note that the direction of travel is in the S direction. The E field is your thumb. The H field is your index finger. And your middle finger is the S direction. So basically you have E cross H is equal to S, and you use your right hand rule. If you happen to be left-handed, I'm sorry, it doesn't work for the left hand. It'll be backwards. You can't use the left hand. Unless somehow you can take your index finger and break it, your middle finger and break it and point it so it's pointing in the other direction. All right, so this is known as an electromagnetic wave. An electromagnetic wave, unlike a sound wave, does not require a medium to travel. It will travel through empty space, and it's a really good thing, because if it wouldn't travel through empty space, our sunlight would never get here and we wouldn't be around. So it is a very good thing that electromagnetic waves travel through space. Now, how fast do electromagnetic waves travel? In order to demonstrate that, I'm going to bring up a little graph here. If I can find it. There we go. Can everybody see this?
Yes.
Okay. This is the electromagnetic spectrum. And notice what we have at the very right-hand side of this spectrum. What does that look like, everyone?
Light.
That is light. Not just light. What colors of light is that?
The colors of the rainbow.
Roy G.
Ultraviolet,
Biv.
right?
Yep, Roy G. Biv. Okay, so now if we pull out from this, we back away. What do you notice about all of those different colors? Let's hear some observations.
High frequency.
They're very high frequency. What else?
Very short wavelength.
Yeah, very short wavelengths. What else?
Looks a lot like a rainbow.
It does. Yeah. What else? With regard to where they fit in with everything else.
Different
on the right hand.
frequencies. Different
also-
frequencies make different colors.
Yeah, different frequencies make different colors. You also notice that it's also a very, 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 very small portion of the spectrum.
Mhm.
So it is true. Visible light is a very small portion of the electromagnetic spectrum. So why are they so important? Why can't we see infrared?
Is it because it's such a it takes up such a small space and frequency that we just can't see it?
It's a lower frequency, but why can't we see it?
Our eyes aren't sensitive to that.
That's
this-
right. We're not made that way. Why can't we see ultraviolet? Bees can see ultraviolet. Why can't we see ultraviolet?
Piggybacking off what you just said, right?
Yeah.
Because these are made to see at that frequency and we can't.
Yep. Their eyes have been, you know, have been built to see ultraviolet because that's for a large part of things. I guess one of the colors that is reflected by things that they would normally go and eat would be my guess. I don't know that for a fact, but they can see ultraviolet. We can't see ultraviolet. We get a sunburn from it, but we can't see it. So
We might say that our creator has tuned our eyeballs to a given frequency based
Yep.
on the needs of our particular species.
Yeah.
And other species were treated similarly.
So if you were to look out and see the trees, actually, you know, trees are by and large not green. You know, leaves are not green.
Hmm.
They're much more infrared than they are green.
They absorb all of the light frequencies and then they shoot out green because it reflects rather than absorbing.
Mhm.
Thus we see green.
We see green, right? But also trees actually are they appear more infrared if you look at them with an infrared camera than they do green. But since we can't see the infrared, we can't really see it. So let's see now, if we were to look at, let's say we wanted to see infrared. How could we do that?
Camera lens.
You use a camera,
Night vision.
night vision. So has anybody ever seen something called one of these? Let me pull this up on the screen. Has anybody ever seen one of these?
Oh, clear? Yeah.
A FLIR?
Mhm.
Yeah, basically this is a false color infrared camera that's used to pick up hotspots because infrared translates more intense infrared, shorter wavelengths, higher frequencies transmits to higher relates to higher temperatures. So if you're looking for a hotspot in an electrical panel, you use an infrared camera that gives you false color. You can do the same thing with ultraviolet. And then use a FLIR camera for freeze drying. So that is how we can see things that we can't really see. All right, so now let's take a look at our spectrum again and understand that the electromagnetic spectrum is really, really big. What is, realistically, what is the lowest frequency on the electromagnetic spectrum?
High frequency, right?
Well, I mean, can you go down to 3 kilohertz? Notice that this is actually in decades. Each one of these spaces is actually 10 times bigger or smaller than the previous one. So if you go to the left, can you go down to 3 kilohertz? Sure. Can you
Yeah,
go down
yeah.
to can you go down to 300 hertz?
Yeah, yeah.
Sure. Can you go down to
And-
can you go down to 0.3?
In theory, there's an absolute zero, isn't there?
Yeah, in theory, you could just keep going forever. How about if you go off to the right? You can always get bigger, right? The
Mhm.
wavelengths get smaller and smaller and smaller and smaller, but there's really no end to this. So basically what we have is that below roughly 300 gigahertz, everything to the left of it is called radio. Literally everything that we have there is known as radio waves. And they're just a different color of light, if you want to think of it that way. They're a particular frequency of electromagnetic wave. Light is another frequency of electromagnetic wave. All the way to the right-hand side, we have X-rays, cosmic rays. Those are really, really high frequencies, which translates to a very, very high energy level. And if we really want to get into it, we can actually talk about the fact that each packet of energy that travels as a light wave is also a photon, but we're not going to get into that for the sake of this class. So it's actually a particle and a wave. But suffice it to say that the higher the frequency, the higher the energy, which is why if you go to the doctor and they don't shine red light at your hand to look at your bones. They shine X-rays at your hand to look at your bones because X-rays have much higher energy and they penetrate everything. Whereas red light does not. Similarly, radio waves, because they're all the way to the left, they're lower and lower frequencies. They don't have enough energy to penetrate anything and cause any damage. In other words, they don't tear apart cells or anything like that. However, they do pass through you. They go around you quite well. One of the most common uses of radio frequency energy in your home is Wi-Fi. How about the second most common one? Virtually every house has one.
Microwave.
A microwave oven. Now, did everybody notice right here this thing called microwaves? Between roughly 3 gigahertz and 300 gigahertz. They're a form of radio frequency energy that is a particularly high, that's high energy for radio. And as it turns out, we're going to draw this little molecule, which is really important. Anybody know what that's called?
It's water molecule, right?
That's water. That's H2O. Right? Okay, so it turns out that the resonant frequency of the water molecule is about 2.415 gigahertz. Now, what did we say a resonant frequency is? This is a resonant frequency. Let's see if I can get it to do it. Nope, not really. There we go. Can everybody hear that? Right? I don't pick the frequency that when I hit my cup, it makes a sound on. That's caused by the mechanics of the cup. Similarly, the water molecule has a resonance of 2.415 gigahertz. If I were to throw energy at that molecule at a different frequency, it wouldn't really respond to it. But if I throw energy at it at this frequency, it will cause it to vibrate very, very quickly. Motion is another name for what?
Vibration.
Motion translates to temperature. The faster something is moving, the higher its temperature. So when we get our water molecules in our food moving, what does that do to the food? Heats up the food. So it was determined that if you could generate a high frequency, a high power level inside a metal box and stick your food inside it and dump a ton of energy, and in this particular case, it's about a kilowatt, into your food, it would heat it up really quickly. Much quicker than many other ways, like putting it on top of the stove. And that's why we have microwaves, and that's why they work.
the original name or trade name for the microwave was a radar range,
Yes, it was.
Amana Appliances in Amana, Iowa.
Yep.
Says the farm boy. And that explains why they picked that name.
That's exactly right. And the story goes that they were doing radar testing after World War II. And so here's the microwave test site, and they had radar going out this way. And the idea being that if something was here, it would actually, at a certain size, bounce signals back. And how fast do electromagnetic waves travel?
Speed of light.
Speed of light, that's right. Or roughly 3 times 10 to the 8th meters per second. Or 300,000,000 meters per second. That's actually very important. This is known as C, or the speed of light. Okay, so now if you could bounce this signal off and know that it went all the way to here to some unknown distance, and then you got a reflected signal in a certain period of time, you'd know that it took X amount of time to make the full trip. You could say, well, half of it was going out and half of it was coming back. Divide it by 2 and figure out at the speed of light that it took 0.0000001 seconds. You could figure out the distance. And that is how a radar system works. Basically, it's known as time of flight, because it's basically determining when you put out a pulse of energy, if you see a reflection, that means it hits something and it's bouncing back. Now, the radar range, it is said that this person, notice I said person, that there was actually somebody out in the field, like out here, who was in the field of the radar system when it got turned on. And the person had a chocolate bar in his pocket and the chocolate bar melted. They said, oh, well, what do you know about that? From there, it was a pretty easy step to figure out that, yeah, okay, well, I guess we're transmitting on a frequency that heats something up. And they figured out what it was and said, oh, well, we can commercialize this. Let's make a microwave oven. So they figured out how to generate a large amount of microwave frequency energy at that frequency inside a small box. But now, one other thing about microwave ovens, see, like I said, I do digress a little bit. So we're going to draw a box. So inside a microwave oven, we have 2.415 gigahertz, or our frequency is 24150000000 cycles per second. That is the frequency in our microwave oven. That is the radio frequency energy that exists in our microwave oven, roughly. So we could actually say, using our formula, C is equal to F lambda, because we know that our velocity is moving at the speed of light. We could say this is our frequency. What do we need to know? We need to know the wavelength. We can also write our formula in the shape of this, and I'm actually going to be using this several times. And in this particular case, what we're going to do is we're going to say that because we could write in 300 million for C, and we could then also write in all those zeros for the frequency, but we're going to take 6 of those zeros and make them disappear and replace them with the word megahertz. Because we're doing that, we can get rid of the letter C and just write 300. So we're going to be writing this over and over and over. 300 equals F in megahertz times lambda in meters. We're going to use this repeatedly for a lot of different calculations. It's good that this is the fundamental thing you need to know about figuring out wavelength and relating wavelength and frequency. Okay, but now we also know that the sides of a microwave oven can't have any current flowing on them because they're the sides. So as it turns out, they have to have a 0 point on each end. So it looks like this. Similarly, from front to back, they also have to have zeros. And from side to and from top to bottom, it also has to be zeros. And this is why microwave ovens can only be of a certain set of sizes. It turns out that one wavelength at this frequency is about 12 centimeters. So that's why in a microwave oven, you can also have a 6 centimeter block where it goes from there to there. Microwaves can only be of certain sizes. They have to fit. It's actually known as a cavity. They actually have to be of a certain size because you have to be able to meet the boundary conditions, which say that you have to have zero voltage at each end. That's also why you should never stick a fork in a microwave. Has anyone ever done that by chance? A fork or a knife or something like that by accident?
I had a brother who stuck part of his MRE meal in a microwave at a very young age.
And what did it do to it?
Well, it was a very shocking experience for both of us.
Yeah. Did it destroy the microwave or just set fire to the food?
It almost destroyed the microwave, but it set fire to the food.
Yeah. And that is because if you have a piece of metal here that goes from there to, let's say, there at somewhere inside, you have very, very different voltages. Well, we're going to learn about Ohm's law. E is equal to I times R. And what's the resistance of a metal sheet? Very, very low. So if you have a high voltage between the 2 points, you're going to generate a really big current, which is going to make something get really, really hot. Okay, well, it's 9 o'clock, a little after 9. Is everybody ready to take about a 5-minute break?
Yeah, it worked with me.
Sure.
All right, we're going to take a 5-minute break. I will see you guys back in 5 minutes. Think of lots of good questions. Okay, I'm back. I hope everybody's still here.
Yeah, I'm here.
Any questions? I'm sure there were many. You know what? Like I said, we got lots of time to talk about stuff. There's a lot of good stuff that comes out of discussions. So if you have any questions, it's a good thing to ask them. And if you don't, that's okay.
I've got a quick question.
Yep.
So I never really understood the relationship between like infrared and heat. Why do we use like infrared cameras to see heat and not, I guess, other things?
Okay. So that comes back to something called black body radiation. Ever heard of black body radiation?
No, I haven't.
Okay. So if you want to investigate that, basically black body radiation is the same thing as do you have an electric stove?
I have gas.
You have gas. Okay. Well, we can talk about that too, but do you have an electric oven or anything electric that heats up with an element that you can see? Space
Yeah.
heater, for instance.
Yeah.
Well, okay. What color does it glow?
Red.
Why?
Guess that's close to infrared.
But why?
I don't know.
Yeah. Okay. So it turns out that an ideal radiator is the same as an ideal absorber. And like, for instance, if you ever look at a hot piece of iron that somebody's pounding into a horseshoe or something, that'll be kind of like, it'll start dark red, then brighter red, then orange, then yellow, then kind of white, right?
Yeah.
Okay. Well, it turns out that the frequency of maximum emission is a result of temperature. And it actually goes back to quantum physics. So you basically have the higher the bluer the light, the greater the energy and the greater the temperature that's causing it.
So that's particularly visible in infrared.
Well, the thing is that infrared, the things that we use infrared for instance, let's say you go to the doctor and they put like a little probe in your ear and they take your temperature. Anyone ever had that? Or like on your forehead?
Forehead, yeah.
Yeah. Well, the reason that works is because what that is basically a very sensitive infrared camera, and it's looking for a peak intensity of wavelengths. It's saying, where in this range am I getting my peak intensity? The temperature shifts the peak. That just happens to be a very, very, very sensitive camera.
Interesting. All right. Thank you. Yeah.
Mhm. And that's exactly what an infrared camera does when it does false color imaging. The hotter something is, the redder it is, or the bluer it is. But since we're in infrared, it's looking for wavelengths of infrared light and putting them on a chart, basically giving you a 2D representation of it. Any other questions? Okay, so I wanted to show you guys this again, and notice that we're dealing in radio waves. Here's 30 kilohertz, 300, 3 megahertz, 30 megahertz. Each of these is a factor of 10, right? So what I want to focus on are these three things called HF, VHF, and UHF, and those frequencies up above. I can guarantee you with 100% certainty that you will be asked one of those three. What the frequency limits are on either HF, VHF, or UHF. So repeat after me. HF is 3 to 30 megahertz. We're going to cover mega in a little while. Yep. VHF is 30 to 300 and UHF is 300 to 3000. But very often we'll replace the 3000 megahertz with 3 gigahertz, which is 3 billion hertz. So I can almost guarantee, I can guarantee you that every test will have one of those on it. Okay, now, if you start wondering, okay, well, why can't we use just any frequency that shows up on that whole chart, right? There's a lot of frequencies, right? These are the frequency allocations in the United States. And notice it's split from 3, and over here is 30. And then from 300 to 3 megahertz and 3 megahertz to 30 megahertz and so on and so forth. Do you notice all those different color bars? In fact, look at that. Here's that exact same thing that I just drew with high frequency, very high frequency, ultra high frequency, infrared, visible, ultralight, ultraviolet, X-rays. They actually went all the way to gamma. This actually shows the radio spectrum magnified above. And notice all those little colored blocks, right? Everybody see how busy that looks? Well, what I want to focus on is notice all the way on the left-hand side, these little teal ones that say amateur, all right? Now, you will notice that there are a few significant blocks that say amateur, like this one, 3.5 to 4. That's also known as 75 or 80 meters. 7 to 7.3, that's 40 meters. 10.1 to 10.15, that's known as 30 meters. Here's one that's 50 to 50.4, which is known as 6 meters. All right, so why are they known by the number of meters? So we're going to go back to our equation. (300) F and lambda. And we have, let's say, 50 megahertz. All right. So the one we don't know is this lambda, which is wavelength. And we have this division bar. Lambda is equal to 300 divided by F is equal to 300 divided by 50 is 6 meters. So colloquially, the 50 megahertz band is known as 6 meters. So the wavelength is typically how bands are known, rather than the frequency. So the approximate wavelength in meters is typically what we call bands. So the most popular one by far is the 2 meter band. Well, if we look at that frequency chart, we will see that 2 meters is actually 144 to 148 megahertz. Well, if we do our 300 F and lambda again, well, let's say that we're going to pick something in the middle, which is 146 megahertz. We're going to plug that in right there. Don't know that. We have the division bar. 300 divided by 146 is 2.05 meters. That is the approximate wavelength. This is known as the 2 meter band. Okay. So now we have some idea of how this stuff actually works, what radio waves are, what a wave is, what a frequency is, what a wavelength is. Now that we know what all those things are, we can actually start to use them and use them for practical purposes. So let me just see what page that we would be on. I believe it's on page, let's see, tune circuits, radio wave characteristics. Okay. So we are actually on page, believe it or not, looks like 39 of the PDF document. I don't have the actual page numbers on there, but it's called radio wave characteristics. Okay, so very quickly, now we should be able to just blow through this because we've already basically covered it. Okay, frequency, wavelength, and the electromagnetic spectrum. Everybody, feel free to just blurt in. What are the two components of a radio wave? Considering it's
Electric and
electromagnetic.
magnetic fields.
Electric and magnetic fields, right. What do you know about electric and magnetic fields? They always have to be
90 degrees.
90 degrees or perpendicular or at right angles to each other. How fast do radio waves travel through free space?
Speed of light.
Speed of light. And what's the approximate velocity of a radio wave in free space in meters per second?
3 times 10 to the 8.
Yep, or 300 million. Either way you want to say it, it's the same thing. So 300 million meters per second. So if you ever stop and think about that, it's about 186,000 miles per second. So how long does it take sunlight to get here from the sun?
8 minutes.
About 8 minutes. That's right. So when we were watching the impactor, did everybody see the DART impact of the asteroid moon a couple of weeks ago? The live video.
Yes, it was awesome.
Yeah, it was. It was great video. Do you know that we were not actually watching live? How delayed was it?
Wasn't it several hours?
No, it was about 20 seconds. We were watching what actually happened 20 seconds in the past because it took about 20 seconds for the video to get here at that speed. So when we received it, we were looking 20 seconds into the past. Okay, let's see. What's the formula for converting frequency to wavelength and vice versa? Or more importantly, what is the relationship between frequency and wavelength? When wavelength gets longer, the frequency goes up or down?
Down.
Down. And when the frequency goes up,
Wavelength goes down.
wavelength gets shorter. Exactly. So you have that formula, 300 is equal to frequency times wavelength. If you can remember that,
Frequency in megahertz.
frequency in megahertz, or it could be in hertz, but in this particular case, it is megahertz. And what does mega mean, everybody?
Million.
Million.
Million. Mega means million. And our wavelength is in meters. Okay. Okay. Let's see. Next thing to cover. What frequency range is known as high frequency? Everybody remember it?
3 to 30.
3 to 30. How about very high frequency or VHF?
30 to 300.
30 to 300 and UHF?
300 to 3,000.
300 to 3,000. Very good. And what does RF stand for? The hint being that F is frequency.
Radio frequency.
RF is
I
radio
should mention
frequency.
Scott WH3IA is next to me.
Hi, Bill. Okay, let's see. Now that we have some idea of what frequencies are, now it's time to talk about what they actually do. But you know what? Before we do that, we're going to give everybody 15 seconds to introduce themselves so I can get a better idea of who everybody is. So I'm going to start everybody, I'm going to pick somebody, and then after your 15 seconds of introducing who you are, where you're from, how you ended up here, and what you want to get out of class, what you want to do, then pass it to the next person. You get to pick somebody and go to the next person. All right, I'm going to start with Vic. Take it, Vic.
Good morning. My name is Vic Dietz. I live in the suburbs of Chicago. Wanted to be a ham all my life. I took the technician test several years ago through some unfortunate events. Walked away from the hobby. So I'm trying to get reactivated here. Scott, since I saw you last, I have purchased a dual band radio. I think I sent you a note. And recently I got really bold and bought an ICOM 7300.
Excellent choice.
So now I have to go take the general exam so I can qualify to run that radio, which is a completely backwards approach, but I understand that happens a lot in the ham world. And my wife keeps looking at me and saying, well, if you fail the test, you can always sell the radio, which is a pretty sharp knife and a deep wound.
Yeah.
So I hereby publicly commit to take the test on the 24th of October at the local ham radio club, and I will report back to you. I've decided over the weekend that I do have enough time to practice and do practice tests every day and so forth. So
All right.
Scott encouraged me to take this class as a refresher. And he also said that the general and the technician overlap. So I would encourage those of you taking the tech test to go ahead and take the general, because the old hams called Elmers will invite you to take another test for free when you finish this one. So if they're as close as Scott says they are, go for the two. Thank you very much. Happy to be here.
Vic, pick somebody.
Next to me appears to be Pat Gallagher on my screen. So let's go to Pat.
I've got into radio because of my father. Heck, it was actually in Scott's Morse code class a couple months back.
Cool.
And I just been curious about it since I was at least 5 because of my father.
All right, Pat, pick somebody else.
Let's do the person next to me, Chris Holden.
Hi, Chris Holden. I am in just east of Portland, Oregon, in a small rural community called Corbett. I was a volunteer firefighter a while back, and that's what got me curious about radio. Since then, I suggested to my son that we get our tech license so we can chat. He's in Prineville, which is about 2.5 hours east of us. So he got his license right away, and that was a couple years ago, and has been pestering me ever since to get mine. So
Good on him. Good on him.
I have been curious about software defined radio. I've got the small little SDR dongle, and I've been playing around with decoding POCSAG and pager data and stuff. So it's been a lot of fun. So
all right, Chris, pass it on.
All right, Raul. Is that
Raul?
Raul?
Yes, can you hear me?
Yep.
All right, great. Yeah, hi, my name is Raul. I'm also here with my son, Lucas. He's also on this chat as well. And we're both taking, this prep course, and we also signed up to take the exam after this. This is something I just wanted to do for years, just never, really, got myself down to do it. My father's been in ham radio for well over 30 years. And just one day I saw his equipment again, and I'm like, you know what, let me try to do this again. So I did. I was watching YouTube videos, going to a lot of forums, and yeah, it just piqued my interest again. I picked up, I got a lot of his old equipment. He, unfortunately, he just doesn't do it anymore. I guess he just, lost interest or whatever the case may be. I never really asked him. And I've been just listening to people, talking on the waves, and, it just seems like something I really wanted to do. And spoke to my son about it. He said, yeah, let's do it. And I just thought it'd be great, a nice father-son thing that we could just do together. And
where are you?
Hopefully we both get our licenses, and we'll talk back and forth with each other on the on the radios.
And where are you?
Oh, we're in Union, New Jersey.
Okay, is your let's give it to Lucas if he's there.
Hi, my name is Lucas, and my dad, Raul, has gotten me into ham radio just because of his father, you know? So I've gone into ham radio with him because we used to go on ATV rides and it's just easier to talk to each other. So like we have our, what's that radio wave called? That's like, you have, remember the other one that we have?
The little
FRS, GMRS.
Yeah, his FRS.
Blue Dot.
Yeah, it's like
GMRS.
one that we have, and we just talk to each other with that one when we're on the ATV rides. It's easier to just talk with like that instead of like actual like phone, because we go in the woods and there's like no signal or anything. Just use that, make it easier.
Cool.
And it's just been a really cool hobby.
And how old are you?
I'm 15.
15. You know, there's a lot of scholarships too.
Oh, okay.
Were you aware of that?
No, I have not.
Ah, okay. Now hold on before we go any further. All right, I'm gonna pop this page up and see. This is one of those dirty little secrets. See this thing called the ARRL Foundation. This is my plug for the American Radio Relay League. Good organization. This is our National Association for Amateur Radio. It's basically HAM's interface between us and the FCC and the government. So they represent the interests of ham radio operators in the United States. There are member societies all over the world that are equivalent. The ARRL Foundation is a grant-making organization that also administers scholarships. This year alone, they have about $900,000 in scholarships to administer.
Oh wow!
And so when it comes time to college, if your grades are good and you've been and you've upgraded and you're active, you apply for scholarships. And so let's say that you apply for a typical scholarship and there are 100 scholarships, right? And you have to just be a good student, right? There are probably 10,000, 100,000 people qualify, who apply for scholarships, and there are 100 to give away, right? Well, how do the people who are giving those scholarships out qualify people? They vet every single one of them. They have to meet certain requirements, right? One of the requirements for an ARRL scholarship is that you have a ham license. Well, if you look at the ham population, it's about 1 in every 500 to 1,000 people in the United States. So you take that 100,000 people applying for 100 scholarships, and you automatically have reduced that number down to about 500, 300, 500, 200 people applying for 100 big scholarships. So basically, this is getting a ham license and being active and having good grades at the same time. It actually kind of pre-qualifies you for scholarships, and these are not small scholarships. So just for those of you who are getting ready to go to college or thinking about going to college or in college, this is a really good thing. Not to mention the fact that this will help you with your education as well.
Thank
All
you.
right,
I didn't know
Lucas, pick somebody.
I guess we'll go to Brandon.
Hello, everybody. My name is Brandon Bedner, and I reside in Oklahoma.
All right.
Can you hear me?
Yep.
Okay. And just interested in the field. Have some older, closer friends that have encouraged me to partake in this adventure, and happy to learn.
That's a good way to look at it. All right.
Yeah.
Brandon, pick someone.
I have here on my screen. How about Crystal Lynn?
All right, let's see if Crystal has audio.
Hey, sorry for the background noise if you guys can hear it.
Yep, you're good.
Oh, nice. My name is Crystal and I'm in Orlando, Florida. This is gonna sound really like silly, but I actually just picked this up like on a whim because I saw it being offered on Discord through my former university's like club page. And then I was thinking to myself, oh well, I'm interested in apocalypse movies, like zombie movies, and I noticed like the important characters are usually the ones that knows how to do like communication, and they're like, oh, you know, who's out there, blah blah blah. So I just picked this up on a complete whim for that type of fun skill, really. And I guess I'll go towards Edna. Pass it on to you.
Hey, I'm Edna Sizemore. I live in North Augusta, South Carolina. I think the reason I got interested in this was my sister and I used to have season passes to Dollywood, and we would use like the walkie-talkie two-way radios to keep up with one another in the park. And it was also fun just to cut it on when we would ride around Pigeon Forge and listen to people talking to other people. And it just kind of got my curiosity and something I was interested in doing.
Okay. Edna, pick someone.
I guess I will go with Haley.
Hi, I'm Haley May. I'm actually a freshman at the University of Oregon, and I'm from Eastern Oregon. So like there's nothing there, and service is not always something that we have. So honestly, that already will help me like in my personal life, but I also picked this up on a whim because I have a friend who's in the club for Ducks on the Air. And so through him, I heard about this. I actually yesterday was, I believe, when I started getting into this. And so here I am. But yeah.
Where are you from in Eastern Oregon?
Burns.
Burns. Yeah, it's pretty remote.
Yep.
Yeah.
Definitely.
But you know what? But you know what you have when you have that much space? You have room to put up big antennas.
Yep.
Yeah.
Yep.
All right, pick somebody, Haley.
Let's go tomorrow.
Sorry, I couldn't get my mouse up to unmute myself. My name's Tamara. I'm from Southern Idaho, and I work with the University of Oregon in the Oregon Hazards Lab, which means we install a lot of wildfire cameras and seismic equipment for earthquakes. So that's why I got into this class. Kind of helps me with my job. A lot of our data is telemetered over radio waves.
All right.
Yeah.
All right, Tamara, pick someone.
I'll pick someone else from the Oregon Hazards Lab, which is Mitch.
Hey y'all, my name is Mitch Hilbert, living in Eugene, Oregon, originally from Massachusetts. And yeah, I work at the Oregon Hazards Lab. I am moving into the telecommunications position, so working with all different spectrums to be able to send data over microwave and other frequencies to hopefully track these hazards and have some prediction models going forward.
Cool.
Think that there's another. I'll pass it over to Elias.
There he is.
Oh, my name is Elias Bianchi. I'm from Eugene, Oregon, actually, and I work for the Oregon Hazards Lab as well. So basically, my interest stemmed from that. I've thought it was cool that we were able to send like camera data over radio waves, and one of my bosses suggested this course because she took it as well. And yeah, so that's why I'm here. I will pass it over to Joe Lewis, if Joe hasn't already.
Yeah. Hi, everyone. My name's Joe. I'm a junior at the University of Maryland. Like Scott mentioned, the W3EAX is resurgent.
Go Terps!
Go Terps. Roll Terps. Yeah. So I'm here to get my license, and I'm going to be a new member of the club and help set back up again. So super excited to be here.
All right, Joe, pick someone.
Oh, sure. Greg.
Hello, everybody. My name is Greg Hudgens. I'm in Sacramento, California. A little bit more denser for population out here. Of all things, I have had some experience in the past. I have some friends that have some long range drones. We're talking a couple of 3-4 miles and travel one direction. And it is pretty amazing to see some video transmitted over that, not only through its goggles, but on a big screen. But I'm looking into getting the licensing so that I can do the same and for SIR or search and rescue, because the radio waves are very important to be able to go over distances. You can't always get that with the FRMs, just the little store-bought ones. You actually need something, even with somebody on top with a repeater, to get up and over to the other side.
You know, it's interesting too that there have been, like with the hurricane in Florida, the Hurricane WatchNet has been very, very, very active because, you know, the hurricane plowed through and took down all the cell towers, no matter how many, you know, no matter how many were there. And again, you know, ham radio has been reduced to one of the only things that was working, both local and long distance. You know, if you have a battery and a radio and a piece of wire you can throw up in a tree, you can get a signal out.
Yeah, it was, of all things, I was remembering back, I had made tennis ball launchers, but they were specifically designed to put antennas further up in a tree.
Yep.
And you could pump it up with a bicycle tire pump and fire away, and you get your antenna very far up in a tree.
Actually, I have several friends who that's their primary way of getting antennas up. Tennis ball cannon.
I know it's effective. I don't put antennas up, but the dogs love it.
Yeah. All right, pick somebody.
Let's see. Adam.
Hey, how are you guys doing today? My name's Adam from Savannah, Georgia. My friend here is who got me into ham radio. He's an extra. It really got me excited when I started learning about the satellite uplinks and downlinks and being able to talk to the International Space Station. Being down here on the Georgia coast, we also set up an antenna here at the fire station to listen to the hurricane net during this last hurricane. That was pretty interesting to be able to hear, you know, just how much ham radio or amateur radioists help in the community when a natural disaster happens, you know, which we see quite a bit down here on the coast. So
cool.
We'll go over to Creek.
Hey guys, my name is Creek Johnson. I'm originally from Texas, the western part and most of Houston. I'm currently stationed at Fort Campbell, Kentucky. So I'm a soldier. I actually work with communication for a job. So doing this class here will actually help me be better about what I do.
Cool.
And initially with my dad, who was into ham radio. I think someone else mentioned it too. They were in the fire station, and fire stations use a lot of ham radios. I got my dad interested in it. So he too's been bugging me about trying to get my license so I can talk to them.
All right, very good. You want to pick somebody?
Pat.
I think we already got Pat.
That is Seth Swan.
Oh,
Yeah,
Seth
no,
Swan.
my name is Seth Swan. I'm out of Eugene, Oregon, and I'm a volunteer medic for Lane County Search and Rescue. So that's kind of what got me into the radio, into things. We operate on VHF frequencies out in the field, and then we communicate with like law enforcement, fire, Coast Guard on UHF stations. Lane County, very, very large county here in Oregon, Western Oregon, from the coast, Pacific Ocean, all the way up to the Three Sisters and the Cascade Mountain Range. And I'm really, more focused, I guess, on the emergency response. In particular, we don't deal with hurricanes here in Oregon, but we do a lot of wildfires. And Scott, as you know, we had one pretty close to home here last few years, up in the McKenzie River in particular, where, landlines are down, cell towers are burnt up and down. and ham operator to the rescue. So hopefully this will give me some more skills in that regard, and take it to the search and rescue end of things.
Cool. All right, pick another one.
We'll go Brandon Bednar.
I believe I went earlier.
Oh, go ahead, Brandon, pick somebody.
Oh, I'm sorry.
Oh, okay. I'm not quite sure who's still in the lineup.
All right, how
Should
about
somebody
Abu?
help me out?
How about Abu?
Okay.
Hello, everyone. My name is Abu. I'm originally from Sudan. I used to be an amateur ham radio. Few years back, call sign Sugar Tango 2 Alpha Bravo. But when I moved here to the States to do my grad studies, I'm currently a grad student at the University of Maryland. I would like to revive that hobby again and get the US license here. Nice to see you all.
Same. All right.
I'll pick Teresa.
Yes, hello. Sorry, computer's glitching a little bit. Hi, my name is Teresa. I got started with this because I was strongly advised by my industry advisor for Portland State Aerospace Society to get my amateur license. I'm an electrical engineering major, so I'll be focusing on embedded systems and digital signal processing. But for the time being, I'll be focusing on cube satellites with my student teams group called ORSAT. And we just recently launched our first CubeSat into space. I did not work on that project, but I'll be working on future iterations. So it was just strongly recommended that I get my amateur radio license.
Very cool.
Sorry.
There's ORSAT.
Yes.
Notice notice the apartment building style of construction there, which I think is very cool. It's actually what a foldable, stackable, and then you can ribbon it up too.
Yeah, no, they've been doing all sorts of things. Like I just joined with ORSAT this year and I like got into their Google Drive and it was like, holy cow, you have so much heritage to work through. It's amazing.
You know what's really cool? That whole thing is 4 by 4 by 4 inches. It's a one satellite. It's so small, so much in there.
Yeah, it's madness. It's so exciting. I'm excited to learn about it this year.
All right, pick somebody.
Yeah.
We're running out of people, which is good. That means we're getting everybody.
I nominate Rose.
Rose Jardine. And I don't know if Rose is here. How about Magnus?
Hi there. My name is Magnus. I'm a mechanical engineering student at Oregon State University in Corvallis.
We won't hold that against you.
Okay. Don't really have a particular reason for getting the license. Just thought it might be some fun. So, yeah.
Cool.
And I'll pass it on to Adam.
I think we got Adam already.
I'm about to say I've already gone, but I'm more than welcome to go again.
Yeah. How about Stacy? Did we get Stacy yet? Okay, let's see. How about Hala? So someone's listed as Hala. Okay. How about Chris? You're muted, Chris. There we go.
Let me unmute. So my background is in being a first responder, and I learned about this class through the Washington Off-Road Recovery Network. So it's a volunteer group of a bunch of four-wheel drive fanatics that we go out and rescue folks that get themselves into trouble in off-road situations. So I do have my GMRS license, but I want to be able to expand that in being able to set up crossband repeaters and I don't know if it would be called a remote station to be able to set something up in an emergency situation so that we can relay communications to be able to reach further distances when we're out on a recovery, because it's oftentimes areas are pretty remote. And so cell phone connections don't work, and satellite phones are really expensive. So this is an option available to us to be able to do that.
Cool. All right. Is there anybody who can go who didn't go yet?
Yeah, I think I'm probably the last one.
There we
Travis.
go. Go ahead, Travis.
I'm out in Hawaii. Grew up in Arizona. Same reasons as Seth and Chris. Mountain rescue technician for a few years out in Arizona in Maricopa County, and a lot of the senior techs out there were all amateur radio. Would take mobile base stations, set them up as repeaters so we could operate in the field. So looking to get into that same kind of line of work, maybe out here in Hawaii for volunteer work, or when I get back to Arizona.
Very cool. Which island are you on?
Oahu.
Oahu. Okay. Haven't been to Oahu yet. All right. Well, any other questions? This is actually really good because you can see there's as many different reasons to get into this as there are people, which is, why I like doing this. It takes 20 minutes, half an hour, but I think it's good for everybody to kind of get to know everybody. Did we get Erica and Jeremy Roberts? I can't see. Hala used to be ST2HO. So Abu, and any relation there?
Yes, Hala is my wife.
Very good. All right. And by the way, just so everybody knows, I have never worked Sudan. I've confirmed contact with 260 DXCC entities around the world, which will make sense by tomorrow. There are 340 of them. Sudan is one of them. I have never contacted Sudan in my entire life. So if your license is still active and you go back, I'd love to try.
Yeah, definitely. At the time when we were operating, we were about 14 people operating from Sudan.
Yeah. It's difficult. Okay.
Yeah,
All right.
I have a quick
Yes,
question.
go ahead.
I was just wondering how soon the recording would be sent after this. I just wanted to watch the first hour again later in my free time.
Oh, I'm going to post this tonight up on YouTube.
Oh, okay, cool, great.
Yeah, you'll be able to get it. I'll send the link out right after class, unless I have to run somewhere, but it'll be within a couple hours. And then you can watch me at double speed. All right. So now that we've discussed sort of what HF and VHF and UHF are, and the fact that everybody seems to be here for a different reason, which is great. There's a little bit of overlap here and there. One of the interesting groups that I get very often are the people who wanted to get a license when they were kids and now they're retired. And now they have the time to finally do it. And I know I heard at least one of those. So I always wanted to do this and now I have time. All right, propagation modes. So now we're talking about waves and what they do. So in order to understand what we're talking about, I'm going to draw this big blue marble, as it used to be called. This is where we live. And then I'm going to draw layers above it, which is our atmosphere. Okay, so now I'm also going to draw this big yellow ball in the sky. Okay, so we live down here on the ground, the big blue marble, and then we have all these layers. Notice our atmosphere. We have the bottom layer, which is the troposphere, which is up to about 30,000 feet. Then we have something called the stratosphere, which is considerably above that. And then above that, we have something called the ionosphere. And there's a little overlap between the stratosphere and the ionosphere and the mesosphere and stuff like that. But anyway, the ionosphere is actually broken up into multiple layers. The first layer is called the D layer, then there's the E layer, and then there's the F1 and the F2 layers. The D layer goes from about 30 to 50 miles up. So we'll go with kilometers. The E layer goes to, let's say, 100 kilometers. And then, let's use miles. That's probably more accurate for this. And then that goes up to about 250 miles. And then there's the F2 layer above that. So we have the D, the E, the F1, and the F2. I assume that they were called DE, F1, F2 because it turned out that F, they named it originally F, and it turned out that it split into two, kind of. And my guess is that D started at D because people were wondering whether or not there was anything lower. So they left space for A, B, and C, but they've never been found. So these are layers of the atmosphere where a certain mode of operation takes place. And to understand that, what we have to do is look at this big yellow ball in the sky. All right, so what's this big yellow ball in the sky called, everybody? Oh, come on. What's the big yellow ball in the sky? That's the sun. Okay. And and this actually comes out of what we talked about before. All right. So the sun is actually a black body radiator. It has a temperature, which means that it has a peak at a peak of light at a certain frequency. Well, if we were to draw this frequency spectrum, the sunlight coming out of the sun looks like this. And it has a peak at yellow, which is why it looks kind of yellow. Right. But that does not mean that the sun doesn't put out radio, which it does. And it doesn't mean that the sun doesn't put out infrared. And it doesn't mean that the sun doesn't put out ultraviolet, because clearly you can go out and get a sunburn. And it also doesn't mean that the sun doesn't put out X-rays, which the sun does. The sun puts out X-rays. And I don't know why my pen is acting weird. There we go, X-rays. Okay, so all of those things come out of the sun all the time. Now, the one that we see the most of is yellow because that's the predominant wavelength. But there's all these other ones. We can actually take radio measurements out of the sun. And in fact, we do. We measure solar energy coming out at 2,800 megahertz. That's a really important frequency. The reason that we look at that frequency is because it generally relates to the amount of ionizing radiation coming out of the sun. We actually call this our solar flux, and we use this to measure the amount of ionizing radiation coming out. Not because it does it, but because it's related. So that's known as the 2,800 megahertz solar flux. Now, let me get rid of that. So the next thing that we do with the sun is that we look at the infrared coming out of the sun. And why is the infrared important? What does infrared energy do for us? It warms the earth, right? The infrared energy passes through some of the atmosphere and it gets down to the surface and it warms us up, which is really nice. Okay, so now there's this other thing that comes out of the sun, which is called UV, or ultraviolet. So ultraviolet has there's actually near ultraviolet and far ultraviolet. They range in frequencies and hardness of rays. The higher the frequency, the higher the energy. Well, as it turns out, that ultraviolet energy, if that were to get down to the Earth's surface, along with the X-rays that are coming out of the sun, what they would do is, if they made it down to the surface, they would sterilize the planet and nothing would be living here. So fortunately, we have this filter. This filter is known as our atmosphere. Our atmosphere contains largely two different things. It has diatomic nitrogen and diatomic oxygen. So that would be O2 and that would be N2. And these molecules are floating around. They constitute about 99% of our atmosphere. and they are floating around in different densities. As you go up in altitude, your air gets thinner and thinner, which is why we can only live down here. And when you fly in a plane, they have to pressurize the plane. But as you get up toward the upper reaches, it gets very, very thin. So what it turns out is that the energy that is incident on the Earth from the sun happens to come down in the form of photons. Photons are particles of light, if you want to think of them that way. They're basically little packets of energy. As those packets get down to the atmosphere, once in a while, a packet of energy will have enough energy built into it that when it happens to strike, let's say, an oxygen atom right here, which has a neutral charge, what will happen is that oxygen atom will absorb the energy from the photon. And what you end up with is an ion, which is a positively charged oxygen atom, and an electron, which is a tiny little negative particle floating around up in the atmosphere. Well, okay, so let's say that somewhere up here you have an oxygen atom and another electron, and then maybe you got a nitrogen atom that got hit and another electron floating around and another nitrogen and an electron floating around. Well, because the sun continually bombards the Earth with ultraviolet and X-rays, which are known as ionizing radiation, because they take these atoms and they turn them into ions. They basically rip electrons away from them. What ends up happening is that so long as the sun is shining, you have a continuous generation and then recombination occurring, where once in a while, these things that are oppositely charged will meet. And when they meet, they basically will join back up, and you will just end up with a plain old oxygen molecule floating around in space. So because we're dealing with electromagnetic waves, things that are neutral are not particularly interesting to us. So this oxygen molecule, not particularly interesting. We're just going to erase it. But what we do have up here now is we have this continuous stream of positively and negatively charged particles floating around up in the atmosphere. Well, what happens when the sun goes down? Everybody, what do you think happens when the sun goes down?
That generation stops because there's no light coming from the sun.
That's right. The generation of those ions stops. And these things have time, not all of them, but a lot of them will recombine and your density goes down. You'll still have a few that never made it to find each other, but by and large, your density goes down, which essentially means that from daytime to nighttime, what you end up with is a difference in the amount of ionizing radiation that is ionizing the atmosphere. So at night, it might be very rare to find any of these ions floating around. During the day, you might have a whole mess of them at different levels. And in fact, what ends up happening is that these different levels of ionization that occur result in different behavior, which is really cool. So let's take a look at the D layer. What happens is now you have a radio wave, which is energy coming up from the surface. And essentially, these charged particles up here will actually, just like if you think about, if you've ever seen a spoon in a glass of water, it looks like the spoon is bent. And that's because of difference of index of refraction of the materials. This will actually cause the wavefront to bend and some of it might aim back down to Earth. Well, that can happen, but what usually happens up here in the D layer is that unfortunately does not happen. You have really two choices. One, the frequency is high enough that you get penetration, or the energy is such that that causes all these electrons to absorb the radio frequency energy and then re-emit it because the atmosphere at that level is actually pretty dense, and then the signal will basically disappear into that area of space. So we have some frequencies. These are higher frequencies that pass through, and lower frequencies that just sort of disappear. So now what we're going to do is we're going to look at our frequency spectrum chart. And I'm going to share this. And right here. Okay, so notice that we have HF, VHF, and UHF. So the cutoff point for that layer is right around, let's say, 10 megahertz for the D layer. So what range does 10 megahertz fall in, everybody? I'll zoom in.
HF.
HF, okay. So what we're going to now do is, if I can find it, we're going to share, if I still have it. I might have closed it. Okay, NTIA, frequency allocation chart. And here we go. Okay, there we go. We're going to share this. Okay. Everybody see that frequency allocation chart?
Yep.
Okay. So now we're looking at megahertz. Notice 3 megahertz right here. And we're looking all the way up to about 10 megahertz, which is right here. Basically, anything below that frequency gets absorbed during the daytime. Isn't that trippy? Never makes it up, and it never makes it up to the upper layers. And this is most easily evidenced by the fact that if we look way over here, do you guys see this thing that says broadcasting AM radio? AM radio goes from 535 to 1700 kilohertz. So if we were to look at that on our chart, we would see AM radio goes from 535 to 1705 kilohertz, or 0.5 to 1.7 megahertz. Well, we said that that layer will basically absorb anything less than or equal to 10 megahertz. So here's the Earth, here's the D layer, here's the E layer, here's the F1 and F2. So basically our signal goes up, hits the D layer at, let's say, 1 megahertz. And what happens to it when it gets there during the day?
Absorbed.
It gets absorbed. Okay. When do we notice this? Has anyone ever listened to an AM radio during the day? What stations do you hear?
The local stations.
All the
that are
local
here at
stations.
night, or
All the local
daytime.
stations. And that's it. Only the local stations. But when the sun goes down, the D layer absorption disappears really quickly, because there's a lot of ions. It's a very dense layer of atmosphere. So that layer disappears really fast. So all of those signals at 1 megahertz can actually penetrate and go up into those layers. Well, it turns out that these layers are really good at bouncing signals back to Earth. So what happens at night to those AM radio signals?
if you keep your radio soft enough that your mom can't hear it, you can lay in your bedroom in Iowa and listen to Chicago radio overnight, all the way to Chicago. That's 200 miles away.
Or growing up in Washington, D.C., you can listen to WLW Cincinnati, or you can listen to baseball games from Chicago, which I did.
WGN, no doubt.
WGN on the air. So
World's
those
greatest
signals,
network.
those signals that disappear during the day because they get absorbed, pass on through up into the upper levels of the atmosphere at night, which basically means that below 10 megahertz, you have a diurnal pattern from daytime to nighttime where your signals behave completely differently. Now, let's take a look at, let's say, FM. Well, FM radio, we're going to draw the Earth again. GE F1, F2. Okay, FM radio, if you look at the chart, goes from 88 to 108 megahertz. Okay, now this is very different from 0.5 to 1.7 megahertz. And it turns out that those frequencies, either day or night, for the most part, just shoot on through everything. It doesn't even matter if it's day or night. So why would this be particularly useful? What would we use these frequencies for? In addition to listening to FM radio.
Communicating with spacecraft?
Communicating with spacecraft, because the signals pass through the atmosphere like it's not even there for the most part. So basically typically anything VHF and above, we would use to communicate with things in space because it looks like the atmosphere doesn't even exist. Now, there are some special modes that do bounce VHF, UHF signals around, and we'll get to those. But now we're going to look at the stuff that's in between. We already looked at the absorbing signals, and now we're going to look at the HF signals that are between, let's say, 10 to 30 megahertz. And what we will find is, depending on the level of ionization that exists up here, higher ionization works better for high frequencies. And lower ionization works better for low frequencies. When does high ionization occur? What time of day?
Daytime.
Right after sunset.
Right. Or basically peaks, right early afternoon to sundown. So basically this is daylight hours. When does your low ionization level happen? When do you see low ionization densities up there?
When there's no sun.
That's right. When there's no sun. Basically, that's nighttime. What that means is that you might have 30 megahertz during the day working really well. And at night, you have 3.5 megahertz working really well. So what this means is you basically can have very different propagation. Propagation is how waves move from place to place. Radio waves move from place to place. How they propagate or travel through the atmosphere or through through empty space. They propagate differently from day to night. So there's a dividing line. And what we're going to do is, one of those things that I sent you guys is something called the US band plan update. And I'm going to share this with you now. Okay. So can everybody see this?
Yes, sir.
Okay. So notice we have frequencies. This is in megahertz, 1.8, 3, 7, 10, 20, 18, 21. These are all bands that are assigned to ham radio. 50 megahertz, 144, 222, 420, all the way up to 1240, and actually well beyond this as well. We have all the way up to light, basically. Or all the way up to infrared. We have lots of different bands in there. And we can actually do light as well. We can transmit over light. So what you will find is that right about 14 megahertz, which is the 20-meter band, that's kind of like the differentiator between daytime and nighttime bands. That anything higher frequency, so 28, 24, 21, 18, all the way down to 14, those signals are actually able to be bounced during the daytime. So whenever their sun is out overhead. Anything lower than that usually gets absorbed and never makes it out. At night, there's not enough ionization to carry those higher frequencies, and those lower frequencies can pass through the D layer, and they're then carried at night over long distances. So why would this be interesting to us? Because one of the things that we do is we sometimes, on the frequencies that we're allocated, like to talk over very long distances. And one of the things that we one of the ways we can do this is we can do things like this. We can take a map of the world and notice what we have on this map. We have the day-night terminator, as it's called, which shows where it's daytime and where it's nighttime. And we're going to, let's reload that. And ooh, look at that, pink. 10 meters is open to the East Coast, and a few different things are open to Europe. Now let's look at a different location. Let's hope this works. Okay, so here is from Europe. Notice we have different colors going to different parts of the world. Notice also that you have this line, which is between light and dark. This is known as the gray line because it's between light and dark, white and black. And what you end up with is very interesting propagation characteristics that can go all around the entire planet on those frequencies, along that line. So let's see. Let's look at another one, QF22. That should be, oh no, it's not. Let's go with this one. Nothing there, huh? Okay, let's go with PM95. I know that's going to be busy. Okay, so from that part of Japan into Europe is alive right now. Okay, so basically different frequencies behave in different ways. So what we're going to go back to is propagation modes. We're on page 42 of the book. So we have VHF and UHF. VHF and UHF are above that fray where we start dealing with the layers of the atmosphere. Again, DE, F1, F2. VHF and UHF will typically shoot right on through, which is why we use them to talk to satellites. Now, there are a couple of interesting things that happen. For those of you who've taken physics, if we aim a wave at a slit, what happens is that we end up with something that looks like this. It ends up that the edges of the slit cause diffraction and retransmission of new wave fronts. And we can actually take a signal that's going this way and it will actually bend downward. So this actually happens on the surface of the Earth. Depending on the frequency you're on, the longer the wavelength, the less curved the Earth looks. The curvature of the Earth has less effect. So because of that, if you're doing VHF and UHF, you're doing this, let's say, over open ocean. This is why we do VHF for marine frequencies. It travels further than the line of sight. It'll actually increase it by 10, 15, 20%. So that's known as the radio horizon. Let's see, the atmosphere refracts radio waves slightly at those frequencies, and it also curves around the surface. UHF signals typically don't get bent very far, which is why they're not as useful for over the horizon. Okay, so now another thing we're going to have to cover is the fact that we have this thing called a wavelength. Okay, so we're actually looking at, let's say, a wavelength of 2 meters. If I were to draw a wave, that would be 2 meters long. What's 2 meters in feet, everyone? Approximately.
6.
About 6 feet. Okay, so about the span of my arms as I stretch them out. That's about the length of one wave on the let's say 146 megahertz. So let us now take a single transmitting point and say that we have a signal that goes from here to here. And it doesn't really matter what that distance covered is. Don't really care. But let's say that there's another signal that goes this way, and then it hits something and ends up bouncing there. Solid object. What do we know about triangles? If we take the length of these two legs, it's always going to be longer than the first straight line, right? That's just a definition of a triangle. So if that is the case, we know that if this wave had to travel distance L, then this one had to travel L plus something to get to that same point. Well, what if that wave had to travel L plus 2 meters? And we start drawing the waves because they're coming off at the same time. And this one gets there right there. This one has one extra wavelength to cover, and it gets there at the same time. It's just delayed by one wave. Are they going to add or subtract when they get there? What do you think?
They'll add.
They will add. That's right. This is constructive interference.
They're both going to get there at the same time, even though the one has to.
Well, no, but what'll happen is that they're not going to get there at the same time. This one is going to be delayed by one wave, but they're going to get there at the same point in their wave, I guess I should say.
Oh, okay. Thank you.
So basically, if I were to draw it, the first one gets there and it looks like this, and the second one gets there and it's arriving in phase. The amplitude might not be the same, but it might be, in which case they would add together. That would be known as constructive interference. But now, let's say that this, for whatever reason, is only a distance of 1 extra meter. And now, what was the wavelength that we were talking about, everybody? 2 meters. So here's one. The other one, as we erase it, now had to go like this. It had to go like this. And instead of getting there, it got there and it was going like that at the end. So now we have that added to this. What are those things added together?
0.
That would be 0. Well, so basically what this means is this is called destructive interference. They are now arriving out of phase with each other and canceling each other out. Now, they might not be completely the same amplitude, but they could be. At the very least, they're going to start to try to cancel each other out. So this is known as multipath when you have signals coming on multiple different paths of different lengths. So because of this, because we are typically dealing with handheld radios, which are handheld, one thing that we can do is we can physically move ourselves over here, let's say, so that our triangle now looks like this. And now we can actually make it so that our path length is now 2 meters longer just by moving a little bit. So by moving a little bit, what we've done is we've gone from an area where we couldn't hear anything to an area where we could hear something. If you have been on a repeater or talked to somebody, you may have noticed that as you're walking or moving around a room, there are loud spots and dead spots. This is exactly why there are loud spots and dead spots when you're listening to the radio, because the wavelength is only 2 meters long. Some cases it's only 70 centimeters long, right? 70 centimeters is about this big. Oh, my video got turned off. There we go. 70 centimeters. Can everybody see me okay? I can't see me. There I am.
Yes.
70 centimeters is about this big, which means that half of that is only this big. It's about 14 inches. So by moving 28 inches, you could go from an area that sounds great to an area that's dead to an area that sounds great, just by taking your radio and moving it around the room. Some of you who have been on FRS or GMRS may have noticed this already. That's what you're hearing. You're basically hearing a real world application of physics and mathematics. And that's why signal strengths can change a lot when you're moving around. Now, if
Hey,
you're in a
Scott,
moving car.
quick question, Scott.
Yeah, sure.
Is the destructive wavelength, is that how like noise canceling headphones work?
That's exactly how noise canceling headphones work. That is actually taken into acoustics. That is how that constructive and destructive interference is exactly how concert halls are wired for sound, so that everybody can hear something, or that you avoid dead spots. That's exactly right.
That's cool. Thank you.
Mm-hmm. And the way a noise canceling headphone works is that it listens to the ambient noise outside and generates an opposite phase signal and adds them together. And the sum of a plus and a minus is 0. So that's why you don't get the ambient noise coming in. Okay, so something called picket fencing. Picket fencing occurs when you are in a moving vehicle on VHF or UHF, and because you are moving from areas of constructive to destructive to constructive to destructive interference very quickly, it actually sounds like this as you're driving along and listening, like you're actually trying to talk to somebody through a picket fence. That's known as picket fencing. If you are doing data transmissions, for instance, for those of you who are going to be working with the hazards lab and doing telemetry, multipath interference will typically, unless you have constructive interference, it will typically lead to increased data rates, or sorry, to decreased data rates, greater error rates. So it's very important to get a good solid signal when you're transmitting data. Now, you could also use this to your benefit. You can take signals and bounce them off of something. I know that one of our guys in our radio club, for someone who's doing search and rescue, you probably know Nathan, AI7NC. He was up in the Cascades up near Mount Hood, and he was actually getting into our repeater and having conversations with us by bouncing signals off of Mount Hood. So he was aiming at Mount Hood, and the signals were bouncing off and going south to Eugene. Let's see, knife edge diffraction. This is again an application of physics and wave functions, where you basically have a tall, sharp object, sort of like a mountain peak, and you aim a signal, which generates wave fronts. When it hits the mountain peak, that acts as a single slit effectively, and you have signals that diffract up and signals that diffract down, and some of them might actually get down to the ground. And again, that's known as knife edge diffraction because it requires a sharp object to cause diffraction. The effect of vegetation on UHF and microwave signals. Now, what did we say about microwaves? So we're going to draw that 2.4 gigahertz. Well, it turns out this is an amateur radio band. It also turns out that this is known as Wi-Fi. We actually share frequency bands between Wi-Fi and ham radio. Now, Wi-Fi is typically allowed to run, I think, about 500 milliwatts. Amateur radio operators are allowed to run 1,500 watts. Okay, who's going to win? We can actually run some really high power, much more so than the Wi-Fi routers can. But we do suffer the same problem. If anyone has ever had satellite radio, for instance, when they were in the car and it was raining, or satellite TV and it was raining and your signal kind of went away, that is because the signals that are being sent up or down are passing through raindrops. And raindrops are made of water, and water is H2O, and H2O, as we said, is resonant at 2.4 gigahertz, which means that at UHF and microwave frequencies, water tends to get in the way of radio waves that are in the UHF and microwaves. So if you have rainy conditions, that will get in the way. Now, similarly, if you look at leaves, a large component in leaves is water, at least until they fall off the trees. So if you aim a radio wave at a leaf, a lot of the energy will get absorbed. Some of it will actually get reflected as well because it's a flat surface, but some of it will get absorbed and some of it will pass through, although it's attenuated. So you basically end up with something called absorption in the leaf because it has full of water. Okay, so next, what we're going to do is something called polarization. Okay, so I'm going to draw our electric field. And now I'm going to draw again our magnetic field.
Question. How does the deconstruction and like the construction wavelengths like apply to the water example? Like, would that be deconstructive?
With what? Well, I mean, it's literally absorption. It's basically the energy of the radio, the energy in the radio wave just causes, it's not constructive or destructive. It's just literally causing the water molecules to vibrate and just absorbing the energy.
Oh, okay.
It's basically doing a microwave oven. The water's acting like the water in your microwave. Okay, so here's our electric field. Electric field is in black. Magnetic field is in red. Okay, so that's our E field. That's our H field. Electric is E. Don't ask me why magnetic is H. It's always been called that. So our E field goes up and down in this case. Because it's vibrating in the up and down direction, the polarization of a wave is defined by the direction of movement of the electric field. So this would be known as a vertically polarized wave. If I were to rotate this, unfortunately, I can't rotate my iPad and have anything change. But what I can do is I can do this. And now it's parallel to the ground. This is my E field, E and H, so E, H. So my magnetic field would now be down and up and down and up and down and up and down and up like that. So my electric field is coming toward me like that. It's now parallel to the ground. It's now horizontal because it's horizontal, what we call horizontal. This would be known as horizontal polarization. Okay, so does anybody have any practical use for polarization in their life? Let's hear it, everybody.
Sunglasses.
Sunglasses. Any other ones?
Monitors.
Monitors. Any other ones?
To some extent, your car windshield.
Car windshield. How about an LCD display? That's actually how an LCD display works. Everybody's got LCDs. Liquid crystal display. That actually causes an additional layer of polarizing light to change material to change polarization. What happens is that we have, let's say, a filter. This filter, up and down would be vertical, vertical and horizontal. Vertical hold, horizontal hold. So let's say we have a material that allows energy in the vertical direction to pass through. Electric field in the vertical direction. So this would be a vertically polarized material. And we take it, and here's our incident light, and it's going up and down. Our electric field is going up and down. That light will pass through. But now let us take an additional form of light that is going like this. Our E field is going horizontally. What happens when the horizontal light passes, when it hits the vertically polarizing filter? What do you think, everybody? It gets blocked, exactly.
It gets blocked.
Right. So the benefit of this is, let's say we're driving a car, and here's the hood of our car as we're looking out over the hood of the car, and we have sunlight. And the sunlight is coming down and hitting the car, and it's reflecting off the hood, and it's basically aiming at you, right? Causing you a ton of glare. So what happens is when it hits this surface, it becomes polarized. In particular, the polarization of the polarized light, because the sun has horizontal polarization and vertical and all different combinations. This is a random polarization. It basically allows the horizontally polarized light to reflect off the surface of the hood. Well, if you wear polarizing sunglasses that only allow vertically polarized light to get through, what happens to that other light? The glare off the hood of the car almost completely goes away. And that's why we do polarizing sunglasses. Okay, antennas work very much the same way. So as we have, let's say, a piece of wire, as electrons move, we haven't really covered electrons that much yet, but as electrons move back and forth, they basically make an electric field that goes back and forth. So a horizontal wire will have an electric field that is in the horizontal direction. If I were to take a vertical wire, it would have an electric field that goes back and forth in the vertical direction. So let us say that I have an antenna, piece of wire, because an antenna is really just a piece of wire that is horizontal and makes an electric field that goes horizontal, back and forth and back and forth. And then it comes across this antenna, which is vertically polarized and is looking for signals going in the vertical direction, vertical polarization. What is going to happen when this signal makes it to that antenna?
very low quality.
Yeah. Essentially, if I have a signal that's being transmitted by somebody with an antenna that's in the vertical orientation and mine is in the horizontal orientation, very, very little signal will actually get in. And that is why polarization is very important. Okay, the orientation of the electric field defines polarization. We're on page 45, by the way. What happens when antennas at opposite ends of a VHF or UHF line of sight link are not using the same polarization? Received signal strength is reduced by a lot. Why do we typically use vertical polarization if we want to talk to a lot of people? So let's look at a mountain from above. Right? So we're looking down on a mountaintop. On this mountaintop, I have an antenna that is just a vertical and I'm looking at the end of it. Is there anything different that differentiates any one direction from any other direction? Which means that I have an equal signal strength that way, that way, that way, that way, that way. Well, if I'm trying to talk to everyone, that is exactly what I want, isn't it? I want to be talking to everybody, so my antenna will have an equal pattern in all directions. Now, what if I had an antenna up there that looked like this? Which direction would that actually put out? That would put it out an electric field in this direction. And actually, it turns out that my peak of who I'm going to talk to would be out in this direction and this direction. Well, what about all the people out here? If I wanted to talk to everybody, the people who are out here and out here in those circles would basically get ignored. That is why if I'm putting up an antenna that is trying to talk to everyone, my goal is that I'm actually going to put something up that is omnidirectional, as it's called. And the most omnidirectional antenna is a vertical piece of wire. Viewed from the side, a vertical piece of wire just looks like this. We're going to put it on a mountaintop. It's just a straight up and down piece of wire. Basically, this radiates in all directions equally. All right, so if we want to talk over, for instance, CW, this is a good opportunity to talk. CW is continuous wave, also known as Morse code, or SSB, which is single sideband. We use horizontal polarization because we're typically not trying to talk to everybody. We're trying to talk to just one area of the horizon. If we're talking on FM frequency modulation, that's typically what we do with this. Our goal is usually to talk to everyone everywhere, so we would typically use a vertical polarization. Okay, now, one thing we're going to do really quick is we're going to draw the picture of the Earth again, and we're going to look at some weird things that can happen. So here's the Earth, here's the D layer, the E layer, and the F1 and the F2. So the D layer, we're basically going to ignore because it doesn't really do a whole lot positive for us. So we're just going to kind of do that. Now, the E layer typically is very boring. This actually works usually on only up to about 10 megahertz or so. That's usually the only range of frequencies that the E layer will work on. However, there are some times that the E layer will form really, really dense layers of ionization where your signals up to, let's say, 200 megahertz will get up to this layer and bounce down. And these are very, very dense patches of ionization, and this is known as sporadic E. The reason that it's called sporadic E is because it's really hard to predict. And literally, this happens in such a way that it is virtually impossible to predict most times. We do know that it happens a lot in the summertime, in particular, like over areas where there are thunderstorms. That's about it. That's all we can really say. Sometimes we just get a really good sporadic E layer that forms, and it might last for an hour and then completely disappear and just go away. So sporadic E is actually really good for the 10-meter band and the 6-meter band and the 2-meter band. And if we look at that and we look at those frequencies, we're going to pull up our spectrum chart again. Well, here's the 10-meter band. That is at 28 megahertz. That is at the very upper end of the high frequency band. And 6 meters and 2 meters are well into the VHF band, 50 megahertz and 144 megahertz, which are typically line of sight. So what this means is that occasionally sporadic E, that E layer, will do something weird to us and allow us to use VHF and cover a range of, let's say, 1,000 miles, whereas normally it's just point-to-point line of sight. So very strange propagation mode, but a lot of fun when it happens. There's another thing called auroral backscatter. So if you look at all the things around the Earth so here's the Earth, and we have all the layers of the atmosphere, et cetera, et cetera. One thing that happens is that we have these solar particles coming out of the sun, and we have up at the poles, north and south, we will occasionally get these particles flowing down into the atmosphere and causing red and green shimmering lights. And what are those called, everyone?
Northern Lights.
Those are the northern lights. Oh, they could also be the southern lights. This is the aurora borealis. Down here in the South Pole is the aurora australis. Except that, the population down at the South Pole is considerably smaller. But essentially what we've got is high levels of ionization, which means lots of electrons and lots of ions forming. And anytime you have a lot of electrons floating around up there, what you can do is aim a radio wave into the aurora, and sometimes it'll bend, which doesn't really do us a whole lot of good, but sometimes it will scatter back at you. So some of the incident energy will actually bounce back, and that's known as auroral backscatter. So typically what happens, because it's very random and shimmering, if you think about what the aurora looks like, if you were to take a listen to that, it would kind of sound ghostly and weird, and that's actually what it sounds like. So you get wide variation on signal strength, and it sounds really distorted. But it does work. People do work aurora. Now, the other thing that can happen is that once in a while, we'll get a bunch of little rocks that fly through the atmosphere and cause meteor trails, right? We'll get a meteor shower. And what happens in a meteor shower is that you have a lot of energy suddenly dumped into the atmosphere, and it essentially causes a plasma to form as the meteor burns up. And what is that? That is a bunch of electrons. And what can we do when there's a bunch of electrons? Send a radio wave up at it, and it'll either get bent down or bounce back down. And that's known as meteor scatter. We actually do that too. Meteor scatter typically works best on 6 meters and 2 meters. 6 meters is usually the favorite of most people for meteor scatter. The other thing that can happen is we can get this thing called tropospheric ducting. Now, we have any drivers out there? People who've driven a car? Most people have driven a car. All right. So if you ever noticed on a sunny, hot day that you will see, as you're looking out over the road, you will see the roadway. And so here's the roadway. And over the roadway, you will see what looks like blue sky, kind of in shimmering waves. Okay. Any idea what that is or why?
The
Okay.
mirage.
Hmm? What was
Is that the mirage?
Well, what's actually happening here is that, like, what causes a mirage? What happens is you have heat that is coming off the surface of the road. And because it's in direct sun, it heats up. So what you end up with is a warm surface, and then a cool surface, potentially, and then a warm surface again. And you basically end up with this little temperature inversion. And it turns out that when you have a boundary layer, you have different indices of refraction. And what that does is the same as if you look at a glass of water where you have water and air, and a spoon is sticking into it, it will look like this. Actually, it's backwards if I'm not mistaken. I believe it actually looks like this. It will look like the spoon is bent. The reason that the spoon looks bent is because electromagnetic radiation travels at different speeds through different media. What happens here is that you basically get light coming off the sun or off the blue sky, and it goes like this. And depending on what's happening in here, it can actually get trapped and bounced around and eventually come out. And what you see is a reflection or a refraction of the sky, because you end up with that boundary layer. We can actually do this with radio waves too. And this is known as tropospheric ducting. And so here's the troposphere. This is where we live. And we have up here a temperature inversion. Typically, as you go up, your temperature gets colder. But there might be a warmer spot and then colder again. And as that happens, you have these different boundary layers right here where you have different indices of refraction. And because radio is just another color of light, a radio wave that you get up into here might actually bounce around inside this duct looking thing. And that's why it's called ducting until it escapes. So who was from Hawaii?
Yeah, it's Travis.
Have you ever heard of the Pacific duct?
No, I haven't. no.
Okay. So there is, let's say you go up to Mauna Kea, where you're at 14,000 feet. And then you go to Southern California and you're at 10,000 feet. Well, what happens is during the summertime, you get a tropoduct that can open up between over the ocean, because you have hot air and cold air and hot air and cold air. People will actually go up on top of the mountains and aim a signal up into the duct that they think is there. And if they are lucky, people in California and Hawaii from mountaintop to mountaintop can cover a distance of 2,500 miles on, let's say, 5 gigahertz. Just by putting a signal into that duct on purpose. Pretty crazy, right? I mean, that's microwave frequencies. That's Wi-Fi. So that's known as tropospheric ducting.
And what frequencies does it work best on?
It totally varies on what the duct is. I mean, my experience with ducting was that I was in my dorm at the University of Maryland on the 9th floor of Hagerstown, or on the 8th floor of Hagerstown Hall, for those of you who know where that is. And here's my antenna sitting out on my windowsill. And here's my TV with my rabbit ears, because we didn't have cable back then. And one Sunday morning in May, I turned on the TV and was flipping around the UHF stations, so about 600 megahertz, and I picked up a signal from Connecticut. And I thought, well, that's weird. I better go get on the radio. And I was actually able to work from Maryland to Connecticut on 146 megahertz. So typically when a duct forms, it's going to work for a few different bands. And that was about 300 air miles on about 5 watts with just an antenna on the on my windowsill.
Now, I have a question.
Yep.
Would that work both ways?
Yeah.
So let's say if you were to communicate to someone in Connecticut and they heard you clearly, would that also, okay.
Usually.
I
Usually.
wasn't sure if it worked traditionally both ways.
Okay, so antennas are reciprocal. That means that the receive pattern of an antenna is going to be the same as its transmit pattern. Now, there is something that is called one-way propagation, which does exist where you don't have a good path both ways. It is entirely possible that the angles will only work in one direction. Usually that doesn't happen. Usually if somebody hears you, you can hear them. All right, what weather conditions can decrease range at microwave frequencies? That would be precipitation, again, water. Effective fog and rain on other bands. So if you look at the 10-meter band, that is far enough away at 28 megahertz. The 6-meter band at 50 megahertz, that is far enough away from microwaves that our radio waves are not affected by it. Okay, which we're on the page 48. For the region of the atmosphere that can refract or bend high frequency or VHF radiation or radio waves, that's the ionosphere. Long distance propagation is actually very common on HF. So for instance, if we were to take a listen right here, and I'm going to unmute this, I hope. Can everybody hear that?
I can hear it.
Yes.
I can hear it.
Okay, so that was a signal from Bulgaria being received in the Netherlands. So that's probably a good 1,000 miles. And that's on 14 megahertz. This is actually a web-based software-defined radio called WebSDR. And there are many of them that have been put out on the web, for instance. These are all web SDRs that are available to be listened to by anybody. You go to something called websdr.org. And so if you want to hear what's being heard on the high frequency bands or other bands in different other parts of the world, you can listen to that. I've actually been able to hear myself, which is kind of cool. I listened to a web SDR in Utah and transmitted from out here in Oregon and was actually able to listen to my transmitted signal. Okay. Okay, so now we also, unfortunately, need to talk about something else. So long distance ionospheric propagation is far more common on the high frequency bands. That is always true. Now, we mentioned day and night. Now, there's another thing that we also have to talk about, unfortunately, which is something called the 11-year sunspot cycle, which looks like this, where you have 0 and 11 and roughly 22. It's plus or minus, a few months here and there, where basically you get up to a peak in sunspots. And those are your peaks. And then here are your dips, right? So we actually go through sunspot.
Hey, Scott, you got a couple of questions in chat here.
Oh, okay.
From Crystal.
So the antennas, the magnetic H, and the so the only thing that plays into polarization by definition is the electric field. The orientation of the wire determines what the electric field will be doing. The magnetic field is always going to be perpendicular to the electric field. Always, always, always.
So can you hear me?
Yeah, go ahead, Crystal.
So going back to the antenna example, if an antenna is basically like going in that slanted direction you had, would you say like the electric field was perpendicular to that?
Well, so here, let's say this is my antenna, just a horizontal. I mean, any piece of wire is an antenna. So let's say my antenna is horizontal. It's parallel to the ground, right? Right? It's parallel to the ground.
Oh, that's the antenna. I thought that was the ground. Okay.
Nope. Let's say that's the antenna. Here's the ground. The electric field would be this way, which means that the electric field is horizontal.
Okay.
If I were to redraw it and my new antenna was like that, a little bit crooked, but my wire is up and down, my electric field is up and down. So my polarization is vertical.
Okay, I was wondering because your example had it at like halfway between horizontal and vertical.
Well, and that's because I had to draw it in 3 dimensions. So if I, for instance, if I draw my wave, right? Here's my 3-dimensional axis. My wave is traveling in this direction. That's known as my pointing vector, Poynting. That's my pointing vector. That's direction of travel of energy. Then my, let's see, 1, 2, 3. My electric field in this case would be going up and down. So it would look like this. And my magnetic field, by definition, would have to be going like this, because it always has to be perpendicular. Does that drawing make sense?
So in relation to the antenna, when the antenna is like kind of like
So if in this case, which way is my electric field going? I define my electric field as going up and down, right?
Yeah.
What would the antenna have to look like? That's making
based
that.
on what you said earlier, the antenna would have to be up and down.
Well, it would have to be vertical.
Yeah.
My antenna would have to be vertical. So that is the wave that is made by a vertical antenna.
Okay, maybe I just misunderstood the previous antenna.
That's okay. That's why we're doing this.
Thanks.
I don't mind spending a little extra time on it. This is actually really important fundamental stuff. So, yeah.
I might maybe suggest drawing a 3D box that might help visualize what you're drawing.
Ooh, we're getting tough here.
This is a suggestion.
Well, I mean, so if I were to label these axes, this would be the, let's see, that's Z, that'd be Z, this would be X, this would be Y. And or I could take it and rotate it. So so you know, this is where it gets a little bit tricky. If I were to take this and draw my axes again, right? And I said, instead, we're going to draw my electric field like this. Let's see, X, Y, Z, like that. So that's my electric field. Notice it's parallel to this axis. My Y axis, my magnetic field would have to go like this. Up and down, as the energy is traveling in this way. So my electric field would have to be going that way, and my magnetic field would have to be this way. And the only antenna that can make that, because the electric field is going back and forth on this axis, oops, wrong color pen, on this axis, the only antenna that can make that is, Crystal, which orientation?
So if that's the electric field going parallel to the ground, then it would also be parallel.
That's right. It has to be a horizontal antenna, which is a horizontally polarized antenna. Exactly right. So if I were to take this antenna and rotate it 90 degrees, my electric and magnetic fields would have to rotate 90 degrees. The whole assembly would have to turn in space. Does that make sense? Yeah, it's three-dimensional. Yeah, it's a little tough to get, but it really, what's most important is to know that if you have a vertical antenna will work with another vertical antenna. That's why everybody on their car has a vertical antenna. Because if let's say you have a mobile radio and here's your antenna sitting on top of the car and you're trying to talk to another person or other people who have a similar polarization, you need to be doing this. Besides the fact that this, if you're looking at it from the end, there's no asymmetry, right? It's going in all different directions, which is exactly what you want.
So with, this might be jumping ahead. So
okay.
Is there a benefit with the Yagi antenna then?
Yagi antenna is gonna have directionality. So let's say that, I mean, now you can take a Yagi antenna, and this is for all you guys in the hazards lab, right? Okay, so this is a Yagi antenna, which we're gonna do antennas. We just haven't done them yet. So this is your antenna right here. All the other ones are just parasitic elements. This right here is the antenna. I have drawn this antenna in a vertical polarization. I could also take this antenna and do this with it, where this is the antenna itself. So this is a vertical and this is horizontal. Now, it's true that in some cases you would want a horizontally polarized Yagi. Sometimes you'd want a vertically polarized Yagi. It really comes down to what signals are bouncing off of and things like that. But essentially, this antenna will give you gain in the forward direction. In either case, it will give you a preferred signal in one direction or the other. And for all you guys who are doing the hazards lab, if you're trying to talk to, you're trying to get signals from a remote sensing area and you're pointed at each other, that's how you optimize your signal path. Aiming those antennas is really important.
It's not omnidirectional, right?
Okay, so let's see, sunspots. Okay, so sunspot peak basically goes like this in 11-year cycles. So sunspots typically relate to solar ionizing radiation. So ionizing radiation is the thing that generates all those electrons floating around. So when you have a peak, you have a lot of electrons in our atmosphere. When you go down to the bottom, you have just a few electrons, which basically means that since we already know that more electrons transmits to high frequencies, and this translates to low frequencies, the 10-meter band was dead for the last 7 years. I mean, dead. 10 meters, we're actually right about here right now. 10 meters is actually doing really well because we have a lot of sunspots, we have a lot of ionizing radiation, and we have a lot of electrons floating around to bounce high frequencies back down. So the 6 and 10-meter band, 10 meters is alive. It might actually be enough ionization that the 6-meter band during the sunspot peak can actually be used for long distance propagation. And that uses the F layer. Again, this is up in the F layer of the atmosphere, way up high. Long distance 10-meter band propagation via the F region, again, because it requires daylight and solar radiation from dawn to shortly after sunset during periods of high sunspot activity. So basically, you're at the peak, and it's during direct sunlight. That's when you're going to get the best propagation at highest frequencies. Another thing that we get with HF is fade. Fading is caused because if we're looking from the Earth and we're talking over a distance of, let's say, 2,500 miles, we're bouncing a signal off of the atmosphere right here, off of the F layer. The F layer, it turns out, is not smooth. It's actually kind of lumpy and inconsistent. And it also moves and it goes up and down in altitude. Well, as that happens, we can get multipath. When we get multipath, we get another signal that comes up like this, another one that goes this way, and they all end up in the same place. And sometimes they add and sometimes they subtract. This is a random process based on what this looks like up in the sky. So random combination of signals up in the sky generates fade. And you can actually hear that. It kind of sounds. And then it starts to come back. This can be a minute long. This can be 5 minutes. This can be every 5 seconds or 10 seconds. Signals propagated by the ionosphere are typically elliptically polarized. That means that they are kind of like a random polarization. There's some in this direction and some in this direction and some in this direction and some in this direction. When they get down to Earth, it doesn't really matter if your antenna looks like that or like that. There's enough signal in there in that particular polarization that you've picked that a high frequency antenna, it doesn't so much matter. The signals are all randomized when they get up there anyway. Okay, now that we've covered RF, how about
Scott, I got a
another
quick
5-minute
question.
break, everybody?
Oh, sure.
No, go ahead, Travis. Let's hear it. Let's hear the question.
Yeah. So early in the lesson, you were saying that the high ionization, the high frequency during the day, less than the 20-meter wavelengths, that's when you'd want to use that.
Yep.
And low ionization is the low frequency at night, and it's greater than 20 meters in wavelengths.
Correct.
But we've got the 6-meter, or excuse me, the 10-meter band, like right at the high end of the high frequency that we shoot during the day.
Yep.
Is it a real specific cutoff at 20? Where, or
I mean, everything's a rule of thumb.
Right.
So one thing I can show you is we're going to open up a website here. And this is called VOACAP. And does anyone remember the Voice of America? Okay, so the Voice of America is the US government's voice to the world over shortwave radio. And VOACAP, Voice of America, put a lot of money into figuring out how to most effectively use its money and signals to get signals around the world. So one thing that came about was that you can, for instance, say, okay, let's say to West Africa, when am I going to have my optimal propagation? Well, here we go. Prop charts, prop wheel. There we go. So notice we've got time on the wheel from 0 hour, and it's in universal time, from starting at 0 hours UTC all the way around, back all the way to 0. And we've got our bands from 10 meters all the way to 80 meters. So this basically shows, based on sunspot numbers, based on ionization levels, expected ionization levels on a given day, from the West Coast to, is it Nigeria? What our optimized signal path is going to look like. So in other words, at our best path, it looks like is going to be 12 meters at 2200 UTC, which out here is 2 in the afternoon, or no, 3 in the afternoon. So let's pick a different path. Let's go to Norway. Totally different looking box. Let's go to South Africa. Looks different again. Now, what we can do is we can also bump up our power and we increase our likelihood. What we've basically done is put more power into the signal path, and we've tilted the odds in our favor. But now let's look at Australia. Changes a little bit. Let's go to Japan. Changes a little more. Let's go to Central Russia. Looks totally different. Let's go to India. All right, now, ready? We're going to go to India, but now we're going to follow the long path. Looks totally different. Long path, short path. Short path, long path. So basically that's going the long way around. This is a wonderful tool. Antarctica, really good short path, really hard over the long path. So one reason you can see why it would be difficult over the long path, which is the dotted line, is that there are a lot of signals that have to bounce over and onto and off of land. Which do you think is a better reflector of radio waves, land or saltwater?
Saltwater.
Saltwater is great. And in fact, if I go to the Middle East, for instance, notice that it's difficult. If I go long path, it's actually better because some of it's going over Antarctica, but look at all that saltwater path. And actually, I've worked into the Middle East from my house on very low power over the long path right around New Year's, because it's all saltwater and it's all daylight down there. So lots of ionization and lots of salt water. All right, 5-minute break, everyone.
Yeah, sounds good. Thanks for answering that.
All right, I know people have questions. It's a good time to ask.
Hey, yeah, so I was looking at the that last question. The signals propagated by the ionosphere are elliptically polarized, allowing antennas to be vertical or horizontal. Why don't are there antennas that allow us to make those elliptically polarized electromagnetic
You can have
frequencies, or-
circularly polarized. But typically that's either going to be right-handed or left-handed. I mean, not really per se. That's largely because signals are absorbed and re-radiated in a random pattern when they get up into the sky. The energy is actually absorbed and re-radiated. And if you think about how it's re-radiated, you have randomly placed atoms, randomly placed electrons. They're randomly re-radiating the energy.
Okay, okay, that makes a lot more sense.
It's really an
it's the
amazing
same, It's the same
process.
thing. It's the same thing as if we had a bunch of antennas all oriented in vertical all the way through the degrees to horizontal.
Yeah,
Got it.
exactly.
Okay, cool.
It's really an amazing process. You know, the fact that energy is absorbed and re-radiated, and that also goes a long way toward explaining why, you know, if you start to look at, we're going to get into the math in a little bit, like really soon. If you start looking at decibels, and which we are going to start to do, we're going to start to look at some very, very, very small numbers. Like the fact that the sensitivity of a receiver, let's say, is minus 135 dBm, right? That doesn't necessarily mean anything yet, but this M is a millivolt, right? And minus 135 decibels, we'll go 130, is 0.0000000000001, and then times 0.001. That's how many volts is actually coming down the antenna to hear a signal. I mean, it's an absurdly small amount of energy that we're receiving. So if you look at how much energy is actually lost, let's say between here and, I don't know, between here and Europe, it's an almost immeasurable amount, you know? It's 99.999999999% of the energy disappears into the atmosphere, or it goes into space. That tiny little bit that comes back is what we are actually able to listen to. And it's only through, you know, the magic of what we're about to cover that we can hear any of that stuff. All right, everybody ready to go? I don't hear a no. Is everybody ready to go?
Yep.
Okay.
Yeah, I am.
All right, here we go.
Yes.
Okay, so now what we're going to do is I'm going to share this thing again, which is right there. Okay, this is the electromagnetic spectrum, right? Okay, so what we've now done is we've looked and seen what all of these different things do, how they all behave. These are all different frequencies and different wavelengths. They're all basically forms of electromagnetic energy. They're all essentially different colors of light. When we listen to a radio, we are basically listening to we're tuning our radio to a different color of light. So for instance, when I turn on my radio here in my hand, Temperature 69. Wind calm. Can everybody hear that? Sun. Temperature 67.
Yep.
Okay, so that's NOAA weather radio on the frequency of 162.400 megahertz out of Eugene. That signal is a carrier wave at 162.4 megahertz with modulation that puts information on the wave, essentially coming out of a recorded message. It's modulating the wave, which is basically changing it so that it has information. That signal is then being received by this radio tuned to that frequency, which is then stripping the modulation back out of the signal so that I can then listen to it. It's essentially demodulating the wave. So the wave itself, the 162.4 megahertz wave, is a carrier frequency that is being changed with information so that the information can be transmitted over a distance. And then the information is being stripped out so that I can then listen to it, or it can be used by my computer or whatever it happens to be. The first part of the class, which we just did, was understanding what waves are and how they behave. The next part of the class is figuring out how to make them. And in order to do that, we have to start all the way from scratch. And when I say all the way from scratch, I mean all the way from scratch. So the first thing we're going to do is we're going to understand what electricity is. Okay, so first thing we have this thing called an atom. And I'm going to draw a helium atom, not to scale. So we have a proton and a proton and a neutron and a neutron and an electron and an electron. And I can't know exactly where the electrons are. I can only assume that they're in certain areas. Protons are positively charged, neutrons are neutral, electrons are minus. This is a balanced system where we have the same number of pluses and minuses. This is an atom. Again, this is a helium atom. Okay, so instead of this, if I were to make, let's say, 27 pluses and actually let's go with 29. That's my favorite. And 29 electrons floating around. That would be copper, right? Okay, so copper has 29 electrons flying around. So it turns out that copper is actually very good at having a loosely bound electron toward the outside. And if you put two copper atoms next to each other, what you might find is that an electron might be able to move from one, and as it drifts in, it manages to push another one back out. So on a macroscopic scale, what you end up with is electrons flowing in and electrons flowing out. Well, the flow of electrons is known as a current. Current is the movement of electrons from one place to another. That's all it is. So if I were to say, well, what's going to make this current happen? If I were to just take this copper atom and just leave it where it is, would there be any current flowing through this copper from one copper atom to another? Would there be any reason? And the answer is no. There'd be nothing pushing an electron in from one side so that one comes out the other side. Something has to be pushing it. Well, that push is known as voltage, or an electromotive force, or EMF. And that is what pushes electrons along in their path. Electromotive is literally electron movement. It's the force that causes electron motion. So an electromotive force, or an EMF, or a voltage causes current. Current is the letter I, voltage is the letter E. Okay, so now I'm going to take this atom and I'm just going to replace it with a block of something. And I'm going to put a voltage across it, which should move electrons from one point to another through this thing, which I'm going to label as letter R. Well, I don't know what this letter R is, but I do know that this letter R exhibits some resistance to flow. I don't know what it is. I just know that it doesn't necessarily always like electrons to flow through it. So if this R is very big, I would call this a resistor, a very good resistor. If this R is very small, it basically says that it's not good at resisting the flow. And I would call a good resistor an insulator, and I would call a bad resistor would be a conductor. So let's think about what would make a good resistor. Some things that are good insulators. Everybody? Let's hear it.
Glass.
Glass. Give me another one. Yeah, give me another one.
Ceramic.
Fiberglass.
Ceramic. Give me another one. Oh, I saw wood. Yeah.
Fabric.
Yeah. Okay.
Rubber.
Rubber. How about air? Dry air. Actually, and water without any ions in it. Water is actually a pretty good insulator. Okay. How about something that's a good conductor? Give me something that's a
Copper.
good conductor.
Copper.
Copper. Another one?
Zinc.
Zinc is okay.
Silver.
Gold.
Silver's good.
Platinum, gold.
Platinum, gold. Why actually gold is really special. Why? Actually, copper is a better conductor than gold. But why do we like gold? Because gold doesn't oxidize. It doesn't tarnish. It stays clean.
You can buy 100 feet of copper wire a whole lot cheaper than you can buy 100 feet of gold wire.
That's true. But if you're trying to make card edge connectors that aren't going to oxidize or corrode, that's why you typically do it out of gold. But you don't do gold wire. Exactly. How about aluminum?
Yeah.
Aluminum is actually a really good conductor. What's the problem with aluminum?
It expands and contracts.
Yeah, a little. But what's the problem with aluminum wire? Or aluminum in general?
Very fragile.
It's brittle, but that's okay. It's lightweight.
It takes on high temp.
It does, but how about another one with, has anyone ever worked with aluminum?
Yeah, it oxidizes.
Oxidizes like crazy. Yeah. You get this black layer, which isn't necessarily bad, except that aluminum is a really good conductor, and aluminum oxide is a really bad conductor, which means that if you're using aluminum and you're trying to tie two aluminum wires together, you can do it. They have to be cleaned before you do it. And then you have to basically seal them inside oil or grease or something to keep it from hitting air, because otherwise they'll just oxidize. And like happened in New Jersey, then if you forget to do that, or you made that connection before it was known that you needed to do that, then you burn down a bunch of houses because you used cheap aluminum wiring, which did happen. Okay. Now this is actually true. A whole bunch of houses in New Jersey burned down in the 70s because of that. All right, so now what we're going to do is we're going to have a voltage, electromotive force. We're going to have, this is a sign for a battery. Now, battery has a plus terminal and a negative terminal, and we're going to have this block, and we're going to replace this block with a resistor. That's a sign for a resistor. And now we're going to say, okay, everybody, what charge does an electron have? Is it plus or minus?
Minus.
Minus. So where do you think the minus charges would come out of this battery? The top or the bottom?
The bottom.
Bottom. Okay. So the electrons would flow around the circle like this. Okay, for those of you who've done electronics before, where is the current defined to come out of? Which terminal? The plus or the minus?
Plus.
The plus. Yeah. So here's your current, which is letter I. So that is by definition where the current flows, out of the plus and back into the minus. And we can actually tie this minus to this thing called a ground that defines us as 0 volts. Okay, so the question is, what went wrong? Everybody, what do you think? What went wrong? What happened was that back in the 1850s or even earlier, when they were coming up with these things, they figured out that if they took two pieces of metal and they put them side by side, it generated a voltage. But the electron wasn't discovered for a long, long time after that. So it was not known that it was a negative particle, which basically meant they got it wrong. They figured that it came out of that the current came out of the positive and then back into the negative, which basically meant that the scientists got it wrong. And unfortunately, we still have this today. And even if you go into engineering school, the positive terminal is where the current comes out of. And it goes around the circuit into the negative. So you're just going to remember that electrons are negative, but for the sake of everything else you do for the rest of your life, with regard to electronics, current comes out of the positive and into the negative. Okay. So now there's a simple equation which was determined by a German scientist named Georg Simon Ohm. E is equal to I times R. This is the first form of what's known as Ohm's law. And I can draw this with that same triangle, EIR, like that, or the same circle. Sometimes it's done as a triangle. And the way this works is that whichever one you don't know, this will help you get over the fact that you say, okay, well, let's see. If I have the I and the E and what's R, well, how do I remember how to do that? You just basically take the R, I don't know what it is, and you're left with E divided by I. So R equals E divided by I. Similarly, if you don't know the E, they just gave you I and R. You would basically take this, say, oh, I don't know that. Well, obviously this is I times R. And you just basically plug your numbers in and you get the right answer. So here we go. The electrical term for something that causes electrons to flow is voltage. We're on, by the way, page 7, actually page 8 now. The name for the flow of electrons in a circuit is current. Again, current. Okay, so our voltage is letter E. Current is letter I. Resistance is letter R. E equals I times R. Ohm's law. Okay, so, and E again, voltage is electromotive force. I don't know why ampere picked that. This is measured in volts. This is measured in amperes. And this is measured in ohms with the Greek letter omega. Okay, so the name for current flow, that's current again for electron flow, and it's measured in amperes. Okay, so now what we're going to get into is something which is known as AC versus DC. Okay, so I'm going to draw another circuit here. And I'm going to have a resistor because resistors are good for that. And I'm going to have a question mark device here. Okay, so if I were to draw this as a plus and a minus, and that is time invariant, which means it never changes, which way is my current always going to go in this circuit? It's always going to go that way, and it's always going to go around and back into here. But now, what if I made it so that this instead went like that? When I changed it to that, which way would my current flow? Flow down. Right, it would go the other way. Right, it changes direction. Okay, so what if, now that's still direct current if I left it alone and never changed it, right? Direct current means that it never changes direction. But now let's say that I had this thing that generated a pattern of current or voltage that looked like that. That was a sinusoidal curve. That sometimes it was positive and sometimes it was negative coming out of this terminal.
AC.
So that would be sometimes plus minus, and then it would switch to minus plus. And that would be known as AC, which is alternating current, because what ends up happening is that the current goes this way, and then it switches back and goes this way. It alternates direction. So an alternating voltage source will generate an alternating current in this circuit. This is nominally known as AC, or alternating current. Okay, the number of times per second that an alternating current changes in a cycle, what do you think that's known as? Everyone? Times per second, that's known as a frequency, and we measure it in what units?
Hertz.
Hertz. Okay, so let's look at our wall voltage. That's our most common AC voltage source. In the United States, our wall voltage is 120 volts AC, nominally. Stacy, right? 110 to 120. And what frequency? How many hertz? 60 hertz, right? Which basically means that we have 60 of, oops. That means we basically get this 60 times per second. So if we were to do that, how long does it take to make one full cycle? 1/60th of a second. Right? So if it's 1/60th of a second, that translates to about 16.6 milliseconds. And what's nice about this is that we used to actually have mechanical clocks that would be cycled, that would be run off of this 60 hertz. And that was accurate enough that we could actually have mechanical clocks that were driven directly off of 120 volts, because our time, our frequency was actually accurate enough that we could actually run those accurately, and they'd only lose like, a second a week or something like that at most. So how about if you live in Europe? What's your voltage look like? $230 volts. And how many hertz? I think Stacy's been around the world. What's the frequency in Europe? Anyone?
50 hertz.
50 hertz. This is true in South America and several other places in the world as well. So they basically are running at different voltages and different frequencies. So this is actually made, the different frequencies are actually made by a rotating machine where you basically have a magnet and a coil. And as those coils pass through those magnets, or vice versa, they're connected to contact, they're connected to wires, and those wires will basically generate sine waves as the machine spins around. And this can be connected to a turbine, this can be connected to a water wheel, it can be connected to lots of different things. And that's how we generate our power. But that's why we have sine wave power. Well, it also turns out that, we'll get back to this AC current in just a little bit. Units of electrical resistance are ohms. The current flow that's opposed by resistance Okay, now a resistor, does a resistor care which way the current is flowing? This is actually going to be very important in the near future. Does a resistor care which way it's flowing?
I'm guessing yes.
It does not. A resistor does not care if the current is flowing that way or that way. It does not care what the frequency is. Resistor is just a resistor. A resistor that's 10 ohms is just a 10 ohm resistor. So it can be direct current, it can be RF, it's just 10 ohms. If it's a good resistor, it's just certain resistance right here to any current at all. Okay, let's see. Ohm's law. We're going to do a couple of simple Ohm's law calculations. So I'm just going to make some up because it's easy to do that way. We're going to say 20 volts plus and minus, and we're going to have a 2 ohm resistance. And we have a current flow. Okay, somebody give me Ohm's law and tell me what the current would be. Tell me how you did it. Not everybody's shy. Don't be shy.
It would be 10.
It would. Give me tell me where to start.
The 20
Ohm's law.
volt.
What's Ohm's law?
Yeah, Ohm's law. The voltage is 20. And since we don't know what the current is, we know what the resistance is of 2 ohms. You would divide 20 volts by 2 ohms to get 10.
Yep. So if I did it like this, E is equal to I times R. And I don't know my I. I is equal to E divided by R. Is 20 divided by 2 is 10. So our current would be 10 amps. Here we go. Let's do another one. How about we have 120 volts and we have a 3 ohm resistor. That would be 40 amps because again, E is equal to I times R. We don't know the current. So I is equal to E over R is 120 over 3 is 40 amps. Okay, one more. How about we want to know what voltage we have. We don't know it, but we do measure. We put an ammeter in line. Ammeter goes in series. We've measured 4 amps, and we know that this is a 6 ohm resistor. So we know we have 4 amps. Okay, E is equal to I times R. It's equal to 4 times 6 is 24 volts. So we know we must have a 24 volt power supply there. And Stacy asked the next question. Does power come into this? Watts. Here we go. The next part of Ohm's law. Okay, there's 2 parts to Ohm's law. The first part is E equals I times R. Now we're going to take this and we're going to replace this with a 24 volt power supply. Plus minus. And we're going to say how much power is being delivered by that battery. Here's the second part of Ohm's law. That's it. P is equal to I times E. Notice you have your power in watts, named after James Watt, and you have your current, and you have your voltage. Okay. P is equal to I times E. And in this case, it's 4 times 24 is equal to 96 watts. Everyone agree with that? So our power supply is delivering 96 watts. Okay, so now here's the next thing. Where is the power going?
The resistor.
Because, okay, here's
Clockwise,
something that's
Eddie.
really important. Energy can neither be created nor destroyed. It just changes form. Agreed? It's conservation of energy. Okay. So if we have, okay, power, the definition of power is energy per unit time. That is the definition of power. Well, we have energy that can neither be created nor destroyed, which means that power can neither be created nor destroyed. Agreed? Because it's just energy divided by time. That being said, if we have 96 watts being delivered to the circuit, what is happening to it? Where does it go? Has to come out somewhere. Anyone?
Heat.
Heat. And what is the heat generating device here?
The resistor.
The resistor. Right there. Okay. And now, what we can do is, if we really want to, we can say that this is 0 volts because it's at ground. We're going to tie that to ground. And we're going to go around the circuit. And we're going to start at our 0 point, and we're going to mark our voltage levels. So we're at 0 volts right here. How about after we get through the battery? What's our voltage? Should be at plus 24. How about when we get through this ammeter? That usually has no voltage loss. So we're still at plus 24. So what do we know about this perfect wire? This perfect wire has how much resistance? We're going to say it's a perfect wire. It has no resistance. And if E is equal to I times R, and resistance is 0, how much is our voltage drop? That's also 0. So we don't have any change in our wire, which means that if we're at 0 volts on this side, and we're at 24 volts on the other side, how much voltage has to be lost in that resistor? Just getting electrons through it. How many volts have to be lost getting through? That would be 24 volts. You have a 24 volt loss. So if we know that it's 24 volts that's being lost in that resistor, we can rearrange this equation if we really want to. And we can say P is equal to I times E, and E is equal to I times R. And we know E, and we know R, and we have an I, so we can take that I and put it in there, and is equal to E over R times E is equal to E squared over R is equal to 24 squared divided by 6. Oh, this isn't so much math. This is just algebra. But yeah, it's 96 watts. So basically that power that's going in is translating to power going out. And resistors turn power into heat. That's how they work. All right. So now that's how we do our power calculation. So now we're going to do another power calculation, which is, let's say that we have this thing called a load. And this is a 100 watt load. And we have our power supply over here. And we are going to, again, say this is a 100 watt load. And this power supply is operating at 20 volts DC. Okay. How much current has to be flowing in order to generate 100 watts?
5 amps.
5 amps. P is equal to I times E. We can also write it like this, PIE. And we know our power is 100 watts and our voltage is 20 volts. I is equal to P divided by E is equal to 100 divided by 20 is equal to 5 amps. There we go. Very good. Okay. Let's see, series and parallel. Okay, now we're on to series and parallel. Okay, if you watch a TV show and you watch every episode in a series, that means you watch them in order. If you are an electron and you are moving through this wire, this is known as series because you have to go through both of them in order. First you're here, and then you're here, and then you're here as you're moving. Those are that is a series connection of resistors. If I were to redraw this, like this, these now are parallel lines. These resistors are now connected in parallel. Importantly, the calculations for figuring out what the total resistance of two things in series and parallel are calculated like this. If this is R1 and this is R2, it's simply R1 plus R2. If they're in parallel, the easy way to think of this is it going to be bigger or smaller? And the answer is actually smaller, because if you think of it as water flowing down a creek bed, if it suddenly sees a wider path available, there's two choices for it. It can go down one or the other. The current will split and it actually becomes an easier path. So the overall resistance of two resistors in parallel is actually less, and it's actually R1, R2 over R1 plus R2. But you don't have to remember that. Essentially, what happens is that when you come to this first combination, the resistances add, and the voltage drop that you experience in each resistor will be defined by the value of the resistor. In this particular case, the voltage at this point is going to be the same for both resistors. The voltage at the end point is going to be the same for both resistors. So the current that you have going down each leg is going to be defined by the resistors. So in the first case up here, your voltages are going to be split. This is actually a device known as a voltage divider. This one is actually known as a current divider. And the amount of voltage or current division that happens is defined by the resistances themselves, because you have a different I1 and an I2 flowing down them. Your V is the same, and in this case, your I is the same. And again, this is series, and this is parallel. Okay, so in which of these is the DC current, is current the same through all components? Which one would you pick, everybody?
Series.
That's right. In which one would you say that the voltage is the same for both of them?
Parallel.
Parallel. Which one is better for wiring your house?
Parallel.
Parallel.
Very good. And why is that? What happens if you wire your house and all the lights in your house in series?
If one light is if it goes off, then that's it for the other lights.
Yeah, all your other lights blow out. It's the classic Christmas tree lights. All the lights go out. In addition to that, if you do it that way, because they have different voltages, all the lights will dim every time you add another light. And depending on the individual resistances of the lights, some will be brighter than others. Again, the classic Christmas tree lighting. In which type of circuit is the voltage the same across all components? Again, that is parallel. Okay, DC power. So we're on page 16. What's the term for the rate at which energy is used? Energy per unit time is known as power. And the unit of power is
Watts.
Watts. And the cool thing about that is that a watt is a watt is a watt, whether it's chemical energy or a mechanical energy or heat or movement or friction. Energy is energy and power is power. So if we use, for instance, a motor that has an output of 750 watts, and it is perfectly efficient, how much power do we have to put in electrically to turn that motor?
750 watts.
750 watts, exactly. And the other cool thing is if we know that this motor is 50% efficient, how much power would we have to put in?
1500.
1500, because it's only 50% efficient. So where does the other 50% go?
Heat and noise, maybe, I don't know.
Yeah, basically anything that you can discern. So yeah, noise. People don't usually think of noise as a source of, as a way of power coming out, but noise, if it makes light, sparking or something, that's power. A little bit different looking, and the big one is heat. So let's say that you have an electrical facility, right? Or let's say you have a conveyor. This is actually very common in the kind of work that I do. And this motor is attached to a mechanical thing. And to generate 750 watts of movement, it requires 1500 watts. But where's the other 750 watts going? We already said it's going to heat. Maybe it's going to vibration. So every so often, what they have to do, maybe it's heating up the bearings. They actually go through and they use a thermal camera and they figure out where the heat is. Because like a lot of the work I do is a sawmill. What happens if you get something that gets really hot and it's covered with sawdust?
Combustion.
You get a fire, and the fire is something you do not want to see in a sawmill. So
then where did the horsepower as a measurement unit come from?
Where specifically, I'm not sure, but 1 horsepower is 746.7 watts. That's the conversion. I mean, I assume somebody, came up with it just like an inch. It was probably related to something to do with a horse. But this is the actual standard conversion that we use now. And for engineering terms, we basically say a horsepower is about 750 watts. So a 3 horsepower motor is 2.25 kW. Stuff like that.
That's interesting.
Okay, now we're into math for electronics and conversion of units. But before we do that, I want to cover one more thing. I want to cover AC because we all have AC. And this is something that gets covered in the general test, but it's really actually very important. So let's say we have 120 volts AC. We actually call our wall voltage 120 volts in the United States. And in actuality, this is actually 120 volts AC RMS. Has anyone seen that before? RMS?
Root mean square.
Root mean square. Okay, so basically what that means is you take the square root of the square of the voltage times current, or I take that back. Let's say the square root of that dt. So basically it's the square root of the interval, the square root of the integral of the voltage squared. What this does for you is it basically says, okay, well, it's going to go back to our power equation. And power is I times E is V squared divided by R. Right? Okay, so power is proportional to the voltage square. So if we were to look at a voltage that looks like this, does it matter if we're looking at the instantaneous power that can be made by that voltage? Does it matter if the voltage is plus or minus? Because we're going to square it anyway. So if this is minus 100 and this is 100, when you square it, the minus terms go away. So in actuality, then what you're really looking at is the power availability at that time. It looks like this. That's the square. It's always going to be a positive number. So now we can basically look at it over one cycle and say, how much does it go up or down? And basically this is our power availability during that cycle. And then we can take it and we can average it over one period. Right? We can figure out what it is for all the times and then average it out over one full cycle. RMS is equivalent DC source power. So in other words, 120 volts AC RMS is the voltage that is capable of delivering the same amount of power as 120 volts DC. That's what it means. And so when we look in our wall, what we will actually see is that when you take a measurement on your wall voltage, if you have an oscilloscope that allows you to look at voltage versus time, it will look like this, right? It's a sine wave with a peak of plus 170 and negative 170. Any guess as to why? Anyone?
I would guess because the peak of the AC and the valley of the AC, that has to be converted somehow. So it has to have more to get that energy into the
Because
circuit.
during this time, you basically have almost no power delivered. Exactly. So when it peaks, it actually has to peak higher to make up for the dips when it's almost zero. So if you're basically, if you're generating the equivalent of 120 volts, the amount of power that 120 volt DC can make, this actually has to peak at plus and minus 170 in order to generate the same amount of power. And that's why we call it 120 volts AC RMS. And that is actually what's inside your wall. So this is actually really important because let's say that you're building a circuit. We're going to get into power supplies right after lunch. And in that power supply, you have a capacitor first. And this is rated at 125 volts AC, or just say 125 volts, period. And you hook this up to 120 volts AC. What will happen to that capacitor, everyone? And
Doesn't it
Stacy
become an
said,
inductor?
A Bluey.
Stacy said it will explode. She's right. It will explode because what will happen is that this voltage, 120 AC, goes from negative 170 up to positive 170. And this capacitor is rated for a maximum differential across it of only 125 volts. These peaks both exceed that value. Even though this says 120, it's not really 120. It actually peaks at 170. And that's why it's important to understand when they say 120 volts AC, what it really means. Any questions on that? Any comments, thoughts? Anyone's head exploding?
Do they have to say it's 120 AC RMS?
Well, it'll typically it'll say 120 volts AC.
Okay.
It's rated for 120 AC, but a lot of capacitors don't say that. They'll just say rated for 50 volts peak. Rated for 200 volts peak. A lot of MOVs, metal oxide varistors, will say rated for 100. In fact, you can buy them with very, very, very varied ratings. An MOV is a shock is like a spike suppressor. You can buy them for a whole bunch of different voltages. You know, when you go to Mauser or DigiKey and you buy an MOV, it will have a rating. The rating will define what it's good for, and it'll be sold with a peak voltage rating, not an RMS voltage rating. Because to be honest, the manufacturer doesn't care how you're going to use it. That's up to you to decide. Questions? I think we can cover this one thing before lunch because I think most people have an idea of this. So we are on page, what I believe is 18, that says Math for Electronics and Conversion of Electrical Units. Okay, so what we're going to do really quick is we're going to say that everything we deal with is in powers of 10. Right? The 0 is actually an incredibly useful number because a 0 is a placeholder that represents something's been multiplied or divided by 10, which means it can represent things that are bigger and bigger and bigger or smaller and smaller and smaller very, very easily. So let's say that I have 3 times 1,000. I can write that as 3,000. I can also write that as 3 times 10 times 10 times 10. Or I can say that this, by convention, is 10 to the 3rd power. I can write this as 3 times 10 to the 3rd. I can also say that this 10 to the 3rd can be replaced by a little letter K, which means kilo. So if I have 3,000 watts, I can replace this. I can write it as 3 times 10 to the 3rd watts. I can also replace it as 3 kilowatts. So what's nice about this is that we don't have to carry all those extra zeros if we don't want to. So we can say, okay, how many milliamps is 1.5 amperes? So 1.5 amps, they want to know how many milliamps is it. So a milli is 0.001 amperes. Well, we start with the original number and we say 1.5 amps is equal to 1.5 times 1,000 times 0.001, right? All I did was multiply those two things together and that's equal to 1. I can do that all day long if I want. Well, I now have this right here. And I have this left over. That's 1,500 times MA is 1,500 milliamps. The trick with dealing with bases and dealing with these letters and changing units and things like that is I can take anything and multiply it by 1, and I always get the same thing. So for instance, if I started with 3,000 watts, and I wanted to say how many microwatts are there? All right, what does micro mean? 0.000000, sorry, 0.000001. That is what micro means. I could also write this as 1/10 times 1/10 times 1/10 times 1/10 times 1/10 times 1/10. or I could also write this by convention as 1/10 to the 6th power, or 1 or 10 to the -6th power. Doesn't really matter. By exponents, I could also do this. I could say 3000 watts is equal to 3000 watts times 10 to the 6th times 10 to the -6th, because this right here is 1. I just multiplied it by 1. It's still true. 3000 watts is still equal to this. I've just written it a different way, except now I have this required 10 to the -6th, which is the same as micro. So now I can say it's 3000 times 10 to the 6th times micro times watts. Okay, so now I can expand this out. I can say 3000 is 3 times 10 to the 3rd times 10 to the 6th microwatts. Okay, well, another thing you can do with exponents is if the bases are the same, the base is 10, I can add the exponents. So that then becomes 3 times 10 to the 9th microwatts. So now I've just changed the base and changed the units, and everybody's still happy. The key with any of these, the key with changing units on any of those things is that so long as you multiply something by 1, it's perfectly legal. If I have 6.28 and I want to change that into something, let's say 6.28 volts, I want to change that into millivolts. I can basically take that and multiply that by 1000, so long as I then multiply it by 0.001. Perfectly fine. Nobody has any argument with that, because 6.28 is equal to that. I just did something to it, and I undid it to it immediately. Now I want millivolts. Well, right here, that's milli, 0.001. And I'm left with 6.28 times 1000 is 6,280 millivolts. And I just converted my number. Okay, so let's see. If I start with hertz, let's say I have 3000 hertz. How would I convert that into kilohertz? I could say 3000 times 1000 times 0.001, because I know that this is going to be kilo. 1000 is the little letter K. So then I'm left with these two things. 3000 times 0.001 is 3 kilohertz. Okay, and and you can go either way with that, so long as you know what your end goal is. Okay, so the next thing we can do with this is working with the number 10. So what's another way to write 10 to the 6th? Is 1 million is equal to 10 times 10 times 10 times 10 times 10 times 10. Those are all ways to write mega. Okay, so from here, the next thing we can do with this is we can say, okay, well, those numbers are really big. Let's figure out a convenient way to express our big numbers or our really small numbers in a convenient fashion. So a long time ago, somebody figured out that we're going to use a logarithmic thing with a base of 10. This is very similar to how we discuss earthquake strength. It's like if we have an exponential curve and those numbers get really small down here and really big up here, we want to give them some meaning as opposed to just seeing a graph that's like super huge. So what we do is we say, well, the number 10 is raised to some power to give us some value. So let's say that we have a graph that looks like this. Down here, we have a value of 1, and up here we have a value of 1,000. Well, okay. We could say that this is 10 to the 0 power. Up here at 1, 10 to the 10th power. Sorry, 10 to the 1st power. Oops. And then up here at 100, this is 10 to the 2nd power. And up here, we have 1,000, which is 10 to the 3rd power, and we're going to mark that 3. Well, if this is truly an exponential curve, notice we have right here the value, and this right here is the exponent to which the base was raised. So this is known as the logarithm. That's called a logarithmic curve. This is the basis for something that we call decibels. So the way that our decibels work is that we have something called a bell, which is the log base 10 of something x over y. And this is just a ratio of two things, which we don't know what those two values are, and it doesn't really matter. So this is basically saying the log base 10 means 10 raised to the what gives you something. So let's say that we have log base 10 of 100. Let's say x is 100 and y is 1. To what power would 10 have to be raised to get 100? Somebody tell me.
10 to the 2nd power, right?
That's right. So that would be 10 to the 2nd power is equal to 100. So that would be 2 bells. That would be a change of 2 bells. Well, what it turned out was that there was a lot of decimal points in there in the end answer. So it was decided that a bell was too big of a unit. Well, I guess it was too small of a unit, right? At too many decimal points, not enough granularity. So what they did is they multiplied it by a factor of 10. And they came up with something called a decibel, which is a 1/10 of a bell. So it's 10 log base 10 of x over y. That is the formula for a decibel. So if we again start with 100 up there and 1 down here, we get 10 times log base 10 of 100. This we already said was 2, and that's 20 decibels. And actually that's true. If you have a power gain of 100 right here, that's equivalent to 20 decibels. The nice thing about decibels is that because they're based on a log base 10, things that are logarithmic, like 10 to the 3rd times 10 to the 6th is 10 to the 9th. What do we do with the exponents? 3 plus 6 equals 9. That does work, which basically means we can take our decibels and add them together, and that means that we actually would have multiplied this number. So let's take this in its simplest form. Let's say we have a gain. We started a level of 1, and we have a gain of 10 times. So we have 10 over here. And then we take a gain of 10 times again. Well, 10 times 10 would give us 100. So let's figure out what the intermediate gain is right here and just verify that this is actually right. So our starting point is 1. Our ending point is 10. So we're going to say decibels is equal to 10 log base 10 of 10 over 1. What's the log base 10 of 10? 10 to the something is equal to 10.
1.
That would be 1. So that would just be 1. This would be 10 decibels. Okay, so this is 10 decibels. And this one right here, we start at 10 and we go to 100. This is the second time. 100 divided by 10. Well, it turns out that is actually the exact same calculation as we just did, because 10 over 1 is the same as 100 over 10. So that's obviously 10 decibels. All right, so now we're going to take that leap and we're going to say, well, are we really actually right? We're going to do the bigger calculation. We're going to prove that this works. We're going to go from 1 all the way up to 100 and ignore the intermediate step and make sure that it works. dB is equal to 10 log base 10 of 100 divided by 1. And again, what's the log of 100? 10 to the what is equal to 100?
2.
2. Well, this is 2, so that would be 20 dB. Well, guess what? We know that the entire jump is 20 dB. And look what we got up top. We got 10 plus 10, which means that it works, which means that all we have to do is add our decibels together. It really does work. Okay, now that we've established that that actually works, there are really only a few things that you need to know. And this is actually true with basically throughout most of engineering, most of ham radio. There are 2 things you need to know. 10 times is exactly equal to 10 dB. And 2 times is approximately equal to 3 dB. Now, the other thing is that these are gain. Now we can also have a loss. 1/10 is equal to negative 10 decibels. And 1/2 is approximately equal to negative 3 dB. So in other words, making it bigger is a positive gain. Making it smaller by the same factor just changes the sign. What's really cool about this is that let's say that you have a gain from 100 watts, or sorry, from 25 watts as your starting point to 100 watts. 10 log base 10 of that. I don't really want to calculate that, right? I mean, what's log base 10 of 4? That means 10 to the what power is 4. I don't want to do that, right? That's not pretty. I'm not going to do it. What I'm going to do instead is to say, okay, well, I started at 25. Looking at these things, what's my next logical jump? If I want to get up to 100.
50.
50. I can do 20 to 50, 25 to 50. That's a change of what? How many times?
3 dB.
Well, it's 2 times,
Oh,
right?
sorry.
And then I go from 50 up to 100. That's a double. Well, I already established that every time I double, that does what? Approximately 3 dB. And this is approximately 3 dB. And I just add them together. And what's my gain?
6 dB.
About 6 dB. And that is true because the math says so. And I didn't have to go and find an exact calculation. Now, I could do an exact calculation, and I think the answer is probably like 6.06 dB or something. But to be totally honest, if I'm just doing rule of thumb calculations, order of magnitude, I don't care. It doesn't matter, I mean, basically it's off by a tiny little bit, but if I'm looking at a gain of 100 dB or something, I don't really care about the decimal point if I'm just doing a basic calculation. So these are really the only things that you need to know. And unless you're doing extremely precise calculations. Those are the only things you really need to know throughout most of radio. So let's say that I go from 10 down to 1.25. That's a little trickier, right? But actually not really. What's a half of 10?
5.
What's a half of 5?
0.5.
And what's a half of 2.5?
1.25.
1.25.
Okay, so this is a half, and this is a half, and this is a half. And every time I go down by a factor of a half, that's -3 dB. -3, -3. What's my sum? -9 dB. Ta-da. Simple calculations. The reason that decibels then become so important is because they are a common language by which a lot of other different things are measured. And I'm gonna just do this real quick and then we'll all go to lunch. And sorry, I'm not buying. So what I'm going to show you is something called cable loss. Here we go. When you go to specify a cable, notice what you have. No, I don't want to use that. I want to go somewhere else. Let's go to this one. There we go. Coax attenuation chart. Notice what you have per 100 feet of cable, your signal loss per decibels in 100 feet at frequencies and for given cables. And notice it's measured in decibels. So if you have power gain, power amplifier or receiver gain in positive decibels, you can then directly add these to your attenuation and figure out what your end result is. And if you use an antenna, for instance, let's say you pick this antenna. Notice what it says. What's the gain? 11.1 dBi. That's dB with respect to an isotropic radiator, which we'll get to after lunch. What that really means is that if you have an isotropic radiator, which is a theoretical radiator that radiates in all directions equally, you will have a gain in that forward direction of 11 decibels. You can then combine that with your cable loss or gain, or cable loss, your amplifier gain, and you can play with all of them together. They can all be combined into one big equation. All right, that's all I got before lunch. Questions?
How long do we break for?
Half an hour.
Half an hour. Okay, cool. Thank you.
All right, see you guys at 1:05 Pacific time. And if you have any questions, I'll hang around for a few minutes. It doesn't take me long to make my lunch. If you've got any burning questions. All right, lunchtime.
Hi, Scott, can you hear me?
Yep.
Scott, I got a question for you. Okay,
Okay.
so after the exam tomorrow, if, let's say I pass, hopefully, I understand that there's a $35 processing fee to the FCC, correct?
Correct.
Okay, now, how do I go about doing that?
So what'll happen is that, as I understand it, once you pass it and the VEC submits your information to the FCC, I think you log on using your FRN and just give them a credit card number, if I'm not mistaken.
Okay, so when I do log in, I will see that, that probably
There should be,
have
yeah,
my,
I would think there's a pending application.
right, that's what I was gonna ask you, right? If I see the call sign and maybe it's something like that says pending, right?
There won't be a call sign yet, I don't think.
Oh, there won't be the call sign yet.
No.
I got you. Okay, but it will have something pending and then I just pay directly to the FCC from there. Okay.
Yep.
I thought maybe I had to pay the examiner.
No.
Of the exam.
Nope.
Okay. Okay, great. That was my question. Thank you.
So you said you're in New Jersey?
Yep, New Jersey.
Where in New Jersey exactly?
Union. It's about a good maybe 10 miles from New York City.
Okay.
Yeah, but I was born and raised in Jersey City, which is about like a mile or two away.
That's like right across the river from Jersey,
Yep,
from New York.
exactly.
Yeah.
Yep.
Scott, you said
go ahead.
You said you had went to the Middle East. Where were you at?
No, I've never been to the Middle East.
Oh.
I've been to South America. I've worked in Europe.
Nice. Where all at?
Let's see. I've done a lot of work in Chile and Uruguay, and
nice.
I mean, I've spent cumulatively like 6 months in Uruguay, in Chile, working over spread out over 10 different times. And I've done work in Finland and Norway and Austria.
Nice.
Yeah. And you know what's really cool? I got to operate from Finland and Austria and Chile and Uruguay.
That's awesome.
Yeah, it was. It actually was really cool getting to operate from a different country. And
yeah.
You get actually I'm trying to remember if I have any pictures. Let me see. I used to. Let me see if it's on this computer. Give me a second. We got 5 more minutes, so miscellaneous junk. Oh yeah, this is a funny one. That was the station that I set up in my hotel room in North Carolina. Can you see that?
Yeah.
Yeah, notice the left foot.
Yes, wonderful.
Yeah. But I take my equipment, like a little portable station, everywhere I go. It allows you to kind of kill the time in a lot of hotel rooms.
Definitely.
Let me see.
In all the studying I've done for 2 exams here, I'm not at all familiar with the left foot concept. What do I need to know?
Okay, let me see if I can. All right, I can't find those photos. Okay, so there's a that was actually unintentional that the left foot was in the photo, but it turned out to be very funny. So there are a bunch of Q signals. All right, there's something called Q code, and Q code looks like this. There are many that are used for telegraphy, right? Morse code. And they're basically Q because there aren't many words that start with Q. So Q and two other letters is a Q code that signifies a something. You know, like QTH is your location, QSY means change frequency, QRM is interference. And there's a joke that, notice it, I don't think it's in here, QLF. Nope, see, QLF didn't make it. QLF was basically sent as an insult to somebody. And QLF basically means you're sending so badly. Are you sending with your left foot? And I thought it was really funny that actually made it into the photo. Like, oh, look at that. My left foot ended up in the photo. QLF, question mark. Yeah, it was totally unintentional.
Could you share that photo again? I'm not aware
Yeah.
of what y'all are speaking of.
Oh, yeah, let me find it. So let's see, it's my Goldsboro ham radio station. There we go. Let me just share it. And there it is. So here's the log from Goldsboro, all the countries, all the places I contacted, and there's my station. Right, so you've got the computer, you've got my antenna, which is a little alpha loop antenna, magnetically coupled loop, little compact Yaesu 817, signal link, which is the sound card, and my left foot. Which those of us, when I posted this to my one of my users groups, it got a lot of laughs because, you know, we all do a lot of Morse code. And I said, when I pointed out my left foot was in there, everybody knew what QLF was. So again, QLF is an insult, meaning, are you sending with your left foot? In other words, you're sending so poorly, you must be using your left foot. It's meant in humor, of course. All right, it's 1:05. We're going to start again. Is everybody ready? You got questions from before? If I don't hear any questions, I'm just going to roll right into it. Because why the heck not? All right, let's see. We are on page number 23. What electrical component opposes the flow of current in a DC circuit or an AC circuit? That would be a resistor. What type of component is often used as an adjustable volume control? So I'm going to draw a resistor right here. And now I'm going to make this an adjustable resistor. I could also draw it like this. Those are both known as potentiometers. A potentiometer or a pot is a variable resistor. The electrical parameter controlled by a potentiometer is resistance. One of the big things is for a volume control. And actually, it turns out that there are multiple different tapers. Some of them are linear, some of them are audio, because audio power goes up as the square of the voltage. So an audio taper volume control, if you use it for something else, will look kind of weird, and vice versa. Okay, capacitors. Okay, so in order to understand what a capacitor is, we basically will draw two metal plates right next to each other with a gap in between. The gap is filled with something that is usually air or plastic or tantalum or something that is a dielectric, which means that it is a non-conductive material that fills the gap. And so what we do with a capacitor is, the only point of a capacitor is that if we put positives over here, positive charges, what will happen on the other side is that we end up with negatives over here, because all the positives repel, they'll go this way, and the negatives will repel. And we'll end up with positives on one side and negatives on the other. That's what a capacitor does. So if we hook it up to a circuit that looks like this with a battery, the negatives will flow this way and the positives will flow back the other way, and the capacitor will charge up eventually to the same voltage as the battery. Now, the tricky thing about a capacitor is if we then take this and we flip the battery so that the positives are now on the other side and the negatives are on the original side, well, then we have our positives here, and our positives flow that way, and our negatives flow this way. Similarly, our negatives flow up this way, and our positives flow that way. And then what we end up with is a capacitor that is now charged oppositely. So we end up with our negatives over here and our positives over here. So if we have DC, a DC power source, again, this right here, the capacitor will simply charge up to the voltage of the DC source. Now, if we flip it back and forth, the capacitor will basically discharge and then recharge based on the new voltage. Well, this actually has a really profound impact, because let's say that we were to take this circuit and instead say we're going to have this curtain here, and behind this curtain we know that there's a capacitor, but we can't see it. And we're going to hook this up to an AC power supply, which is sometimes plus, and sometimes it goes and flips back the other way and goes plus like that. Well, every time that happens, the capacitor charges up and then it discharges. And if it happens fast enough, what happens is that for all intents and purposes, we can't even see the capacitor there, right? What happens is that the capacitor then starts to act like something else. It starts to act like just a piece of wire, because if it happens fast enough, we're able to just put current into it and it's like it's not even there. So
I'm out. What's in the circle on the bottom with the
that's an
squiggle in
AC
it?
power supply. AC power.
Well, that's the AC. That's your house current.
That's, well, any AC supply.
Okay, but it's not DC. It's AC.
Right.
Okay.
Right. If we use a DC power supply, it'll charge up the capacitor and just sit there. What's the frequency of DC?
The one in my house is 13.8.
No, what's the frequency? DC has no frequency, right?
Whatever you say, boss.
Well, think about it. Does it ever change direction?
No, that's why it's called direct current.
That's right. It has no frequency. It has zero frequency. So,
okay. All right, back to your lecture already in progress. We got AC on the bottom and the capacitor on the front that goes away.
Well, the capacitor is really there, but it acts like it's not even there. So for a capacitor at AC looks like a short circuit. And a capacitor for DC, essentially, if we replace this with a DC power supply, the DC charges up the capacitor, and then it gets fully charged. And once something is full, how much more can you put into it?
Nothing. It's
nothing. All right. So if there's nothing else, if there's nothing else that's flowing into it, and you have no current flowing, no electrons flowing, that means you have no current. What can you simulate? What does no current look like?
It's an,
Open circuit.
yeah, that.
So a capacitor at DC looks like an open circuit. All right, so the trick is that a capacitor stores energy in an electric field because it has charges that are opposite, and each pair of charges creates an electric attraction between them. But since they're being physically held apart by that gap, they basically have an electric field energy in between them. So capacitor, again, stores energy in an electric field. And the unit of capacitance is known as the farad, named after Michael Faraday. Represented by the big letter C. Okay, next, an inductor. Okay, in order to do this, we have to imagine we have a straight piece of wire. Next, doctor. Oh, that's funny. Okay, so we have an inductor. Well, again, we're going to just use a straight piece of wire. All right, so everyone hold up your thumb on your right hand. And now take your fingers and roll them forward. A current going in the direction of your thumb makes a magnetic field going in the direction of your fingers. So the magnetic field actually forms a loop around a current. So if I drew a current that was like that, then the magnetic field would go into the page and out of the page like that. This goes, the X means into the page and the dot means coming out of the page. And this would just basically create loops like that. So long as the current was flowing. So a current makes a magnetic field. A magnetic field also makes a current, as it turns out. Okay, but now let's say that we have an inductor. We're going to basically take this and we're going to make this inductor in the shape of a coil, where you basically now have current flowing this way. Current flows through all the links, and what you end up with is a magnetic field. Let's see, like that, and then like that. You're going to end up with a magnetic field that forms lines that look like this. This should be somewhat familiar to everybody in that this is how you build an electromagnet. If you take a nail and you put a wire, you wrap a wire around it and hook it up to a battery, you can pick up paper clips, right? It's like a third grade experiment. But if you haven't ever done it, it's really fun. You should try it. But basically what you create is a north and a south pole, and you have magnetic field lines that go all the way around the coil. Excuse me. Well, again, this is called an inductor. The letter is L, believe it or not, and the unit is henries. And as it turns out, a farad or a henry is a very, very large unit. Those are both extremely large units. So typically we're into millihenries over here. And for capacitors, we're usually into microfarads or picofarads, which are very, very small. Like a 1 farad capacitor is a gigantic capacitor. Okay, well, with regard to inductors, let's say that I were to hook this up to a battery. Plus and a minus. I have a current that's established, a magnetic field that's established, and everything's happy. I have energy that's stored in a magnetic field. And so long as my power supply is still connected down here, my battery, the magnetic field energy stays there. Everything's happy. All right, now I can disconnect a capacitor. Let's look at that capacitor again. And I charge it up using my battery. And now I suddenly disconnect my battery. Does the capacitor stay charged? Yes or no?
Yes.
Yes.
A certain amount of
it does.
time.
It does. Okay, but now let's say that I have this inductor, and so long as my battery is still connected, I have a magnetic field. Well, now let us disconnect the power supply. Just take it out. What happens to my magnetic field energy?
Disappears.
Well, nothing disappears. It's energy. You can't destroy energy, right? We have a problem, right? Because we have that energy that's stored in that magnetic field, but it can't go nowhere. So what happens is that energy actually says, you're not going to do that. And if there's a gap right here, what will happen is that magnetic field will actually cause a voltage to appear across that gap until it gets large enough to dissipate the energy. So what do you think that form might take? What do you think it'll look like?
The spark.
A spark. Now, we actually use this in some places. Does anyone know where?
Flash bulbs.
I don't think specifically flash bulbs, but maybe to generate it.
Casey says welding.
Yeah, it could be welding, arc welding, other places.
Spark plugs in vehicles.
Spark plugs in a car. Yeah, and in fact, that was the simplest way. We used to have something called a coil and points, and you would essentially have this coil that was turned on, and then you suddenly break it, and these two wires would go down into your spark plugs through the distributor, and then that would go like this, and you'd get into a spark plug that looked like this. And you would develop a spark, which would ignite your fuel. So that's a practical use of magnetic field energy. Now, therein lies a little bit of a problem, because let's say that you have this magnetic field and you did not intend for this to happen. So typically what we do with this magnetic field is, if we have it hooked up like this to a battery where we have a plus and a minus, we then add another device here, which looks like this. Anyone know what that's called? We haven't done it yet, but we're going to.
Diode.
That's a diode. A diode is a one-way thing. So in this particular case, what happens is when this thing is running, the diode is out of play. And when the power supply goes away, the diode serves as a path to dissipate the energy. That keeps your, and that's actually known as a snubber diode, and it keeps you from destroying your contacts. Okay, what electrical component is typically constructed as a coil of wire? That's called an inductor. It stores electrical energy in a magnetic field. The ability of something to store energy in a magnetic field is known as inductance, and the unit of inductance is called the Henry. Excuse me. Now, the same way that we just did, and this is what I would call a little bit of enrichment beyond what's normally taught. And so what happens is, in this particular case, we just said that a capacitor for AC is a short circuit and a capacitor for DC is an open circuit. Well, now let's draw our coil. if I hook this up to DC, that's just wire, right? It makes a magnetic field. This actually looks like a short circuit. An inductor for DC looks like a short circuit. But let's say that I replace this with an AC circuit where I'm continually flipping things back and forth. What was the problem we just ran into when we disconnected the power supply completely? What happened to the magnetic field energy?
It needed a place to go.
Yeah, it needed a place to go. Well, so inductors are resistant to changes in current flow. They're naturally resistant to it, which means that if you try to increase the change fast, what'll happen is that an inductor will say, I'm not going. And it'll eventually say, you're not getting any current through me. And an inductor will look like, at very high frequency AC, it'll look like an open circuit. Now, in actuality, these are at the end points. So this is for very high frequency AC. In actuality, somebody brought up the letter Z. Who was it that brought up Z before? Somebody brought up the letter Z. Z is impedance. Z is impedance, which is similar to resistance, but different. Resistance is the ability of something to resist the flow of DC current. Impedance is the ability of something to resist the flow of AC current. For a resistor, they are the same. For capacitors and inductors, they are not the same. And in fact, not only are they not the same, but for capacitors and inductors, the impedance is frequency dependent. So we're going to put something here called X. X is reactance. And Z is actually R plus JX. If anybody wants to stick around and learn imaginary numbers, I can teach them. But basically, reactance for an inductor is 2 pi FL. And reactance for a capacitor is -1 over 2 pi FC. Or really it's plus, but then it's a negative. It's got to be there somewhere. So importantly, though, what you see here is, do you notice there's a letter F in each of those? What is that little letter F?
Frequency.
Frequency, which means that your reactance, or because you actually have impedance, is equal to JXL and Z is equal to minus JXC. So really, we'll do it like that. So what this really means is that your reactance of an inductor gets higher and higher and higher, which means your impedance gets higher and higher and higher as frequency goes up. Well, if it gets higher and higher, it looks like an open circuit. Whereas with a capacitor, as your frequency gets higher and higher and higher, the denominator gets huge, and this whole thing goes to 0, which is actually what we saw up here, open circuit and short circuit right there. So what's cool about this is that capacitors and inductors can be played with in such a way that you can actually make a frequency dependent circuit. So if I have a this followed by a this has a negative and this has a positive X. And I can actually pick them so that negative XC is equal to, or I can say XC is equal to XL, in which case they are just X and they completely cancel each other, in which case they just look like a straight line. And all this goes away at one particular frequency. And that's the basis of something called a tuned or resonant circuit, which is the basis for how virtually every tuned thing, and there's tons of them in here, and there's tons of them in here, and there's tons of them in your iPad, and there's tons of them in your computer. Anything that deals with analog circuits, anything that deals with amplifiers has tuned circuits. And the basis for every one of them that uses analog components are inductors and capacitors. All right, batteries. Certain batteries are rechargeable and certain batteries are not. The carbon zinc battery is the old heavy duty battery, which is not rechargeable. Nickel metal hydride, lithium ion, lead acid batteries, those are all rechargeable. Okay, next. This is a diode. This is the cathode. This is the anode. If you find a diode, it might say 1N4007 on it. The cathode is marked with a band. That's usually thought of as the negative terminal. That's the banded end. Current is allowed to flow in this direction only. If you try to push current through the other way, it will not work. Let's see, depending on the material of construction of a diode, that'll determine how much voltage drop there is. So for instance, if I have a battery here that is 3 volts, and I have a diode like this 1N4007, this will drop 0.7 volts in it because it's a silicon diode, which means at the other side, I will only have 2.3 volts left. If instead this was, I believe, let's say a 1N914, that's a germanium diode, and that drops 0.3 volts. So I would have 2.7 volts left on this side. And that's just a function of the material itself. The reason that it's a function of the material itself is that now we have to look at these things that are called semiconductors. Semiconductors are made of materials that are neither resistors nor conductors, neither insulators nor conductors. Silicon and germanium, and there's a few other ones. Intrinsic material, what's special about silicon is that its outer electron shell, it can hold up to 8 electrons, but it has 4, which means it can either gain 1 or lose 1 relatively easily. If it gains 1, then it acts more as a negative. If it loses 1, then it acts more as a positive. So this material, silicon, if we just take it as a brick of silicon, it doesn't really play either way. However, if we were to take this and make this P silicon, which means we add a few more positives to it, we add some stuff that has a lack of electrons, and make this side slightly N. This is a PN junction, and it allows current to flow in one direction. The fact that it has this junction inside it determines which way things can go. The other thing we can do with a diode is we can take like this. We can do a P and then intrinsic and PIN. This is known as a pin diode. These are used for very high-speed switching diodes. They basically act in the same way, but because they have this intrinsic silicon in between, it changes the characteristics of the diode. We can also make a diode that looks like this, but then we can add another thing to it. Or we can, because we have 3 things now. Anyone ever seen one of these before? Look familiar?
transistor?
That's a transistor. That is actually a bipolar junction transistor, or a BJT. And more often than not, this is actually drawn like this, where we have our collector, our base, and an emitter. And this is actually an NPN diode, or NPN transistor. And you might notice that the PN looks like that. Well, that kind of looks like that. And what happens is that you have a plus and a minus here, and this is a special device that when you have a positive bias here, what that does is that it opens up this big channel from one end to the other, so that what you end up with is that a small signal can make a very big copy. And why would we want to make a big copy of something small? What would that be called?
Amplification.
That is an amplifier, exactly. So a transistor can either be used in, depending on the mode you're using it in, as a switch or as an amplifier. Okay. One thing we're going to cover also is this. This is a diode. We're going to have little arrows coming out of it. When this diode turns on, because of forward current, it does this. Anyone recognize that? That is a light emitting diode. Notice what's coming out of my phone. Forward current into the diode makes it emit light. Okay. Transistors. Let's talk a little bit more about transistors. Okay. So now that we have this 3-terminal device, basically a stack of material, stack of semiconductor material, we've just created something called a bipolar junction transistor. And that's what my BJT looks like. So a bipolar junction transistor has this thing called gain. Gain is a ratio of how big this thing gets compared to what's making it. So that's a transistor's ability to amplify a signal. Let's see, as far as a transistor goes, a transistor's curve from input to output, if it were perfect, what do you think it would look like? Probably like this, right? It would be a straight line. Ideally, that's what it looks like. In actuality, it actually looks like this. So a transistor actually has 3 operating ranges. This part is cut off. This is the linear range. And this range is known as saturation. Basically, in saturation, once you dump so much into it that no matter how much more you dump in, it really can't do anything with it anyway. If it's in the cutoff range, that basically means that it doesn't even have enough input to turn the thing on, to turn on the output. So depending on how you're going to use your transistor, that determines which areas you want it to be in. So if you're building something called a linear amplifier, well, you would probably want it to be in the linear range so that a small change produces a proportional change in the output. That would be this range right here. That's the linear region. However, if you're doing something that is a computer, something digital, for instance, where you definitely want a 1 or a 0, either hard on or hard off, you would probably want it to be this range. So on would be this range, and off would be this range, because it's digital. It's either 0 or 1. You don't want any of this iffy stuff in between where it could be one or the other. I mean, that's not how digital works, right? So that's why a transistor can be used either as a linear amplifier or a switch, depending on how you use it. Again, in a bipolar junction transistor, you have the collector and the emitter, and the current is controlled by the base. So base, collector, emitter. Now, there's another type of transistor which looks like this. All right. So does anybody recognize what this is or what it kind of looks like in here? What does that thing look like?
Capacitor.
Two parallel plates. That makes a capacitor, right? So if I put a plus here, I'm going to attract minuses and vice versa. So what this allows me to do is by, instead of putting a current into this device, it allows me to just place a voltage right here at this point, and that changes how much current can flow through here by determining whether or not this area is suitable for current flow, whether it's attracted or repelled. So these are known as the gate, the drain, and the source. And this is known as a field effect transistor, or an FET. And the reason it's field effect is because a capacitor, you'll remember, works on the basis of an electric field. So this is a field effect transistor. Okay, we are on to schematics and circuit diagrams and cool stuff like that. Okay, we are on page 31. The name of an electrical wiring diagram that uses standard component symbols is known as a schematic. The point of a schematic is to show how things are connected, not how they're actually built, just what the electrical connections look like. So the first thing we're going to do is just redraw what has been drawn here. Okay, so they have component 1, component 2, component 3, and component 4. All right. All right, somebody tell me what's component number 1.
Resistor.
Yep. Okay, don't go anywhere. Component number 2 is? What's component number 2?
Not the bipolar junction
It
transistor.
is. That's, in fact, that is an NPN bipolar junction transistor. The easy way to remember which way it is, the fact that it's NPN, which way is the arrow pointing?
Downward.
Well, it's pointing outward, right? From
Or
the middle?
outward.
Well,
Sorry.
I would say that it's not pointing in.
I see what you did. Okay.
That's the classical way of remembering which is which. It's
Oh.
not pointing in, therefore it's NPN. All right, number 3,
An LED.
LED or lamp or something. And number 4,
Voltage source.
yep, we'll call it a power. So we'll call it
Power
a
supply.
battery. Or okay, how about number 5? All this stuff that I put down here is number 5.
Ground.
Ground. Okay, now ground. There are different ways to draw ground. Ground can look like that. Ground can look like that. Ground can look like that. They mean slightly different, but essentially the same things. Essentially, a ground is a common reference point for a circuit. Usually, we just call this 0 volts by definition. Ground is essentially the earth. It represents a 0 volt reference point. All right, so the way that this circuit works is that the transistor is basically splitting the circuit in half, where we essentially have a signal coming in over here on the left, When that's positive, what happens is that the resistor limits the amount of current flow. The current flows through that half of the transistor from the base to the emitter, which turns the transistor on. When that happens, the other half of the transistor allows current to flow this way. Well, the current came from here, it flows through here and through this number 3, which turns the light on. This is an electronic switch for turning on a light bulb. Okay, number 2. This is actually a really important part, and I like to spend a little time on this. Okay, so we have that. Okay. All right. Hey, Teresa, you still there?
Yes.
Okay, component number 1. Sorry, I'm going to pick on you, but I'm doing it.
Yep. Oh God, that is AC power supply.
AC power supply. Okay, component number 2.
That
Let's
is
let's say this is labeled 5 amps. What would that be called? We haven't really covered that one yet.
well, the shape of it and what we talked about, I want to say diode, but it says 5 amps. So
Yeah, it's not.
yeah.
Number 2, that is a fuse.
Okay.
And the reason that a fuse is included in a circuit like this is because if there's a short circuit somewhere, the fuse is designed to be the element that blows up when a certain amount of current flows through it. So
Got
you
it.
essentially pick that value so that it blows up instead of like setting fire to your circuit.
Okay, so it's basically a contingency plan that you build into your circuit.
Exactly. It is an overcurrent protective device.
There we go.
It's an OCPD. Okay, and in that time, I drew the whole thing. All right, number 3 is a switch. How about number 4?
Am I still answering these?
If you know it.
If yeah, number 4 looks like a, wait a minute. Transistor?
Nope.
Nope.
Air coil transformer.
That is a transformer.
Transformer, other keyword.
All right, let's see. How about number 5?
Diode.
That's a diode. Number 6?
Capacitor.
Capacitor. Number 7?
Resistor.
Yep. Number 8?
Light emitting diode.
An LED. Yep. Okay. Number 9?
The variable resistor.
Yep. That's a pot. All right. That's a variable resistor. And how about number 10? This is the enrichment part again.
Schottky diode.
Close. Not a Schottky. Starts with the letter Z.
Zener diode.
That's a Zener diode. Okay, so what we're going to do is we're going to work through this circuit. So what we have here is AC. We're going to draw in green what the voltage looks like at every point through this circuit. Well, so we're going to close this switch and we're going to allow AC to flow through this coil. Okay, so now we're going to draw this right here and we're going to draw this, but we're going to make this special. We're going to say that this has, each of those coils is wrapped around an iron core. So remember what the magnetic field around a coil looked like? It made these lines that look like this. Well, what happens if we wrap that coil around iron is that we get a constriction of the magnetic field lines in the iron core, which basically means that most of the magnetic field energy is contained in the core, and it's actually forced to travel around in a loop inside the core. Well, if we put power in here, what do we know about power? Power in has to result in
Has to go somewhere.
Has to go somewhere. Well, guess what? Power in translates to power out, which basically means that if we have power going in here, we have power coming out on the other side. But because a current, an AC current makes a time varying magnetic field, a time varying magnetic field makes an AC current. So what that means is we now have power going in equaling closely the power going out. There's probably a little bit of heating in this circuit, but this is a transformer. It only works for AC. On top of that, a transformer has an interesting property such that if we have 100 turns of wire over here and we have 10 turns of wire over here, if we have 120 volts over here, we will have 12 volts AC over here. It is proportional to the number of turns around the coil, because that basically changes the number of flux, the number of times that the loop goes around the flux, which changes the voltage that's made. Now, the interesting thing is that since power has to be conserved, right? If we have 1 amp going in over here, that's 120 watts. How much power has to come out on the other side? 120 watts. That's right. Okay. So if we have 12 volts, what's our current? 10 amps. Exactly. So basically what this allows us to do is have a step up or step down function. Now, this is a step down. In other words, we have 120 volts AC over here and we have 12 volts over here. Now, I could reverse this and say that this is going to be 10 turns and this is going to be 100 turns. And if I have 120 volts over here, 10 turns and 120 volts, how much will I get on the other side? I will get 1,200 volts. If I were to make this 1,000 turns, I'd get 12,000 volts over here. All right, so what's the practical application for this?
Until you got to the really big numbers, that looks like my power supply in the back room, where it's coming in at 110 volts and translating down to 12 or 13.8.
Yep.
So you can run my rig.
Yep. But how about when we're going the other way? When would you ever use a step up transformer?
When you're trying to consolidate a bunch of small power lines into a really big fat one to go across the desert with.
Yep. That's one of them. How about when you're, how about if you have a vacuum tube amplifier with a 5,000 volt power supply to run the tube? They make those. That's one of the reasons you're in this class, so you don't accidentally do something and kill yourself. So the other cool thing about this is that, let's say this is 12,000 volts at 0.1 or 0.01 amps. Now let's say 0.1. That's 1,200 watts. This is 10 amps over here. All right, so I'm going to ask, by Ohm's law, which is going to be a more efficient way of sending power through power lines? High current or low current? The power is the same.
Low current. You can
Low
always step
current.
it up.
And what's Ohm's law? E equals I times R, and then P is equal to I times E. The power loss is I squared R. So in other words, as your power goes up, your power losses get, they grow as a square of the current if the resistor is the same. And that's why we transmit power on power lines at, 750,000 volts, 1,000,000 volts, because we can do it at very low current and they don't have to use gigantic wires and cables, and they don't have to use, they don't have to basically heat up cables. That's the basic point of it. Why bother heating up the cables? Nobody's paying you for that. Okay, so now that we've done transformers, We still have AC over here on the other side. This is AC. Now, when the voltage is positive over here, our diode is turned on. When the voltage is negative over here, our diode is turned off. Well, we can see that we have a waveform that looks like this. It goes from positive to negative. What comes out of the other side of the diode? It looks like that. The bottom half is chopped off. This is half wave rectification. We basically have now something that is only positive or zero. This is what we call very, very ugly DC. Okay, so when it charges up to its peak, this capacitor charges up to its peak. When it goes down to zero, the capacitor is charged, and we get the effect of smoothing this out a little bit. The bigger the capacitor, the smoother it gets. Well, now we have this indicator here that lights up because we now have DC voltage. We can also have voltage limiting here and current limiting. And then we run this thing through a backwards looking diode called a Zener. So let's say that our voltage looks like this, right? Would you want to put that into your computer? I wouldn't. That's called ripple. So what we do is we use this thing called a Zener diode, which will say, let's say, has a reference of 9 volts, which basically means if the voltage goes above 9 volts, it's going to turn on with a little bit of resistance internally and allow only 9 volts to exist at the top part. Essentially flat topping the signal and taking all the other stuff and flushing it down the toilet. Which basically then gives you a nice, clean power supply. So this right here is a schematic for a half-wave rectified power supply.
A Zener thing cutting off half the wave.
Not half, but it's cutting off the excursions. Anything above a certain point.
Is that somehow similar to the single sideband that cuts off half a wave?
No.
No. Okay, thank you.
Okay, but now one thing I'm
Hey,
going to
Scott, I had a quick question. If you go back to that
Yeah.
diagram, because we got the AC current started on the left side.
Yeah.
I'm not seeing the diagram right now.
No,
but,
I know. I just erased.
Oh, okay. Yes, we got the AC current on the left side.
Yeah.
And it's alternating the current on the top where the switch and the fuse were, and then below where it just goes straight into the what's it called? The transformer.
Yep.
Sorry. Wouldn't that always create energy going through the transformer onto the other circuit?
No.
And it wouldn't,
because it's based, it actually is based on the draw. In other words, how much current is being pulled through the secondary determines how much goes into the primary. In other words, if there's an open circuit, there's going to be voltage, but there's going to be no current.
Okay. Got it. Thanks.
I got another quick question.
Yeah.
That half bridge rectifier, so the energy has to stay constant, right? Where does the other half of that wave go? Does it go into heat, or like how do you get rid of half the signal, I guess?
It basically just it creates a high impedance. It's the diode basically says that there's not enough voltage to forward bias it. Essentially, it just slams the door. And what happens is that is then echoed back in the transformer.
Oh, okay.
In other words, the current, the required current goes down, which also means that the amount of power that it can produce is not all that efficient because you're only producing power for half of the cycle. Now there is a way around that, which I'm going to draw right now. All right, so here's that. So this is always a little tricky. Okay, so this diamond thing, right? Okay, so when this is positive, we're going to go out like this, up and around and down and back and through here and back to here. So I draw this, there's that, and I draw this. Right, and then the other way, when it goes the other way, it goes like this, but now it has to go up through here. And oops, I drew that wrong. Darn it. It's really easy to get confused with this thing. Okay, here we go. Up, I got to follow the wires up through this way. Then out through here and down and back and up this way. Okay, there we go. This is a full wave bridge rectifier. And essentially what a full wave rectifier does is that only half of it operates during each half of the cycle. So that when we have a voltage that looks like this, during the blue part, the blue part activates, and during the yellow part, the yellow lines activate. And the overall result of that is that the load over here always gets power for the entire cycle. So if you're building a power supply, here's the load. The power supply, that load will get power the entire cycle, but it requires 4 diodes instead of 1. And this is a full wave rectifier. Does that make sense?
Yeah, definitely.
Is everybody good with that? And again, this is known as a full wave rectifying bridge. It's the basis for most power supplies today, because it allows you to use all the power that's coming in instead of only half of it. Okay, let's see. And in particular, what we're going to do a little bit of is going to do a switch. Okay. So this is a single pole switch. It's a single throw switch, which means it's either open or closed, and it's only one pole at a time. So now I'm going to take this switch and I'm going to do this and link these together. This is now double pole. A pole is basically a circuit. This is a double pole single throw because it's still only open or closed. That would be represented by like DPST. A single pole single throw would be an SPST. Now, I could also change this so that I had another pole here, or sorry, another possibility for my power to go when I link this together. So it has 2 options. They either go this way or they go this way. But either way, there's no dead spot. That would be known as a double pole, double throw switch, DPDT. So when you go to the store and you're looking for a replacement light switch for the wall, it's important to know what kind of switch you're getting, whether it's a single pole or a double pole or single throw, double throw. Just thought I would bring that up. Okay. Transformer changes one voltage, or one, if you want to think about it, one flavor of AC into another flavor. What device changes an alternating current into a DC current? That would be known as a rectifier. A diode is used for rectification. You can also do full wave rectification. If you think about it, rectifying means correcting. Full wave rectification with 4 diodes. Okay, let's see. Here we go with the next circuit.
So that means my power source is a full wave rectifier.
Most likely, yes.
It's a rectifier for sure, probably full wave.
It's probably full wave.
Okay, thank you.
Just to, for efficiency. Okay. Oh, this is one of my favorite things to draw. It's our first view of something called an antenna. There's an antenna. Okay. Now, this is a very special circuit. And okay, so we have component one, that's our power source, which is going to be AC, and it's actually going to be RF. What does RF stand for, everybody?
Radio frequency.
Radio frequency. Okay, excellent. Okay, component two, and also other component two, those are variable capacitors. Component three, that's an inductor, and it's a very special inductor because it's a variable inductor. Now, sometimes an inductor may look like this, in which case you can then move that connection from there to there. That would be known as a tapped inductor, because a continuously variable inductor is notoriously difficult to build. So very often they are tapped inductors. A continuously variable capacitor is not all that hard to build. So what this circuit basically does is, remember I mentioned that for capacitors and inductors, there's something called reactance and impedance. Impedance is something's resistance to the flow of alternating current. And in fact, Z is equal to R, which is resistance, plus JX. And J is an imaginary term, which basically goes back to the circle. So you have R this way and X this way. And that basically says that it ends up being here. So it has a magnitude and an angle. This is in the general class, if you're curious. So for this case, our capacitor and inductor are assumed to have no resistance. So we're going to say that our resistance is nothing. And we can pretty much ignore the fact that it's in two different dimensions and just say that Z is equal to JX for an inductor. And ZC is equal to minus J over XC, or minus JXC. Okay, so why is this so important? Well, we have an antenna which has a Z, which is some impedance. You're going to hear the word impedance from now on in this class, because impedance is, antennas have a resistance, but resistance is not really important as far as antennas go. What's important is this thing called impedance, because it operates at, because they operate on AC. Oh, go away. So, sorry, hold on a sec. Let somebody else get it. Somebody please get it. Okay. All right. Anyway. So that's our antenna impedance. Well, as it turns out, this is a capacitor. So I'm just going to use the letters JC for that, or ZC for that. ZC2 prime. I'm going to use ZL here and ZC2. Well, as it turns out, impedances add the same way that resistors do in series. So I have basically these two things in series. So I would add the Z of the the Z of the antenna to the Z of this capacitor. Well, effectively, this antenna can kind of be viewed as sort of like a ground, in which case now I have that combination in parallel with this ZL. And then all of that in series with that additional capacitor. What this allows me to do is take whatever this impedance is that the antenna has, and this is my radio over here. The radio is looking for an impedance of 50 ohms. That is how power that is the impedance of almost all equipment today, and it's chosen to maximize power transfer. So 50 ohms impedance, it's actually a characteristic impedance, is what is looked for by the radio. Well, let's say this is 362 ohms. Okay. So let's say this is 362 ohms. Let's make it even trickier. 362 plus J294 ohms. Something crazy. How do you make that look like something that the radio can actually dump power into? I mean, this looks nothing like 50 ohms. And the magic is that because capacitors can have a negative impedance, they can actually be used to cancel some of it out. And inductors can have a positive impedance, and another capacitor can be used to look like something. You can actually use this to tune your circuit at a given frequency to make it look like something that you can put power into. And this is known as an antenna tuner. And tunable capacitors and inductors are the basis for impedance matching, as it's called, which is very, very, very important. And
What happens if it's not tuned?
If it's not tuned, well, that's a really good question. Let me pull up a picture of this right here. Let me take this MFJ 901. I want to see the schematic of it. Give me 1 second here, and I'm going to show you what the inside of one of these looks like, hopefully. Product name. Okay. Notice what we have in here. There's a capacitor, C1, a capacitor, C2, and a tapped coil. Notice all these 12 different taps. So if I were to take a look at a picture of one of these, I would see something like this. An air variable capacitor. There we go. It looks just like that. So a capacitor is basically two metal plates with a gap in between. By having these on a shaft, you can change the amount of plate that's parallel with the other side. And you gang them together to basically add more space. And notice what the measure is here. 365 PF, which is a picofarad. This is a practical device right here. This is actually used for tuning circuits. So now the question comes up, what if you have a poor match? And the easiest way I can describe this is, let us, for instance, take a rope, okay? And you're going to take the rope, and this is going to have a length infinity, okay? And you grab the rope and you whip the rope, essentially creating a wave on the rope. What's going to happen to that wave?
It's going to keep expanding.
It's going to keep going. It's just going to keep going. A single wave is just going to keep going down the line. But what if the rope is infinity long?
In theory, just
It's
keep
eventually
going.
going to die
It's
off.
just going to keep going. You'll never see it again. Okay, but now we're going to take this rope and we're going to tie it to a doorknob. Okay, there's your doorknob. And you're going to take that same rope and you're going to make a whip. You're going to whip a wave on the rope. What will happen to it?
The wave will keep going until it reaches the doorknob.
And then
The energy is going to transfer either to the doorknob, with some of it coming back.
Yep. And it'll probably reflect on the underside or on the top, depending on which side the energy is. I don't remember if it'll come back on the top or the bottom, but either way, what'll happen is you will have a reflection coming back this way, which is just fine. Except what if you weren't expecting that and your hand is there? What are you going to feel?
You're going to feel that energy transferring to your hand.
That's right. Okay, so what if you're putting out a continuous string of pulses? They hit the doorknob and they bounce back. As you're continually going thump, 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 what's going to keep coming back and hitting your hand?
The same wavelengths that you're sending
Okay,
out.
so far so good, right? But let's say that you now have these signals, and for whatever reason, they start coming back on the top side. Whoops. And they're bouncing back as you're trying to make new waves. How well are you going to be able to make them?
Not at all.
Not very well. And in fact, what will happen if a wave, if it comes back and the wave you put into it was big enough that the wave coming back actually whips your hand and breaks a finger? Because it jerked your hand up and actually broke your finger.
Not a pleasant situation.
Right. This is a big problem, right? Well, this actually is known as a reflected wave. The rope that goes on forever, infinity long, this would be a perfect match. In other words, a signal that goes out and never comes back. You never see it again. This up top would be known as a serious mismatch. That would be known as an impedance mismatch, where basically you have a signal that goes out and then something gets reflected. And the worse the match, the worse the reflection, the bigger the reflection. So let's say that instead of doing a mechanical wave, you're actually putting out a signal that is let's say your transistor is running, 46 volts DC to generate a certain signal. Well, all of a sudden, on that same wire that it's putting it out, you have a signal coming back that's 28 volts DC. At the same time that you're putting out 46 volts DC, how much voltage are you going to have on your transistor? Someone?
46 and 28 or 74. aren't
Well,
they?
you're going to have 74 volts DC. What if your transistor is rated for 50 volts?
Something's going to melt.
You're going to smoke your transistor. So that is why if there's a big enough mismatch, most equipment today actually will sense this and intentionally reduce the amount of power that your transmitter is putting out to keep your circuit from getting destroyed. But a bad match will actually do that. So the reason that we do impedance matching is basically to allow us, let's say I have my transmitter at 50 ohms and I run it through this circuit, which is all tunable, and that goes up to here. And I have this big question mark, but I've actually tuned this circuit, this antenna matching circuit, so that as I'm sitting right here looking at this combination of the transmitter, of the antenna tuner and the antenna combined, it looks like 50 ohms. Do I have to look any further?
No.
Nope. My cable is 50 ohms, characteristic impedance. My transmitter is 50 ohms. My antenna looks like 50 ohms. I put a signal out into it and it never comes back. As far as the transmitter is concerned, the world is good. Now, what actually happens from this point on in the real world is another story. I mean, I still might have a really bad match. And out here, I might have a signal that, goes up, and because this is 50 ohms, I get signal that reflects back, and then it hits here and goes back up and comes back and goes back up and comes back. And every time it does, I get a little bit of signal out. So it might be terribly inefficient still. Now, the more times that it does that, the worse the worse my efficiency gets. And a lot of it is determined by the loss in my cable. And remember, we saw a little while ago that loss in cable is measured in dB per 100 feet. That was right before lunch. That's a measurement of how lossy cable is. If I have really good cable that doesn't have much loss, then I might not have much of a problem. Why is that looking like that? So weird. There we go. Losses in dB per 100 feet. Well, depending on how bad the match is up here at the antenna, I could actually have, I could have 10% of my signal going out and 90% going back every time. In which case, I'm making a lot of passes through that cable, which means that loss in my cable is really, really important. If I have really lossy cable, most of my transmitted signal, or in my radiated signal that goes into the antenna, is going to come out as what? What is not transmitted into the air disappears as what?
Heat.
Everyone? Did I hear heat?
Yeah, heat.
Yep, it'll do nothing but heat up my cable, which might keep it free of ice during the winter, but that's about it.
Why we are not considering the loss in the antenna itself?
Because there is effectively no loss, very little loss in the antenna itself, depending on what it is. I mean, if it's just a dipole, there's very little loss in the actual antenna. Most of the loss. Go ahead.
Yeah, what happens if we split that antenna and the matching circuit and keep transmitting only on the wire? It's the same case as you described before.
In other words, if you did what? If you took, let's say you took out the matching circuit?
Yeah, take it out and keep transmitting.
Oh, well, you're still going to be having signals going up and down, but now your transmitter is going to be exposed to all of those reflected waves.
Mm-hmm.
All that reflected energy.
Even if it's not connected.
Not connected to what?
Not connected to the circuit after the yellow vertical line.
In other words, if I did this with it and just jumped through it, so this is all gone?
And the antenna too.
Well,
like it's not connected to an antenna.
If I'm not connected to an antenna, all the energy gets reflected.
Isn't that an open circuit?
That would be an open
somehow?
circuit. As far as a transmitter is concerned, whether it's an open circuit or a short circuit, it really doesn't matter. You're probably going to destroy something.
Okay.
Yeah, I mean, power has to go somewhere. If it's an open circuit, it's going to all come back. If it's a short circuit, it's going to go through it and all come back. I mean, it has nowhere else to go.
So I have to make sure that my transmitter is connected.
Well, yeah, I mean, the fastest way to destroy it here, the fastest way to destroy a handheld radio's amplifier is disconnect the antenna and transmit at high power.
Oh my God.
That'll destroy it in a hurry. Yeah, that'll do some serious damage really fast. Okay, we're on page 36. Which of the following is a resonant or tuned circuit? That would be an inductor and a capacitor in series or in parallel, which we just drew, and we understood why a little bit. If we did it like this, that's a tuned circuit. It's a resonant circuit. If we did it like this, that's a tuned circuit. We can actually show this. You know what? Now's a good time to do it. Here we go. Everybody ready for this? This is magic. Z is equal to negative J over 2 pi FC. Z is equal to J 2 pi FL. Okay. So we have to make these equal and opposite from each other. 2 pi FC is equal to 1 over 2 pi FL. Equal and opposite. Solve for F. F is equal to 1 over 2 pi square root of LC. This is the resonant frequency of an LC circuit. Why is this important? Because if we pick our L and our C, that determines what our resonant frequency is. And at that frequency, if we were to draw a graph of impedance, we would find that it's high, high, high. And then at that frequency, we would have no resistance to current flow at all. There's nothing. So what does this look like it might be useful for? What does this graph look like it might be useful for?
I saw a graph like that last time my antenna got tuned.
Yeah, that's exactly right.
Grasp the obvious.
So the other thing we can do is if we draw it upside down, it looks like this.
SWR graph.
Now, how about a filter?
Yes, selective frequency, right? We select
a very selective filter, because this is our frequency and this is our amplitude. That is a selective filter. That's exactly why we want to use stuff like this. And by using by using a different number of inductors and capacitors or changing values, we can shift that peak up and down. We can make it wider, or we can make it taller and thinner. We can do all kinds of cool stuff with that, just with capacitors and inductors. Okay, what is the function of an SPDT switch? That's a single pole double throw. We're going to draw that. SPDT. Okay, so that's single pole double throw. Like this. It allows you to switch to here or to here, double throw, one way or the other. It allows you to take one circuit and switch it between two other circuits. A relay is basically this if it's connected to one of these, which generates a magnetic field and pulls the contact in. So that's an electrically controlled switch. A device that shows an electrical quantity as a numeric value is known as a meter. So I could have an ammeter or a voltmeter. A device that contains several semiconductors and other devices in one package is called an integrated circuit. We have lots of them in our phones, in radios. What type of circuit controls the amount of voltage from a power supply? That would be known as a voltage regulator. Electrical component used to protect other circuit components from current overloads. That's known as a fuse. A fuse is a sacrificial device. We typically will say, okay, well, let's build a little circuit here. And here's our 120 volt power supply. And here's our fuse. And here's our heater. And this is nominally, let's say, 1200 watts. This is a space heater. So 1200 watts, 120 volts. This would normally pull 10 amps. So let's say we put a 10 amp fuse in here. Let's make it 12. So that if we got a slight overload, instead of melting the wire, we would open up the fuse. Why should you never replace a fuse with something that has a higher rating than originally was there? So let's say that you replaced it with a 20 amp fuse. And then you had a slight overload where this went to 15 amps. And now instead of 1200 watts, you're putting out 1800 watts. And you're pulling 15 amps through this wire, which is rated for 12 amps. What happens to your wire?
It destroys it, right?
Yep. Well, your space heater catches fire, or the cord gets really hot and sets fire to the carpet that it's laying on, or something like that. So that's why you always want to replace a fuse with something of the same value. A good reason to use shielded wire. Shielding this is really important to note. If I have a piece of wire, any wire that is carrying a current generates what, everybody? What kind of field?
Magnetic field.
Magnetic.
Yes. Okay. So what happens if there's another wire that is in the magnetic field? What will happen on that wire?
Current will flow in it.
That'll make a current. It'll make a current that's similar to the original current. So if I have an AC current that's flowing here, what I will end up with is a small copy of that AC current flowing in that other wire. That is called crosstalk. And that is why we take this wire and we do this with it. And then we take this wire and we do this with it. And we ground this and we ground this, so that if there is any magnetic field being generated, it's contained inside this area. And then any voltage that exists, will get shunted to ground. There's really no chance for any of that signal to ever make it out to the other one. And that's why we use shielded cable. Okay. Let me see where we are. Let's see, we skip right over the electrical. We skip right over the RF and propagation because we've already done it. And let's see where we're on. I think we're on antennas now.
I had a quick
Oh,
question.
yeah.
Scott.
Yes.
So how does this grounding relate to balanced cables?
When you say balanced cables, you mean like twisted pair and stuff?
Yeah. Is that related to this?
I would never shield an individual wire in a twisted pair, because they have to have a differential voltage between them. Now you can have shielded twisted pairs. That's the same idea.
Sure. Okay.
Is that what you mean, or something else?
Somebody had spoke to me about balanced cables, like I guess the resistance between the insulating conductor and the inside being the same. Does that sound right or no?
I don't know.
Okay.
I mean, if we're talking about a feed line,
Mhm.
there's a symmetric feed line and an asymmetric feed line. And this is something that we'll cover, where you basically have like parallel line, which is two wires that are spaced. That's a balanced line. And then you have this, which is coaxial cable, where you have the shield and the center conductor. And obviously this is symmetric, but unbalanced, because you're going to have, you have the same overall current inside and outside, but the current density is going to be higher on the inside than the outside. So basically you end up with, like a radial field, and then another one going around in circles. Whereas in this case, you end up with a magnetic field going around each of these and an electric field between the two. So yeah, I mean, they both work. The nice thing about coax is that it's, self-contained. Whereas this, a bird can land on it or take a crap on it or something. So
Right. Cool. All right. Thank you.
all right, how about a 5-minute break? I know I can use it.
Down for that.
Yeah, sounds good.
All right. See
Sounds
you in
good,
5
sounds
minutes.
good. Thank you.
See you on 5.
All right, everybody ready to talk antennas and feed lines?
Oh yeah.
Was that a heck yeah?
Heck yeah.
Heck yeah. Okay.
Heck yeah.
I know it is a lot, but you know, in the end, you don't have to remember everything. But my goal is that I'm going to give you enough theory to remember stuff if the time comes. You know what I mean? Okay, here we go. Antennas, antennas, antennas. No radio will work without an antenna. So antennas are one of my favorite things, and they're a lot of fun to play with. And it's actually one of the areas, it's hard to build a radio. It's really easy to build an antenna. Now, it's not necessarily easy to build a good antenna, but it can be. Okay, a simple dipole. All right. Now, what we're going to draw is this. That is an antenna. It's split in the center. We're feeding a quarter wavelength of each side. That's how long each side is. So this overall is a half wavelength long. Now, why is this such a magical antenna? The reason it's such a magical antenna is because we're going to look at each piece of wire here and ask a very important question. And I want somebody to answer. What is the current through a piece of wire at the end of the wire? What is the current at the end of a wire? It is not the same as it was at the beginning.
I'm just gonna guess in a perfect world, in this case, all the energy would be going through the antenna. So hopefully all that energy's out.
Nope.
So the current would be zero? No? Okay.
Oh yeah. Good. Well, but think about why. If current flows in, it has to flow out somewhere, right? If there's any current going that way, it has to be matched by current going that way because it's at the end. And if it's at the end, it doesn't have anywhere to go. The current at the end of an antenna or any piece of wire has to be nothing. So the easy way to start with this is that now we're going to draw waves. All right. How long is this entire antenna?
Half wave?
A half a wave. What does a half a wave look like if a whole wave looks like this? And you know that it has to be zero at both ends because we just said so. Has to look like that. That is what our current distribution on our wire has to look like because physics says so. Okay, so now empirically, and we're not going to use resistance now, we're going to do Ohm's law, E equals IR. But because we're not really working with resistance, we're going to use impedance, which is Z. E is equal to I times Z. So now we're going to rearrange that. Z is equal to E divided by I. So now we're going to look at this empirically. What is the current right here? What did we just say it was?
Zero.
Zero. What's the current over here?
Zero.
Also zero.
Zero. If we tried to push power into that point and our I is zero, what is something, a number, divided by zero? What is
Zero.
anything divided by zero?
It's always zero.
It's not zero.
Infinity.
Infinity. In other words, we would have a really, really, really big impedance where we're trying to stuff power into. What happens if you try to stuff power into something that's not going to accept it? You won't get any power into it. So that is a non-starter. It's very, very difficult to do unless you have a transformer that matches you for a really high impedance. This is actually an antenna known as an N-fed half wave, which is actually very popular now, but requires a very high impedance match. So what it turns out is that the closer we get to the center of a half wave antenna, the higher the current becomes, the easier it is to stuff power into. And as it turns out, the impedance of a half wave dipole is about equal to 70 ohms. Well, this is actually quite usable. Remember, we said that we use typically radios that have an impedance that they're looking for of about 50 ohms. Most cable that's out there is 50 ohm cable, and the antenna is about 70 ohms. That's actually not bad. We can actually do this quite well. That's actually a fairly good match. There's a little power going up and down a few times, but it's not overly bad, and it's a really simple antenna. A half wave dipole is therefore the most common antenna that you will find because it's really, really easy to make, and it's really easy to feed power into. If it's a horizontally stretched out antenna, it's a horizontally polarized antenna. Now, another thing about this antenna is that if we were to look at this antenna from the end, it looks like this. Does everyone agree with that? If we take this antenna and we turn it sideways, looking at it from this point of view, it just looks like a dot. Everyone agree with that?
Yes.
Okay. So is any direction more important than any other direction if something's just a dot? Is there any difference between up and down or right or left?
No, because it's looking in all directions equally, right?
That's right. Okay. So a dipole transmits a signal in every direction equally, but looking at it from the end, which means that if it's a horizontal antenna, some of it goes straight into the ground and some of it goes straight into the air. Some of it goes this way and some of it goes this way. As it turns out, if we then rotate this antenna so that we're looking at it this way, it actually radiates energy kind of in the shape of a donut. And it's strongest away from the axis of the antenna. In fact, there's virtually no energy that's radiated along the wire. It's all perpendicular to the wire or very close to it. So it kind of makes a shape of a figure 8 of the radiation pattern around the antenna. What that also means is that a dipole is actually a directional antenna. So if I were to draw this antenna so that if I was looking at it from above, and this is north, and this is south, this is east, and this is west, where would most of my power be going? Which directions? Remembering that a dipole makes basically a figure 8 pattern perpendicular to the wire.
North and south.
North and south. So if my wire is east-west, my main pattern goes north and south. Most of my energy goes that way. If I were to rotate this antenna and make it so that my wire now was going this way, where this is north and south, I would find that my pattern would look like this. So what have I now done by rotating my antenna?
You shifted where your power now.
Yeah, I shifted the receive pattern and the transmit pattern. just by rotating it. So actually a rotatable dipole, which is easier said than done for low frequencies, because that's a big antenna, can actually be a very powerful thing. Now, because at certain frequencies, let's say, all right, so now we're going to do a little math, and we're going to make an antenna. And this is one of the antennas that I have. I have a 40-meter half wave. Okay, so here's our calculation: 300 F and lambda. Okay, so we're going to look back and see that on the frequency chart, 40 meters, we're going to pick 7.2 megahertz. 7.2 megahertz is in the 40-meter band. So we need to know how long a wavelength is. 300 divided by 7.2 is, anyone have that handy? See who gets there first. I get 41.6 meters, 41.7 meters long. Okay, I'm going to divide that by 2 because I need a half wave antenna. 20.83 meters. Okay, well, now what I have to do is that if I were to make this antenna, it turns out that it would be too long, because the real world requires a reduction in length of about 5%. So this is very important when you're figuring out an antenna. You want 95% of what you just calculated. And I get 19.79 meters, and then multiply it by 3.3 to get feet. 65.3 feet long. Okay, now, seeing as though my antenna has to be 65 feet long, and each one of the legs has to be, 32 foot, let's see, 32 foot 8. How am I going to rotate that? Anyone have any ideas?
You could go vertical or across the ground.
Yeah. Or I could use another one and just make it like that and have 2 of them and switch between the 2. And in fact, that's what I do. I have 2 of them at right angles to each other. And I have 2 separate antennas, and I have 2 separate tuners, and I just switch back and forth. Whenever the signal gets louder, I know I'm on the right one.
I need to have a large backyard for this.
Well, you don't actually. Nah, we're getting to that. We're getting to that. Okay, when putting up a dipole antenna, you should consider the orientation because it radiates better in some directions than others, which we just showed. Okay, so we're going to do a 6-meter dipole. 6-meter dipole. Okay, who wants to go through and do these calculations? Somebody please say yes.
Why not?
Okay, why not? Ready? Okay, so we're going to do it on 6 meters. We're going to pick 50 megahertz. We're going to make that easy. Okay, so the formula for doing it, 300 F lambda to figure out the wavelength. All right, so we have lambda is equal to 60 divided by 300, or sorry, 300 divided by 60 is, sorry, 50. Yeah. 300 divided by 50, Haley May.
6.
6 meters. Okay. All right. 6 meters times 50%. So a half, because it's got to be a half wave. That would be 3 meters, right? Okay. And then multiply that by 3.3 to get feet. I hope it's 9.9. Is that right?
Yeah.
Okay. Now we only need 95% of that. So we're going to actually take this and convert this to inches first. So that's like 100 and let's see, 108 plus, it's about 118 inches. Now, but we only need 95% of it. So 118 times 0.95. What do you get? Somebody, what'd you get?
112.86, just over 10 feet.
Let's go with 112 inches. And according to the book, the approximate length of a 6-meter half-wave dipole is 112 inches. So congratulations, we've just built our first functioning antenna.
Hey, Scott, what's the reason for the 95%?
It's because of capacitance. It's because of the fact that it's not a perfect conductor. It's got some inductance. It's got a finite thickness. So it effectively, the fudge factor is about 5%. Now, if you start looking at, okay, well, this is actually the next question. What happens how do you increase the frequency of an antenna? What would you do to it to increase the frequency that it works on?
Would you make it shorter?
You'd make it shorter. Okay. So let's say that I made my antenna and I found that here's my SWR plot, which is standing wave ratio. And it went down and back up. And I found that this was resonant at 48 megahertz. My antenna is too long or too short?
Too long?
Too long. That's a good thing. Why is that a good thing?
You can always make it shorter.
You can always make it shorter. Now, if I were to do it again, and I'd say, I found that it was resonant at 56 megahertz and the band ends at 54, would I have to make it longer or shorter?
Longer.
I'd have to make it longer. Well, at that point, I already cut too much off, which basically means that I'm starting over. So it's always a better idea to make your antenna a little too long and nip a little bit off at a time.
Measure twice, cut once, right?
Well, measure twice, cut once, and then make it too long on purpose. All right, here's the next one. A quarter wave antenna. How many waves long is a quarter wave antenna? I just gave you the answer.
Quarter.
A quarter wave. Okay, right. But now, will a quarter wave antenna work by itself? The answer is no, it will not, because a quarter wave antenna is a special case of, what is this antenna called? Remember this whole thing? We just built one.
A dipole.
A dipole, a half wave dipole. A quarter wave vertical antenna is a half wave dipole missing the bottom part. So to understand why this can work at all, what we're going to do is I'm going to turn off the light and I've got a reflective surface and hopefully this trick works. Okay, I've got a plate which is reflective. Can everybody see the reflection of the light in the plate?
Yes.
Okay. Did I just lose my camera there? No? Okay. All right. So there's my plate. Notice. Now, let us say that you could not see and did not know that there was a plate there. How many lights would you see? If you didn't know that was a plate, how many lights do you see?
Two.
You see two lights. Okay, good. Because how many lights are there really? There's only one. But as far as you are concerned, there are two. Well, so as far as the rest of the world is concerned, the outside world, that must be a dipole. So really what we're doing is we're taking a quarter wave antenna. Oops, that was terrible. And we're putting it over a reflective surface, which basically makes it look like the rest of the antenna is down there. To the outside world, what you see is this half and this half. And as far as you know, that's a dipole. So everything's fine. The way that we're doing this, of course, is that this is being reflected down to here and then back up. But again, you don't really care. So the way to achieve this is that we then take our half wave to our quarter wave vertical and we stick it over an electrically conductive surface to make it basically image that antenna in the reflective area, in the reflective surface. This is usually something like a car roof. So, or it could also be the ocean. Nice conductive surface. Now, this can actually be, as we feed it, the center part goes to here and the bottom part can drop it in the ocean, or it can just be right here inside a magnet. Now, how in the world could that possibly work? Without putting a hole in the roof of your car, how can this possibly work? This is where we get into another little trick of the math that we're doing. So here's the base of an antenna. Here's the center going out, and here's the bottom part. It connects to a plate. Well, what do you guys see? Notice I said it connects to a plate.
I see a capacitor.
That's a capacitor. That's right. That is a capacitor. And a capacitor at AC looks like a short circuit. So what's happening is that the capacitor is coupling through capacitive coupling to the roof of the car. And it's making the roof of the car look like it's connected. Pretty cool, right? That's how a magnetic mount antenna actually works. Okay, the approximate length of a quarter wave vertical antenna. I have one of these on the roof of my house. It's a 19-inch antenna. It's at 146 megahertz. That's only half of it, though. The rest of it looks like this. These are each about 20 inches long. These are known as radials. And if you take an antenna that has radials that are perpendicular and you feed it right here, at this point, you get about 35 ohms. Remember, a dipole was about 70 ohms. You get half the impedance because there's really only half an antenna. If you take it and bend the radials down and feed it right here, you get about 50 ohms. I built one of these for $5. The most expensive part was the PVC holding it all up. You can build a functioning antenna. It's been on my roof for 7 years now. It cost me a total of $5 to make. Okay, antenna loading. Very important concept. So if I were to tell you that a quarter wave antenna had to be 19 inches long for 2 meters, which it does, that's a quarter wave antenna. Now, if I were to tell you this is a quarter wave antenna at 2 meters, what would you say? Everybody see this really short, stubby antenna?
I see it.
All right. So what's the problem with this antenna? This
Too short.
This is actually 19 inches long. This is actually 19 inches long.
And probably you did some tricks with math and.
Nope. It looks like
Just
this
'cause
on the
it's pulled
inside.
up.
Because it's coiled, so it's
It's
it
a
has the
total
longer
of 19
length,
inches
but
of wire.
yeah, it's just coiled up.
Yep. But it's physically only 7 inches long. It's 19 inches of wire and it's coiled up in a 7-inch space. So what do you think happens to my signal when it gets into this part of the antenna?
It's compromised.
Terribly compromised. Because
Distortion.
for every section I have going that way that generates a magnetic field going this way, when it flips around, it generates a magnetic field going the other way. Those cancel each other. The next coil, it does the same. Effectively, it largely cancels out its signal. And really the only functioning part, there's a little bit coming out of the base, but really the only functioning part is way up here. Now, this might only be 4 inches long. If I were to draw this whole antenna from bottom to top, this is what my current distribution should look like. It's a 1/4 wavelength long. But this whole section, the bottom 15 inches, is all scrunched up into a space like this. So basically my current looks like this. But this whole section here is all scrunched up. So it's really doing nothing. So basically my antenna is greatly compromised. However, now we're going to look at something that I would call system design and understand why for a lot of instances, this is perfectly okay. So let's say that I have a repeater on top of a mountain or on top of a building or on top of something. So here's my tower, here's my antenna here's my antenna up top. And here is me on the ground with my antenna on my radio. Here is somebody else on the ground with the exact same radio, but with a real antenna. So let's say that to get from here up on top down to here, because the signal has to go out in all directions, it starts out with 1 watt. And the path loss to get from here down to there is 120 dB. We lose 120 decibels of signal strength just because it has to be distributed and it goes through the air and it hits things. And okay, so now let us say that on the ground, our radios have to have a minimum signal of minus 130 dB. Well, 120 is still above minus 130. Minus 120 is still above minus 130, right? And everything's fine. Let's say that this antenna has a gain of 0 decibels. It's not a good antenna, but it's not bad either. This one has a gain of minus 5 dB. So the signal that's getting into here is minus 120. And the signal that's getting into here is minus 125. Well, it's still better than the radio needs, right? Which means that even with the compromised antenna, it's absolutely fine. But now let's take those same people, and we're going to move the repeater much further away. And our path loss goes from minus 120 to minus 128. Right? And nobody's changing antennas. So this person, negative 128 dB, minus 0 is minus 128. The receiver needs at least minus 130, so this guy's fine. This one is minus 128 minus 5 is minus 133. And it needs at least minus 130. So what happens to the guy with the short antenna? He doesn't pick up the signal. Conversely, depending on what they're doing, he also can't be heard because his signal is now attenuated and now too weak to get back to the repeater, which basically means that even though they're in the same physical location, the antenna gain that's being used now makes a difference. So for like, I remember there was a company that made an antenna that was 2 inches long for 2 meters. If you were sitting right under the repeater, it was just fine. It worked fine. You know, it was a perfect match for the antenna, for the radio. It didn't care, but it had a lot of loss, but sometimes that doesn't matter. Okay, so now we're into beam antennas. So
I have a question.
Yeah, sure.
So let's say you have like a quarter wavelength antenna. So it's a quarter wavelength for a specific wavelength
Yes.
of signal, but then it could also be a half length for a different frequency, right? So how do you pick up the specific one you're looking for?
Well, that is a good question. So what we're going to here. So let's say that we have a quarter wavelength, or sorry, let's say we have a half wave. Well, yeah, let's make it a half wave on 40 meters. Well, so we can draw our waves and it looks like this. All right, so now we can also draw on 20 meters. It'll look like this. I mean, we can use the same wire, but now it looks like that. And we can also use it on 15 meters and it'll actually look like this. So you can see that for some of those frequencies, it's suitable and others it's not. Agreed?
Which ones are unsuitable?
Well, I mean, we're feeding it on 20 meters. Where are we feeding it? Right at the center. And what's our current at the center?
Oh, 0. Okay.
It's 0. So we're going to have a hard time unless we have an impedance matching network feeding power into that, which is why having antennas that work for multiple different bands can sometimes be tricky. The other thing is, if you have, let's say that quarter wave antenna. So let's say this is 19 inches long with radials. Well, it turns out that is a quarter wave on 2 meters. So let's also go to 70 centimeters. It actually, because 144 to 432 is 3 times, the wavelength is 3 times as short. Well, so this is actually 3/4 waves, which means it actually looks like this. And guess what? That's actually a good match. Now, what you'll also find is that that does not have a dipole pattern. The more waves you have on a piece of wire, the more interesting the pattern looks. It's no longer necessarily a dipole. Like this is a half wave dipole and this is a half wave dipole, and they're now fed out of phase with each other. And so you have all kinds of cancellations. And if you start having even longer antennas, what you end up with is something that has a lot of you end up with something that has a lot of nodes and a lot of what's the word I'm thinking at? I'll think of it. But basically you end up with a pattern that kind of looks like a multi-leaf clover. It's no longer, solely directional in this direction and this direction. Lobes. You start to develop multiple lobes, the more waves you get long.
But can you really like control how that, because that's like inherent to just the size of it. So how do you like control for that?
Well, one thing you can do is, you can pick the frequency you're operating on. You can also electrically disconnect something. You can, you throw a switch somewhere. Let's say you have an antenna that's out on, hanging in a tree or something, or a vertical, and you can have an RF switch out there, and you can open or close the switch, and that brings a section of antenna in. In fact, one of the things that we often do is we have, picture this. All right, good with that so far? Just looks like a coil of wire with a whip on top, right?
Yep.
Okay, so now what we're going to do is we're going to take the whip and we're going to split it right here. So we have a fixed point. And this fixed point is now going to be disconnected from that. What we're going to do then is take this and we're going to connect this to a set of wipers. And that is then connected to the whip. And what we can then do is connect this center section right here to a jack screw. All right. That's connected to a jack screw that runs up and down the center. And so by doing that, we can raise and lower this entire thing and and allow, like, for instance, I guess we have to do this. We have to raise it up. Here's our, whoops, here's our jack screw. And it's now connecting to here, and the antenna starts again up there. And our jack screw now goes up to here. So now what have we done with our antenna? We have made it electrically longer by adding this section of coil. This is actually known as a screwdriver antenna. And because we have a couple of shorting elements, this actually allows us to tune the length of the coil that is now part of the antenna, thereby electrically changing the length of the antenna.
Gotcha. Yeah,
Does that
thanks
answer?
for cleaning that up. Yeah, it makes more sense now.
All right, any other questions before we go on? Like I said, antennas are the most fun because there's so many ways to do it. A beam antenna. A beam antenna is an antenna that concentrates its signal in one direction. Let's make our dipole again. So a dipole has a signal that's perpendicular. So it goes this way and this way. Now, one thing we can do with this dipole is that we can put a longer element over here, which is known as a reflector, and another element over here, which is shorter, and that's called a director. These are not electrically connected to anything, but they exist in the electric and magnetic fields that are generated. And this one kind of acts like a backstop, and the director sort of acts like a funnel. And what you end up with when you do something like this is a signal that now looks like this, where you have less signal going backward and more signal going forward. And this is known as a beam antenna. And in fact, this is known as a Yagi, but it doesn't have to be a Yagi, but this is the most common one out there. And we measure the amount of improvement of this antenna. We use something called gain. And what do you think we measure that gain in, everybody? Yeah, measured in decibels. Yep. All the gain is measured in decibels. So basically it's the improvement of one antenna over another. Now we can also measure something called front to back gain or front to back ratio. So we measure how much signal come out here, how much signal comes out here. That basically tells us how much directionality we have. That's also measured in decibels. Antenna gain is the increase in signal strength in a specified direction compared to a reference antenna. So this would usually be compared to a dipole antenna, which is known as DBD. Again, there's something that uses something called an isotropic radiator, which is an antenna that transmits in all directions in a spherical, in a sphere equally well, which is an imaginary antenna. If we compare something to that, it's called DBI or DB isotropic. This number, dBi, is always going to be 2.15 dB better than the dBd. dBd is compared to a real antenna. They mean the exact same thing. So if I had an antenna that was 7 dBd, it would also be 9.1 dBi. It's just kind of like a, no, again, isotropic radiator doesn't exist. It's just something that some people use. What provides the greatest gain? Some different antennas. Yagis are great at providing gain. You can also do an antenna that looks like this. And that's known as a dish. Dish antennas are great for providing gain. You can provide, 30 decibels of gain in the forward direction using a dish antenna. Most handheld transceivers come with an antenna called a rubber ducky antenna. The rubber duck antenna has very low efficiency. Again, that's what you get on your typical handheld radio, known as a rubber duck. Disadvantage of using a handheld transceiver with a flexible antenna inside your car is that your car acts as a Faraday cage and shields the signals going out of the car. A 5/8 wave antenna can work very similar to a quarter wave antenna. Here'd be a quarter wave antenna, and here's a 5/8 wave antenna on the roof of your car. A 5/8 wave antenna might have a pattern that looks like that. A quarter wave might have an antenna pattern that looks like that. A 5/8 wave might have an antenna pattern that looks like that. And since most of the people you're trying to talk to are along the ground, it's a better antenna for mobile operating. Now, what's the disadvantage of that? A quarter wave antenna is how tall? 19 inches. A 5/8 wave antenna is about 45 inches long, which means that if you happen to park in a parking garage, you're always going to hit the 5/8 wave antenna on the door. And you're probably going to want to take it down. So that's why I have a quarter wave on my car. Feed lines and connectors. All right, any questions on antennas before we go to feed lines? Anyone? No questions.
Could you clarify what a Yagi is? Because you said it's like a beam antenna, but not all of them are.
Well, not every beam is a Yagi, but every Yagi is a beam. I mean, a Yagi antenna looks like this. And a Yagi is specifically, it has a driven element and a reflector and director or directors. And that can be any number of them. And they're mathematically spaced, and they're mathematically proportional in length to each other. So this would be a Yagi style beam. Now you can also have a directional antenna that looks similar, but actually that looks like this. There you go, Pat. There's your LP. So this is something that's called a log periodic. The way a log periodic works is that these are all dipoles, and you basically connect all the elements. They're all driven, and they're all logarithmically proportional to each other. And essentially, because there's such a wide range, at any given frequency that you pick, you'll have 2 or 3 elements that are in play, and the others won't even be there. They'll act like they don't exist. So this is a very wide range. This, again, notice an LP or log periodic. And when you feed it, you feed them all from a common feed point, and they're all driven. And again, because they vary so much in length, at any given frequency, let's say only those 3 are active, or only those 3 are active, or only those 3 are active. So it's sort of like a self-selecting thing. But because there are only 3 elements active, you only get a certain amount of gain. This might be, 6 dB, but of a range of frequencies from 100 to 900 megahertz, which is, something that's almost unheard of. A Yagi will never do this. A Yagi with as many elements might provide, let's say, 17 dB of gain, but only from 140 to 160 megahertz. It's much tighter bandwidth. That makes sense?
So an LP is different from a Yagi.
Oh, totally different. Yeah, the design and construction are completely different. So a log periodic, actually, have you ever seen an old school TV antenna?
Yes.
Okay, because television, channel 2 was down at 54 megahertz, and they were supposed to operate from, your log periodic antenna was supposed to operate all the way up to the top end of UHF, which is about 800 megahertz. So a single antenna to operate from like 54 to 800 megahertz with some gain. So it could be turned. So you could actually point it at the, at the station you were trying to receive. That's not a Yagi. But because it didn't have to handle any power because it was a receiving antenna only, that wasn't really a concern. So it didn't have to be made that expensively either. And they worked really well for that. All right, feed lines and connect. Any other questions? Okay. Now, next we go into feed lines, because now that we've talked about antennas, we have to talk about how to actually feed power into it. Okay. Can everybody see that picture?
I see it.
Yes, sir.
Okay. So notice we have 2 different feed lines. Now, what I'm going to say might sound a little weird, but both of those antennas are both of those cables are 50 ohm cables. And you say, how can that possibly be? Okay, so when we talk about feed lines, okay, so we have our transmitter, which is going to have an output connector, which is going to be 50 ohms. Internally, it's looking for 50 ohms. The antenna is going to have an impedance, hopefully, of 50 ohms. We are trying to connect these 2 things with cable that has a characteristic impedance of 50 ohms. It's not actual impedance. It's a characteristic impedance. It's basically an intrinsic property of the cable. It's not supposed to, the antenna uses power. The transmitter makes power. The cable is just supposed to move power from place to place. It's kind of a different thing altogether. So if we were to look at this, we can model a cable. Let's look at a piece of coaxial cable. If you have cable TV, you've seen this before. It looks like that. And then you have a cable coming out of the center and another one coming out here. Right? It's basically a tunnel. Well, you have a spacing that's usually filled with like polyethylene or something. And then you have a center conductor, which has a diameter, and the whole thing has an overall diameter. And because of the space between this conductor and this conductor, the center to the outside, that's a capacitor. Does everyone agree with that? You basically have, looking at it from the end, you have an outer conductor and an inner conductor, two conductors separated by space. That's a capacitor, right? And then you have length, and you have a piece of wire, and you also have an outside shield. Every wire has inductance. So basically, this can be modeled like something like this. an endless string of capacitors and inductors that goes on forever. And because if they're ideal, neither of them actually uses any power. They just have something on the outside. This would be 50 ohms. And each of these sections would basically make it look like to the outside world. Yeah, I drew one too many. Get rid of that one. Get rid of that one. That section and that section and that section and that section. And each of these basically looks like a full network to the outside world. Let's draw another inductor. It's just a repeating string of things. And as you model these, basically it shouldn't use any power, and it has a certain impedance that's defined by the components that you modeled it as, which are actually defined by part of what defines a capacitor is the size and the diameter and the spacing of what's inside. Part of the inductance is the thickness of the wire and the overall amount of shielding that you have. Those determine the inductance. So because of that, so long as I have something that looks like this, I can draw another one. So long as it's exactly proportional, it has the exact same impedance, characteristic impedance. This could be a 50 ohm cable, and this could also be a 50 ohm cable. So how would they be different? From that point, let's go back to this picture. Notice that they're totally different sizes, right? But they're proportional to each other. So in what ways do those two big cables differ?
Would they differ in length?
No, the length is exactly the same.
Oh, interesting.
Greater amount of loss in the thinner cable.
More loss in the thinner cable. Yeah, what else?
One has more insulation than the other.
Yeah. But again, they're proportional. So they're both 50 ohms. But what other impacts would you see when it relates to more loss? It's kind of a double whammy, because if it has more loss, what does loss do?
More heat.
More heat, but it's smaller to begin with, right? So for the same amount of power, it generates more heat and is actually smaller also. So what'll happen to it? In other words, let's say they generate the same amount of power, right? The same amount of heat. Which one's going to get hotter?
The smaller one.
The smaller one. And it's lossier to begin with, which means it actually makes more heat for the same amount of power. Which means that not only is it going to get hotter, it's going to get hotter faster, which means that you can't run as much power through it. So the one on the left, you might be able to run 1,000 watts all day long. And the other one, you might be able to run 100 watts all day long. It also means that the worse your match, the worse the cable on the right is going to perform because it's got more loss. You know, the one on the left is more forgiving. So now let's look at this one. Let's look at like RG174. Here we go. Notice RG174, the loss per 100 feet at 100 megahertz is 8 decibels. That's almost 10 times, that's almost 90% of your power. Why would you ever use that? That's a real question. Why would you ever use that? It's only 2/10 of an inch across. Why would you ever use it?
On a budget.
Yeah, but you'd end up replacing it. Why would
Short
you?
connections, low power.
Short connections, low power. Let's say you're building a satellite and you only need 4 inches of cable, and the signal that you're connecting is only on the order of 10 milliwatts, right? So you put 10 milliwatts in, you get 9 milliwatts out. Who cares? It's still 50 ohms. It's only, it's only 4 inches of cable. Everybody's happy. But if you took 100 feet of it and you put 100 watts into it, if it didn't melt, you'd get, a quarter of a watt out or something by the time it was all done. And at that point, why are you even bothering to do it? You're putting out no power at all. So there's a lot to be said for choosing cables and choosing connectors. Okay, let's see. Why do people use coaxial cable compared to any other feed line like parallel line? And that's because it's really easy to deal with. You can bury it, you can slam it in your car door, and it'll be just fine. Impedance is the opposition to AC current flow. And by the way, we're on page 54. The unit of impedance, confusingly, is also ohms, just like resistance. They're both measured in ohms, and they are somewhat related. The most common impedance of coaxial cable is how many ohms, everybody?
50.
50, yes. Okay, what happens as the frequency of a signal in cable goes up? What happens to the cable loss? Gets worse and worse and worse. Your loss gets worse and worse. You can go to one of these cable attenuation charts. There you go. As your frequency goes up, your attenuation gets worse and worse and worse. Independent of the cable. It's just a function of cable. Certain cables are better than others, but it always gets worse and worse. The difference between RG58 and 213, that was that picture that we just saw. What's the difference between 58 and 213? 58 is the small stuff and 213 is the big stuff. Why would you pick one over the other?
The 213 suffers less loss.
Yep. And it's also going to have a higher power handling capacity. So, but yeah, the big one is that it's got less loss. Following types, which are the types of feed lines that have low loss at VHF and UHF? That would be air insulated hard line. So I'm going to show you a picture of hard line. This is what hard line looks like. Okay, so this is 1/2 inch hard line. And eventually. That's Andrew Heliak's. And notice it's basically spiral wound copper. $3.25 a foot. And that's for 1/2 inch 50 ohm. So what are some of the disadvantages of working with this? What do you think?
It's probably way more
Pricey.
fragile. Like
Yeah, a lot more expensive. What else? What else?
Probably just more fragile. Like
Actually,
if you move
it's
it
really
or bend
rugged.
it.
It's actually really rugged.
Okay.
But it also weighs a ton. And they say it's flexible. It's not flexible. We once put up a run of 1.5 inch hard line at a repeater site when I was in school. If you're at the University of Maryland and the repeater's still there, I believe it's still up there. I think we got 200 feet of it. You cut it with a hacksaw. The connectors are really expensive. And on top of that, the 200 feet came on an 8-foot spool. That's as tight as you could bend it. So very low loss and very, very hard to work with. Which of the following is a source of loss in coaxial feed line? Water intrusion, high SWR, or multiple connectors. Every time you put a connector in a line, you run the risk of basically having an impedance bump or loss, which causes loss of signal. Moisture contamination causes most cables to fail. That is the mode of failure for most cables. If you're going to solder a connector onto a cable, you got to waterproof the heck out of it. Because
there is a question about SWR, the meaning of signal to wave ratio.
Standing wave ratio.
Oh, yeah, thank you. I just couldn't remember the acronym. Thank you.
Okay. Yep, standing wave ratio. That's basically a measure of how much signal is going out compared to the signal going in. How much of it bounces back. And there's actually a formula for SWR based on a coefficient called gamma, which we can look up in a little bit. Why should the coaxial cable jacket be resistant to ultraviolet light? If you have it outside and it's not ultraviolet resistant, the sun will crack it. As soon as the sun cracks it, it gets water in it. As soon as you get water in it, you might as well just throw it away. A PL259, that is the most common RF connector. This is what a PL259 looks like. It is very, very commonplace. I have dozens of them in use. I have dozens of them that haven't even been soldered yet. The great thing about PL259s is that they mate to most radios that are out there. However, above VHF, they really are not very good. And to be totally honest, notice that this says UHF male. Don't fall into the trap. UHF does not pertain to ultra high frequency. A UHF connector means universal high frequency. It came about a long, long time ago. And just because people could be confused, that's, I'm sure, why they did it. So this is known as a UHF or PL259 connector, and they're not good at UHF. Now, what is good for use at UHF come on, is an N connector. These are great for use at up to like a gigahertz plus. So N connectors are greatly preferred. All right, what can cause erratic changes in standing wave ratio? SWR is very often a result, high SWR is very often a result of a loose connection in the feed line. If everything's not snugged down, if you've got, some water in the feed line, you can have a problem with that. All right, the next section is standing wave ratio. Standing wave ratio is a measure of how well or poorly matched something is. And standing wave ratio, here we go. Knew I'd find it, didn't take very long. There is the formula for standing wave ratio. Everybody see that?
I see it.
1 plus square root of power reverse over power forward divided by 1 minus square root of power reverse over power forward. So if you have no reverse power, your standing wave ratio is 1. It's usually displayed as something to 1 because it's a ratio. So you'll typically see a perfect SWR is 1 to 1. It's a measure of how well a load is matched to a transmission line. It's essentially looking to see how much reflected power there is coming back off of something. Again, a 1 to 1 is a perfect match. 4 to 1 is a serious impedance mismatch. A benefit of low SWR, because the higher the SWR you have, the more reflected signal there is, the more times it has to travel up and down the feed line, the more power gets lost. What happens to power loss in a feed line? Power lost anywhere turns into heat, sometimes flames. Why do most solid state transmitters reduce output power as SWR gets up to a certain level? as we looked at before, when the power, when the voltage coming back gets too high and it combines with the voltage going out, you can basically blow up your transistors by putting over voltage on them. So it's to protect the output amplifier transistors. What should be considered when selecting an accessory SWR meter? Not all SWR meters are as accurate as others. You also need to know what frequency they work for. I have an SWR meter in my station that's good up to about 160 megahertz. And I've tested it and it does seem to work at that range. However, I have another one that doesn't work very well above 30 megahertz. And that's just because it wasn't designed for that. Also, some SWR, some meters, watt meters, power meters, SWR meters, they're designed to operate on, let's say, 200 watts max. Some people run linear amplifiers. If you try to run a linear amplifier through that, you will cause something in there to melt, undoubtedly. What instrument can be used to determine SWR? That's known as a directional watt meter. And in fact, virtually every SWR meter has a pair of directional watt meters in them. So let's look at SWR meter schematic. I'm sure I can find one. Here we go. Okay, so notice we're measuring forward and reflected power, and we're using them. We have a diode, and then the diode is driving our forward and reflected power. So that's not actually computing the SWR. It's just, there we go. Ugly construction, but it works with a pair of meters. Now, if we wanted to have something that was even a little more interesting, we could look at something like an N7JI 949E. And the meter looks like this. So notice the meter, and it has 2 meters built into one. It actually has on the left-hand side, that meter is forward power, and on the right-hand side is reflected power. And the curves in the center basically are doing the calculation of that 1 over the square root of reverse over forward divided by 1 minus the square root of reverse over forward. So those lines are basically the calculator. By looking at those lines, that determines what your SWR is. Obviously, you want the reflected power as close to 0 as you can. That's where the 1-to-1 line is, all the way on the right. Where should an RF power meter be installed? That would be in the feed line between the transmitter and the antenna. And what we're going to do is just show you where to do that. So here's the transmitter, and here's the antenna. You want the SWR meter way down here. So it's really seeing what's happening in the outside world. Now, let's say you have an antenna tuner built in. You would tip it, or that you're using. The matching network would be right here. And then you would use the SWR meter to adjust the antenna tuner. So here's a good question. If I make it so that I've adjusted my tuner so that the transmitter is happy, if I had a 5-to-1 mismatch out here before I put in the tuner, what is my mismatch out here now?
It's still the same.
It's still the same. It's still a 5-to-1 mismatch. You still have a problem, but the transmitter doesn't have a problem. You can still put power into the system, whereas you couldn't before. So it doesn't solve all your problems. Which of the following is used to determine if an antenna is resonant at the desired operating frequency? So you could transmit into your antenna and see what the SWR was. Or you could do this. and you could use something called an antenna analyzer. What an antenna analyzer does is that it's a very, very low power, unlicensed transmitter. It puts out like a milliwatt or something. And in doing so, it allows you to sweep through frequencies that you as a ham are not allowed to use because the power is so low. And it shows you what the SWR is at each of those points. There are also antenna analyzers out there that will automatically sweep a range and print out a graph for you. So for instance, something that looks like that.
So you're saying it helps to sweep through frequencies that as hams we are not allowed to use? Is that
Well,
what's-
yeah. And here, like, here's a picture of, you notice what, shoot, where'd it go? I lost it. There we go. You notice that curve on the right?
Yes.
Okay, so let's say that what you have looks like this. You measured in the ham band, you measured SWR that went like this. So here's the range you're looking at. And it should be 1-to-1, but, and let's say this is like infinity. And it was like here. The question is, you know that your antenna is resonant somewhere. Which side is it on? It's like, you know, it could be here or it could be here, but you're blind to that without knowing. You don't know. I mean, it could be that your antenna's resonant right here, in which case it's just a little bit too, it's a little too long. So this is infinity and zero frequency. But you would never know that unless you could sweep outside. Fortunately, most hams or many hams who build their own antennas have antenna analyzers for doing just this. Because it's actually very instructive to know, for instance, that if you went and grabbed your analyzer, it would do something like this. And okay, there's the dip that I'm looking for. Or you run it again and you say, okay, the dip was actually over there. What you would do with it is completely different at that point. You know, the decision that you would make regarding what to do. The purpose of a dummy load is to prevent transmitting signals over the air when making a test. A dummy load consists of a non-inductive wire wound resistor and a heatsink. And the reason it's non-inductive is because an antenna ideally is going to have exactly 50 ohms. Now, it's a good time to discuss this. So here's resistance and here's reactance. They are perpendicular to each other. So if I have 50 ohms resistance and plus 50 ohms reactance, I would actually get 71 ohms. That would be the measurement that I would get. Because it's actually the square root using the Pythagorean theorem of 50 squared plus 50 squared. Now, it's also important to know that not only that, I have an angle of 45 degrees, which means that it turns out that this is the positive side and this is the negative side. So this is inductive and this is capacitive. So I would need to know, if that was the case, that I had to add capacitive reactance to bring it back down, which means I really need to use a capacitor in my circuit. This is actually really important to know. That's why up here is very different from down here. But they're both 71 ohms, except that this is at a minus 45 degree angle, which is a completely different thing. So if I were to do this and I had an inductor, well, let's say I had a classic wire wound resistor, which looks like this. It's basically a resistor in a block of ceramic. Why would I not want to use that, even if it said 50 ohms? It might be 50 ohms resistive, but what does that also look like? everybody. What does that thing look like? It look like a coil in a box?
It does.
Okay, what's a coil? A coil's an inductor. Well, that means that what used to be 50 ohms is not going to be 50 ohms anymore. It's going to have inductive reactance, which means that its reactance, that its overall impedance is going to be somewhere up here. Is that 50 ohms anymore? No. It's 71 ohms. If it's 71 ohms, how good of a test instrument is it for me? Because every time I change the frequency, the value changes because the impedance of an inductor changes with frequency. So at low frequency, it might be here. At high frequency, it might be up here. So it'll go from 55 ohms to 71 to 90. If I'm trying to tune a radio, if I'm trying to tune a transmitter that's looking for a 50 ohm impedance, that's no use at all. And that's why we don't use a wire wound resistor. We call it a non-inductive wire wound resistor. Okay, so now we are up to modulation techniques. And here we go, modulation. All right, I think this is going to be the last thing that we do today. Any questions before we do it?
I did have a question about antennas
Yeah,
regarding the SWR.
please.
Okay, so SWR, is it, how much is it affected in the receiving portion, or is it more in the transmitting portion?
Well, I mean, if you have, I mean, SWR is SWR. It's just indicative of a match. It's not going to hurt your ability to receive that much. But I mean, you'll still, you know, when you're perfectly matched, your receiver will be optimized also.
Oh, for both transmitting and
Yeah.
receiving?
Yeah.
Okay, okay, gotcha.
Anything else before we go? All right. So now what we're going to talk about is taking a wave. This is what we would think of as a carrier wave and doing something with it, making it more useful to us. How much information is on this? If it never changes, we just know that this is a frequency of F. How much information is carried here? Other than the fact that there's a frequency there, is there anything that's telling you that there's something else useful about it?
No information.
Nothing. There's nothing useful. Now, what if we were to take this signal and do this with it? How about that? What do you know? What do you know about it that's now different?
There's a break in frequency.
Yeah, well, no, we turned it off and turned it back on. That is information. You know that it turned off and turned back on. That is conveying some information. What if we did this with it? What information is conveyed on that now?
Variable information?
Yeah, it's basically we did something to it, which tells us something interesting is happening, right? That's another way of doing something with it. Now we can also do this with it. What's different between one part and the other?
The wavelength?
Yeah, the wavelength and the frequency. We just modified the frequency. We could also do this with it. What just happened there? We skipped a piece of the wave. We did a phase shift. In other words, we skipped the whole part where it went down and back up. And up here, we skipped the whole part where it went up and down. That's a phase shift. We just modified the wave by changing it. We made it jump in time. And we shifted it to somewhere else. All of these are different ways of putting information on a carrier wave to make it more interesting. So these are all things that are used that we do to modify waves to make them carry information for us. This is the simplest one. This is known as continuous wave. This is what we use for Morse code. We just basically turn it on and turn it off. This is known as on-off keying. We can also take this wave and instead do this with it. This would be something that would be known as FM because we're changing the frequency. This is used for voice. It's used for packet radio. It basically is used for data transmissions. It's very, very easy to send over moderate distances. It doesn't require a constant amplitude, which is kind of nice. There's another one that we do called AM. Where we take our carrier wave and we shape it using somebody's voice in time. So this is known as the envelope. And we basically can then strip out the carrier and all we're left with is the envelope, which is the shape of the signal that's making the thing bigger and smaller. That basically gives us our voice back. That's known as AM. Now, as it turns out, AM, if we were to plot this on that's actually in time. Now we're going to start moving to frequency. So here's our frequency graph. AM looks like this, where we have a lower sideband and an upper sideband. So we have our zero frequency out to infinity. Now, AM has the exact same thing on the upper and on the lower sideband. Well, they're redundant. So why bother transmitting them both? So we can take this and strip it out, and then we just transmit the upper sideband. Well, there's also this thing in the center called a carrier, which is just a marker. It's like a reference point. Well, that has no information on it at all. So we can get rid of that. And now we're just left with a single sideband. Can anyone guess what that signal is called? I think I just said it.
SSB single sideband.
That's upper sideband. Or if we did just the lower sideband, that would be lower sideband. Those are both forms of single sideband. They are the most efficient means of transmitting AM radio signals. And they are for instance, on VHF and UHF, they're the most commonly used signals for transmitting voice for long distances. For short range, it's FM, but FM is really quite inefficient compared to single sideband. So there is on the 10 meter band, on the 6 meter band, on the 2 meter band, basically for virtually everything that you're going to do, you use upper sideband. Lower sideband is rarely used. It's only on 40 and 80 meters and down. Okay, now here's another characteristic of bandwidths. So we're going to actually put our bands. Okay, so here's our center frequency. See, Morse code is about this big. Morse code is about 150 hertz wide. And we have something called PSK, which is a digital mode. That's about 30 hertz wide. And then we have single sideband, which is about 3000 hertz wide. And then we have AM, which is roughly 6000 hertz wide. And then we have FM, which is about 10,000 to 15,000 hertz wide. Okay, this is actually a physical representation of how much space a signal takes up. Now, the bigger the bandwidth, the more information it can carry. So obviously, a higher bandwidth mode like FM is going to be the widest of all of them, but it's also going to potentially carry the most information. AM is going to be pretty good. Single sideband, we can speak a lot of information over voice. Using this mode, which is called PSK31, it's a keyboard to keyboard mode. It carries a small amount of information, and this is Morse right here, which again carries a fairly small amount of information. But what's a good reason to use a narrow band mode? Just thinking about bandwidth as a limited thing is the fact that, you know, it takes up a certain amount of space. Whatever space you don't use can be used by somebody else. One disadvantage of FM compared with single sideband is that FM has something called the capture effect. The capture effect means that basically if you've got one signal right here and another signal right here, the bigger one wins, or nobody wins if they're equal size. So that's known as the capture effect. And this is actually, I'm told, why aircraft do not use FM, because if there are two signals right next to each other or right on top of each other, they want the air traffic controller to potentially be able to hear both. They don't want people wiping each other out. There's another mode called AM. Another mode called AM fast scan television. This is NTSC fast scan TV. It's 6 megahertz wide. So why would we never use this on the high frequency bands? Because what's HF again? What are the limits? 3 to 30 megahertz, right? We would only be able to fit like 4 of them on there. There's just not enough room. So you can't use AM fast scan TV anywhere below 70 centimeters. CW is Morse code. Morse code has a very narrow bandwidth again. It's about 150 hertz. So it does not take up a lot of room. And finally, an electronic keyer is a device that assists in the sending of Morse code using a computer, basically. So DITs and DAWs, and I have one over here somewhere. And unshare that right here. One side makes DITs and the other side makes DAWs. Does it automatically so I don't have to have my wrist get really tired after operating for 12 hours. All right. We've got one more section that I could do, but I'm going to ask everybody if you want me to do that now or you want to just finish it in the morning.
I'm cool either way.
Can we do it in the morning? Because I have to head out shortly.
Yeah, okay. We'll get it in the morning. So if anybody has any questions about what we've done, I'm going to stick around for a little bit and feel free to ask.
Which pages are we covering tomorrow?
We are on 65 right now.
So tomorrow's like 65 until like 127.
Yeah, or whatever the end is. I mean, it's not really 127, but tomorrow goes pretty quick. And remember, we're doing it at 10 tomorrow.
Okay, thanks.
Is everybody doing okay? I know it's a lot of material. I'm going to stop recording.